Look at that. It's... Oh, that's really nice. So I actually had a much more formal intro, and now I'm totally, I've been thrown. So this has been a project which I have talked to some of you about for multiple years. And if you've followed me in my story a little bit, you would have known that I've been running this consultancy for a couple of years, and finally with some, it's done pretty well, and so I thought I should finally try to see if we can get Rust going in Australia and New Zealand. I feel as though this language has to be the better default for safer, more secure, and more energy efficient software. It's customary to say thank you at the end and to provide acknowledgements, but I really want to say thank you right now because there are some people that are very, very important to thank, because without them this event would not happen, or not. The wonderful branding is actually being, was actually provided mostly, although I added annoying touches, by a very good friend and colleague of mine, John, who lives in Winnipeg, Canada, who may or may not be saying hi to us over the live stream, and also there are a bunch of others, such as yourselves. Without your trust in me and trust in this conference, the event would not have happened. I also need to acknowledge the speakers, many of whom have had to basically fund themselves. I said to everybody, I don't know if I'm going to be able to secure sponsorship. So if you're able to, please pay yourself, and many of them have. And every single time I think about that, I am really aware of how much trust people have placed in this event and how much trust people have put on the future that we are building. I also want to acknowledge all of the sponsors, both LexisNexis, IDverse, who have been hanging out with us in the co-creation rooms for a couple of days, and in particular Resideo, who have also been with us working together, have come on board as sort of anchor tenants of the space and have really helped provide the financial security for the event, as well as our, I'd like to thank my customers. So I run this consultancy, I help people adopt Rust, and without them, this thing wouldn't have happened as well. And so, but most importantly would be the team. So Tash outside, my partner Katie, lots of people have helped and offered help and sort of become part of this collective project. One of the people who I am most happy to welcome into the team is Amber Craig, who will be the MC for our 2 days. I have been following Amber online for like a long time, like an embarrassingly long amount of time, and always been like so in awe of everything she does and what she stands for. And so Amber Craig is a pioneering Māori technologist, strategist, and kaupapa Māori innovator. She's founder of Te Whara Hangahanga, Whakahangahanga, Whare Haora, and she's also helping other people start their own businesses from sort of behind the scenes as well. All from the Wairarapa, which I think is kind of neat. So she's brought a whole family here. That's actually off the script. She designs Māori-led solutions for social change. Her current focus is re-indigenizing how we build our whare, our buildings, our houses. She was recently recognized for over a decade and of her digital mahi, her digital work, of winning the Tōtara Innovator Award at this year's Matahiko Awards. Please warmly welcome Amber to the stage.
Okay. Can we chuck my slides up? Okay, those aren't my slides, but that's ke te pai. Ko te manu e kai ana i te mero no nā te nahiri. Ko te manu e kai ana i te mātauranga no nā te ao. Ko te manu e kai ana i te mātauranga Māori no nā te ao tukupu. Te hei Māori ora. Te whare e tū nei, tēnā koe. Ki ngā hapu e te kāinga nei, e pupuri nei te ihi me te mana karanga mai mihi mai. Ka hiki ngā roimata ki ngā mate, ngā aitua o koutou ara o mātou. Ka tangihia e tātou i tēnei wā. Haere, haere, haere atu rā. Hoki mai te wairua ki te kanohi ora, ki ngā kai whakareti o tēnei kaupapa koutou e whakawhāiti nei, e te iwi o rust. Nau mai, haere mai ki tēnei kaupapa whakahirahira. Nō reira, ki raro i te maru o rangi nui e tū nei, kia papa tuanaku e takoto nei. He karakia nā te ururoa flevo. He pō, he ao, he ao. Tākiri mai te ata, kōrehi nā manu, ka pō, ka ao, ka awatia, tihei Māori ora. Ko waia hau, no ko te rana no inarangi no konei hoki o kutupuna, hu uriau no tara ika, rātou ko rangitāne, ko kupe, ko Amber Craig taku ingoa, kei aku rangatira tēnā koutou, tēnā koutou, tēnā koutou katoa. Kua mutu noa nā kōrero Māori mō tēnei wā, tēnā koutou katoa. So, today I opened this conference in our Indigenous language here in Aotearoa, New Zealand. It is under threat here from our current government, and so it is important to share with you our language so we can all uphold the mana of our reo, our language. My whakatauki, or a proverb that I opened with at the beginning of this, talks about the consumption of what we eat. That when we, as birds, feed on their food, the metalberry, they get the forest. But when we feed on knowledge, we open the world. Or in the adaptation of this whakatauki from my ancestors in Moa Upoko, we talk of Indigenous knowledge unlocking the universe for us all. I see the Rust Conference here as a way for us to share and acknowledge and unlock knowledge together. To share our learnings, or our mātauranga as we call it in Te Reo Māori. My name is Amber Craig. Oh yes, here. So this is where I live, Waiohini Gorge. This is my marae, Papawai. And this is another place that's very close to my heart, is Onuki as well. I am your MC for the next 2 days. My ancestors are Indigenous to here, and even to this spot as well. But I also have ancestors from Scotland and England as well. Part of my kōrero or talk this morning acknowledges those that are from this land, acknowledges this house or this whare that we are within. It also acknowledges the dead of our ancestors who travelled with us and guided us today. And then I welcomed yourselves. I've heard that we have some people in this room from over 11 countries, which is very exciting. So we want to welcome you to here, and for you coming to share our learnings, or your learning, your whakaaro, but also for us as Aotearoa to show you ours. I have a few things to run through to make sure that everything, hopefully over the next couple of days, goes really smoothly. So let's get into it. What I will try to do is there will be a bit of te reo during the next couple of days, so I will try to put translations up. I am going to prefix it with some of our kupu. You could write a whole thesis on, and each kupu can, each word can have its own concept. So I've roughly put a translation up there, but it can have very many meanings. Right. Let's go back because I don't want to terrify you just yet. And I also realise that I'm between you and the speakers right now, so let's get into it. On checking in at reception this morning, you would have been given a badge. These are most likely dark blue like this, right? But there are some who are green like this, And so these are the people that are able to help you out. They're part of the Rust conference team. We also have, and I really love them, these funky 80s badges that remind me of my childhood. And these are our VIP guests. So they will be our tamariki, our children. And there are a few who have managed to win some conferences or swindle their way into getting one of these cool badges, which hopefully will be me by the end of this conference. But if you do see a child by themselves with one of these badges, if you could please let us know at the reception desk, or if you feel comfortable enough escorting them to the reception desk, because most of our VIPs should be with someone. Right. Now to health and safety for our day. So keeping ourselves safe during this event is paramount, whether that is physically, mentally, emotionally, and or spiritually as well. Our code of conduct is very close to our heart for this event, so we expect everyone to uphold it. If you don't, you won't be attending anymore. It's pretty much that simple. If you're feeling unsafe, the actual details, now just to clarify, the details are on the back of the blue one. If you have a green one, you probably should know those details and you might need to check your Discord channel. But on the back of here is actually how, if you're feeling unsafe, what are the details for how to actually report that. We do want to know because it's really important to us. We also have a co-creation space, and that will be opening up during morning tea. It's the far room down the side here. So you just keep going. If you exit the building, you're too far, it's the room before that. So this is a space for us all to get together, collaborate and create. Another thing as well is, I just realised I put this in. We have a different emergency services number if you are not from New Zealand. So I'm just going to put it up when we're going through health and safety. Our emergency number, if you ever are in an immediate emergency, 111. Okay, te pai? All good. Right. Discord. We also have Discord for this event. It's a way to share information with everyone else who is attending as well. If you want details on how to join, this is also on the back of your lanyard. It's a very handy lanyard. But that's a cool place where I've already seen people being able to share details about where they'll be, social events, all those types of things. Okay, te pai. So, if there is an earthquake, aka the whole building shakes, you need to stop, drop, cover and hold. I've put this up because I realised as well with over 50% of the people here not being from New Zealand, you may not have experienced an earthquake. It's quite a regular thing here in Wellington, so don't stress out. Just if we start panicking, then you panic, okay? Ka te pai. In the green team, you've got to maintain your calm composure, please. So it's actually safer for us to be inside than to run outside. So that was one of the things that we learnt during the Christchurch earthquake as well. And so basically, I just chucked this up so that you guys can know that while we're in here, it's probably safe just to cover your head. But when you're in the other rooms, it's better to get under the table where you can. But we're talking about if you're right beside it, not if you're going to run across the room. Also, if you're near a doorway, is also a good place to sort of brace yourself. If there is a large earthquake, there may be an evacuation where we need to go to higher ground. Our team with the green lanyards will let you know if that is the case. We are quite vulnerable here in the, I was going to say in the Wairarapa, but we're in Wellington. Location check, Amber. So we just need to make sure that there's no risk of tsunamis, but the team here at the event centre will let us know. If there is a fire, you will hear alarms and you will exit at either end. So we've got big, large signs that are pretty well lit, and so you'll be able to go through all of those. And there's ones here, and then you can go out through both ends as well. If there's any other emergency, you await instructions from the Rust Forge team with green badges. And I think that is all the health and safety that I can think of at the moment. We've tried to prepare you as much as possible, but hopefully we don't need any of that. So, I am going to welcome our first speaker. So our first talk is Engineering the Future at Adobe by David Sankel. David is a principal scientist who leads Adobe Software Technology Lab and is an active member of the C++ Standardization Committee. His experience spans microservice architectures, CAD and CAM, computer graphics, visual programming languages, web applications, computer vision, and cryptology. Nope, that's not the right word. Cryptography. Katapai. He is a frequent speaker at C++ conferences and specialises in large-scale software engineering and advanced topics. David's interests include dependently typed languages, semantic domains, EDSLs, and functional reactive programming. He was the project editor of the C++ Reflection TS, as a director of the Boost Foundation, and authored several C++ proposals, including pattern matching and language variants. He also wins the award for the most acronyms in his bio. And so we're going to give a warm welcome to David to come to the stage, and he's going to share his presentation.
How's everybody doing this morning? All right? Cool. So this talk is a very special talk. You're in for a treat because this talk is a talk that they don't want you to hear. Yeah. In fact, so I had a podcast interview with Tim, I don't know, a few weeks ago, and it went out on the internet, and it went on, Rust Reddit. Everybody was very nice. It went out on the C++ Reddit because, it's talking about C++ interop as well. And maybe they were a little bit less than nice. So just to give you a preview of some of the things that were said on there. So Rust sales talk, brings bad vibes, cheap clickbait tactics, ulterior motives, saboteur. All these people actively sabotaging within the committee, because I'm on the standardization committee. Someone actually responded to this one and said, the committee doesn't need David Sankel's help to sabotage itself. Which I think is true. Rust people trying to sabotage C++. The Rust community as a whole sucks. And my very favorite, David Sankel is a cancer. So have you seen the candy cigarettes that they have out in front there? So yeah. Now, to be fair to the C++ Reddit moderators, they did actually delete that post. Because apparently, they draw the line at comparing somebody to a debilitating illness that kills millions of people every year. So, I mean, I'm glad that they have a line. But in truth, I actually am a cancer, okay? According to the Zodiac. So this was a very true statement that was put out there. Now, for the conspiracy-minded among you, what is the zodiac sign for Cancer? Coincidence? Maybe. Maybe not. But anyway, let's go back to some reality. So this is what we're going to talk about in this talk. Okay, why is Adobe incorporating Rust? Why are we moving to Rust? What does it look like? What's our process? Where are we at with our phase introduction? Right, this is what we're going to talk about. And this starts way back in 1990. So this is Adobe Photoshop 1.0. And when we bought software and it came in gigantic boxes. It up, all black and white. So in 1990, something happened. So Adobe Photoshop, does anybody have a guess as to what Adobe Photoshop was originally written in, its original language? Pascal, yeah. Object Pascal was what it was written in. And something happened in 1990. There was essentially a big industry trend where Unix was becoming a very big thing, right? Everybody thought the future was going to be Unix. And so C and C++ were like part of that. Another major thing that was happening is that we needed to port our software over to Windows, because at this point it was only Macintosh, and the Object Pascal libraries we were using were not like a Windows thing. And so we did. We converted all the lines of Object Pascal over to C++ at that time. And it's been C++ ever since, with the addition of some like scripting languages on top and such. But anyway, we made this transition. And if you look at the Photoshop code base, you can actually see some remnants of the original Object Pascal in it based on like the naming conventions and stuff that were part of that conversion. So these kinds of industry shifts have happened in the past. They don't happen very often, but they do happen. And it happened for Photoshop way back then. And so that kind of brings it to my team, which is the Software Technology Lab. So this team, our goal, our responsibility is to keep an eye on the 10-year horizon of software development practices. What's going to happen in 10 years? How do we create the kind of future that we want to have in 10 years for software development? So we do a lot of research, we do a lot of interacting with the community, and we do a lot of strategic thinking. And so this team consists of the most amazing engineers I've ever been on a team with, Dave Abrahams, Sean Parent, Mark Hamburg, and Nick DeMarco. And these are just like absolutely top people. They've done amazing things like created Lightroom or a co-creator of the Swift programming language. So like very, very strong, powerful team that I joined. And it was really intimidating to join, but now I lead the team. And one of the first things that we needed to do was address something that happened. Okay, so Chandler Carruth in 2022 gave a talk at CPP North talking about the Carbon project. Okay, so this is like a new programming language that he was trying to create for Google. It was like an experimental programming language. But essentially he introduced this idea of a C++ successor language. Like what comes after C++? And he cited two reasons for this. One, C++'s complexity has been growing year after year after year. And right now we know that the #1 complaint that C++ users have about C++ is the complexity. And we have no solution for that, right? Everything that we do to C++, we just continue to pile on more and more complexity in order to try to evolve. And the reason why we have to add more complexity is to retain the backwards compatibility. So that was like #1 reason why he wanted a C++ successor language. The second reason was he didn't think that ISO was a good way to evolve that language at that time. ISO is a very bureaucratic process. It involves multinational politics sometimes. You have to get like a lot of consensus in order to make change. He felt like something more rapid would be more appropriate. And so we started looking into this. We started trying to figure out, okay, what are the possible C++ successor languages? We looked at Zig, we looked at Rust, we looked at Swift, we looked at Hilo, pretty much you name it, we looked at it. And what we thought at the time, after investigating all this stuff, is that the most likely successor language for C++ is actually C++. There's just a lot of industry momentum behind it. The benefits of lowered complexity that these other languages bring, we did not see that being enough of a pull to move out of the C++ space. And that was our conclusion. And we did note that Rust, it has been getting uptake. So this is the percentage of C++ developers that also use Rust. If there's going to be a successor language, we're going to see a lot of overlap between the communities. And so in 2019, 6% of C++ developers also said that they're Rust developers. In 2020, that increased to 10%. So we did note there is something happening with Rust. But still, for like big companies, it doesn't make any sense to switch over. C++ seems like the best place to invest. Okay, but then some stuff happened. So in September 2022, this EU regulation came out. It's the EU Cyber, I forget the name of the thing. Cyber Resilience Act, thank you. So this act came out, and it basically said that software manufacturers need to have some kind of responsibility for how they do their software development, for producing secure software. Nothing mentioned memory safety or anything along these lines, but it essentially started the process of this idea that software developers need to be responsible for the software they create in terms of its security profiles and such. And then in November 2022, the NSA came out with a document talking about software memory safety and talking about how important it is, how big of a deal it is, memory safety in terms of like security profiles, and that they were generally recommending using memory-safe languages. Then in July 2022, there was HR 7900. So HR stands for House of Representatives. This was a defense spending bill, like a routine defense spending bill that went through Congress. And the House version of this actually had the creation of groups to investigate memory safety things to try to improve memory safety with regard to procurement and things along these lines. That part was removed when it hit the Senate, but the fact that this happened sent a huge shockwave in the industry because we're talking about regulation related to memory safety. And then in January 2023, Consumer Reports, of all places, came out with Future of Memory Safety Challenges and Recommendations. This was making very specific suggestions on how to improve memory safety through regulation. March 2023, the White House came out with a national cybersecurity strategy talking about memory safety. September 2023, the America's Cyber Defense Agency came out with the urgent need for memory safety in software projects. In December, there was the case for memory safe roadmaps. Another document came out from the government. And in June 2025, which is just recently, the Cybersecurity Information Group came out with memory safe languages, reducing vulnerabilities in modern software development, calling for use of memory safe languages. And I just want to give you like a sense of some of the verbiages that are used in these documents. First one, developing new products in C or C++ when a memory-safe alternative exists is, quote, dangerous and significantly elevates risk to national security, national economic security, and national public health and safety. If you use C++ software, you can get sick. Existing C and C++ code without a published memory safety roadmap by January 1st, 2026 is dangerous. Okay, software is now dangerous if it's not in a memory safe language. There were a couple of pretty important points that were made in this, and this is really important for a big public company like Adobe. One is the regulatory aspect of it. So one of the big things that was threatened in these documents is related to public sector procurement, right? We sell Adobe products all over the world to all kinds of people, and part of that is governments. You know, governments use Adobe Acrobat, and they were saying, and all of our software really, and they were saying that they're going to put obstacles to procuring software that is not following good memory safety practices. So they didn't define exactly what the good memory safe practices are. They essentially boil down to using memory safe languages for new code. Don't continue to write your software in C++. But that can cost us millions and millions of dollars if such a thing were to pass. But that's not even the worst one. The worst one is related to reliability in software. So if you install a piece of software these days, you usually click accept to some kind of ridiculously long agreement that you don't read, right? Part of that agreement says that if something were to happen because the software has a defect and you were to have any kind of financials losses, that's your thing you have to deal with, right? So if you get hacked because of using some kind of software that had a vulnerability, you go to the software manufacturer, they're going to be like, yeah, really sorry to hear about that. We'll sure try to patch that. But this is changing the game. This was saying that if you are not following memory safety best practices, you can be held liable to the damages that are caused due to vulnerabilities in your software. That's huge. What's the cap on those kinds of damages? Who knows? So with all this coming out, we gave this C++ successor language idea another look. Okay, and the first thing that we learned is that any C++ successor language absolutely must be a memory-safe language. There is no compromise there. That eliminates a whole bunch of things that were on our list. The second thing is that a C++ successor language, it really can't be C++, right? We can't see a way to make C++ memory safe and just oh, you use C++, it's memory safe. So we needed to find an alternative. Right, and we're looking for it. But what is the deal, memory safety in C++? Just to give you a hint of what that looks like. So here we've got some code. Here we create a vector of string, which is basically a list of strings in C++. We push back, add to the end of the list, hello, and then we get a reference to the first element of that string list. And then we push back world to add to the end of the strings list. Does anybody see any problems here? Yeah? Go ahead, shout it out. Reallocation, yes. If that pushback happens to produce a reallocation and it moves that memory to a different place in memory, that first string reference is a dangling reference, right? There's nothing that it points to. So if you go and then assign something to first underscore string to that reference, then boom, right? This is a memory safety violation. And the thing that's really annoying about it is it's a memory safety violation sometimes, right? Depends on your compiler. It might not necessarily do that reallocation. This bug could, just pop up because you happen to upgrade your standard library version, and now all of a sudden you have a vulnerability in the wild that can be exploited and, do all kinds of damage. But, how frequently does this actually happen? So here's some data. This is vulnerability root causes. First, take a look at the Microsoft data. 70% of all their vulnerabilities, this is their numbers they published, are due to memory safety issues. Google Android project, 76% of their vulnerabilities are due to memory safety issues. Chromium, 70% of their vulnerabilities are memory safety issues. Now, Mozilla released a list of all of what they call critical vulnerabilities, right? And of their critical vulnerabilities, 94% are memory safety related. And then there was a compendium of total zero-day vulnerabilities that came out in 2021. So zero-day vulnerabilities, these are ones where the vulnerability is found in the wild by some kind of attacker, and that's how the company finds out about it, is that someone's attacking their customers. 67% were due to memory safety issues. And I can tell you that Adobe's own numbers, I looked internally, they're along the same lines. Like, we're not special. This just seems to be about like where it's at. So, okay, this has been going on for a while. Why are folks making a fuss about it now? Right? We've already known, yes, C++ has undefined behavior, it has these vulnerabilities, and we know that there are safe languages. Safe languages have been around for a long time. You got Java, all this other kind of stuff, C#. If you want to write software, basically, you would use these other languages. You would use these memory-safe languages, and you would only use C++ if you absolutely had to because you needed it for performance, right? That was the thing. So what are you going to do? Why is this a big deal all of a sudden? We already knew about this. The thing that happened is Rust, okay? It's really nothing other than Rust, because Rust demonstrated on a practical, large scale for the first time that you can have high performance and memory safety in one language. So then all of a sudden, if you're writing new C++ code, especially in a safety critical situation, it's like, why are you doing that? Like, there is an alternative. Like, why are you putting people at risk? They can get sick, right? So great, cool. All we need to do is rewrite all of Adobe's code in C++. Right? Does it sound like a good idea? It's not really a good idea. Like, just think about that. Like, Adobe's been making software for, I think, like 30 years, maybe 35, 40, I don't know, somewhere around there. In order for us to rewrite all this stuff, okay, maybe if we are faster the second time we write it, it could be maybe 20 years. We rewrite all of our software, and in the meantime, we don't create any new features. We just focus our entire development organization on rewriting stuff in Rust. No, that's like completely not a viable solution. But fortunately, it doesn't have to be a viable solution. So this article came out in the Usenix conference. It's called How Long Do Vulnerabilities Live in Code? A Large-Scale Empirical Measurement Study on FOSS Vulnerability Lifetimes. The important thing is essentially this graph over here. So they took a look at every vulnerability that got created in their large code bases that they were looking at, when did the vulnerability get introduced, and when did it get fixed, okay? And like where you see 1,000 up there, that is how many vulnerabilities lived 1,000 days from the introduction of the vulnerability to when the vulnerability gets fixed. And what you see in this graph is obviously it clusters to the left, right? Which essentially means that most vulnerabilities are fixed pretty soon after they're introduced, right? If you go within like a few years, you kind of get the vast majority of it. Of course, there's more vulnerabilities that are coming. There's the long tail, like something got introduced like 20 years ago, and then we just discover it lately. But the vast majority of vulnerabilities are coming from the new code that people are creating. So if you start your new software development in a memory-safe language, then you are going to get a drastic reduction in the number of vulnerabilities that you discover just because the old code kind of hardens over time, right? Whereas the new code is the more dangerous stuff. That's good news for us because that way we can stay in business. But this also played itself out in Android's shift of new development to Rust. So what you see here in the blue is the percentage of new memory unsafe code that they add to their code base. So you see like in 2019, it was about 80%. And that shrunk down to till about 2024 when it's like, I don't know, 25%, 30%, somewhere around there. And the red lines, or the red bars, are showing you the percentage of vulnerabilities that are related to memory safety. And you see that that drastically reduces. So you don't need to rewrite all of your code. You just need to make sure that you transition new development into Rust, and then you can get the memory safety benefits. So additionally, the industry itself is just converging on Rust as a solution to C++'s issues. So Google donated $1 million to the Rust Foundation. Google staffs a Rust C++ interop team. I actually just met with them last week. Great people, doing really good work. Microsoft donated $1 million to the Rust Foundation. And Microsoft actually has an internal order of preference for the languages that you use inside of Microsoft products. Number 1 is C#, makes sense. Number 2 is Rust, and failing all those is C++. Now that's really interesting because Microsoft produces Microsoft Visual C++. It's like a part of like their business strategies. They make a lot of money on C++. But even with that, like they recognize the issues with C++, and I think it's mostly driven by memory safety issues. And they flat out banned C++ on their Azure platform. And it's not too hard to understand why. Because when you talk about memory safety vulnerabilities, if you have a vulnerability on a desktop piece of software, someone gets hacked, you know, that's a big deal, and I don't want to discount how big of a deal that is. But if someone is able to hack your cloud platform because of a vulnerability, it's not just one person's data, it's like whoever else happens to be on that machine at that time. Like, this is super dangerous. And then Meta, they're using Rust extensively internally, and they're rewriting a lot of their infrastructure code in Rust. So we're seeing this industry convergence. And again, remember, we're trying to figure out what's on the 10-year horizon, and things are all pointing in the same direction. We did look at some alternatives. We looked at C++ profiles. This is something being talked about right now. So the idea is you can opt into certain memory safety features on a per file basis. This is really very much in the idea phase in ISO C++ right now. There have been some slide decks which said, hey, you know, we'd love it if it would find issues here, but some experts have pointed out, like, there's no way that you think that does what you think it does, and there's no implementation of this. So even in like the most ridiculously optimistic terms, this thing wouldn't even be start to delivered until like 5 years, right? And I don't think that that's going to be enough time. Even if you do, they are able to actually find something solid for this. There was Safe C++, so this was created by Sean Baxter. And his idea was to incorporate a Rust borrow checker into C++. And he actually did it. It was very, very cool tech. Unfortunately, Sean discontinued this effort. No one else is pursuing it. The reference implementation was completely closed sourced. There was strong pushback in ISO. I think it was because some people wanted to push towards the C++ profiles direction, but also there were concerns about the large amount of additional complexity this would add to C++ in order to make it happen. You would actually need to have a whole like parallel standard library separate from the normal C++ standard library. And so we've never actually added that much complexity in the C++ like at this level. And given people's complaints about complexity in C++, it's unclear that this would actually work in practice. It might just be the thing that tips everything and like, I can't learn this language, it's way too complex. We also looked at Swift, right? Swift is a great programming language, I like it a lot. Swift, there's risk of vendor lock in there because it is controlled by Apple. And just more significantly, it's just not getting uptake for cross-platform development. Nobody seems to be just going in that direction. You know, if a lot of people were flocking to Swift, that would be a different story, but that's not happening. So all that is about memory safety, right? But there are two other motivators for shifting new development to Rust from C++. And actually, they're the ones that I'm actually more interested in. Memory safety kind of came along the side. The first one is that, on balance, Rust is just a better technology for most applications, right? There's the language mechanisms, enums, pattern matching, traits. And I gave a whole talk on this at C++ Now in 2022 before we shifted in this direction, Rust features that I want in C++. The procedural macro-driven libraries are awesome. The engineering features are really, really good. The documentation, you know, coming from C++ into Rust, I've had this experience, a lot of other people have had this experience. It feels like moving from economy class to business class. You know, it's like, oh, this is nice. You know, I get the warm napkin and everything. Like one of those feelings is when you write your little documentation snippet and Rust is like, I'm going to check to make sure that compiles for you. You know, it's really good. Excellent tooling. Getting a dependency, you know, in Rust compared to doing that in C++, oh my gosh. Ergonomics are fantastic, great error messages, and the community itself is really good. I have yet to be called a heart condition in the Rust community or tuberculosis or anything like that. I just give it some time maybe. Reason number two is related to the trends in programming languages. So remember when we had this graph up earlier, right? The growth of the percentage of C++ users that are also using Rust, 6% to 10%. Well, I've tracked that further, and this is how it's gone up until today. It has gradually risen up to 25% of C++ developers are also Rust developers. 1 out of 4. That's huge. This blew my mind because I didn't look at the latest 2025 number until I was preparing this talk. Like 1 out of every 4. If you consider how many C++ developers there are in the world, the millions and millions there are, how many of them also know Rust? Like this, and these are languages that are in the same space, right? These are like high performance system level programming languages. So this is happening, right? Here's another graph that I think is interesting. This is age on the horizontal axis, and the desire to program in C++ versus the desire to program in Rust. And both of these are from the Stack Overflow surveys. I should have mentioned that. I think it has like 65,000 respondents, so it's good data. If you look at the Rust side, you can see if you're on the 18 to 24 range, if you're a youngin, 24% of all software developers in that age range want to use Rust. And look at how that drops down. Only if you're 65 plus developer do you want to use C++ more than you want to use Rust in general. But this demographic slide, like it only shifts in one direction, right? Like the 65 pluses right now, they're not likely going to be in the programming area in 10 years, right? So all this is going to shift over like 2. And we see that there's a larger number of people that are interested in Rust versus C++. And this is important. If you want to like hire a development team, it can be really hard to staff a team, as it is right now, with C++ people. It can be very difficult. And so some may even decide which language they're going to use based on how easy it is to staff the team. And so as we see this demographic trend, we want to make sure that Adobe doesn't put itself into a situation to where there's not enough of a pool of people that we can hire to work on our products. So this is really important as well. Then there's the JetBrains Language Promise Index. So this is an index that JetBrains came out with based on their own surveys, which are, I think, about like a third the sample size as the Stack Overflow surveys, but still really good data there. So this is based on audience growth over the past 5 years, the stability of this growth, the share of people expressing an intention to adopt a language, and the share of its users who want to adopt another language. And so they came up with this index, and these were the results. Rust was actually the second highest in the Language Promise Index. The only one that was higher was TypeScript with 199 points, right? Very, very close. And then way down the line, you get C++, which is like almost half that of Rust, and then even lower than that, you have Swift. And this is really important data for JetBrains. They produce software for developers, right? They want to make sure that they're investing in, basically IDEs in the languages that people are going to use in the future. And so JetBrains came out with the Rust thing, I'm sure based on this data. Okay, so why are we moving to Rust? 3 reasons. Number 1, we want to build safe software. We actually care about our customers. I shouldn't say we actually care about our customers. We care about our customers, okay? We don't want them to get sick. But we really don't want them to get hacked. And we really want people to be able to install Adobe software and not be afraid of North Korean state actors hacking their system and stealing their data. We also want to use state-of-the-art tools to build state-of-the-art tools, right? We're trying to make the absolute best products for our creative people. Like, we want them to have the most awesome photo editor, the most awesome video editor. Why would we want to give our developers something less state-of-the-art? We want to give them the great tools that they need so that they can be productive, they can be excited about what they're doing, and delight our customers. And then finally, to address the evolving software developer demographics that we just looked at. Okay, great. But what's the plan? Like, how do you even do that? And we're certainly not at the point to where, like, yes, we've moved our development to Rust, all of our new development to Rust, and we're all happy. No, we are part of the process of moving in this direction. So step 1, confirming viability. Creating some pilot projects, right? We had some self-contained pilot projects. We staffed them with trailblazers, people that are not afraid of, like, oh, this doesn't work. Well, I'm going to have to go over here in this area that's outside of my area of expertise to make this work. Basically, get the people in there to just prove out, make sure that this thing can actually work. And as going through these process, note the pain points. Keep track of, like, what were the issues. And also ship as part of flagship applications. Because going all the way to shipping as part of flagship applications, you learn a lot more stuff. You might learn things about deployment. You might learn things about, different versions of different surfaces that need to be addressed. And so we've done this. We've completed our step 1 to confirm viability, and now I think pretty much all of our flagship products are shipping with Rust code as part of it at this point. Step 2, address the infrastructure gaps. Give Rust a first-class build system support. If you're using CMake, great, is probably going to be easier for you. For most large organizations like Adobe, we have our own build system internally. So we had to make sure that that build system can support Rust code in a first-class way. Don't make it so it is harder to add Rust than it is to add C++. It's got to be the same or better. Get a training program started. So what we did for the training program, and I highly recommend, is this comprehensive Rust course. Maybe, I don't know if you're familiar with it or not, but Google released all of their training materials for teaching Rust. And it's available online. You can download it. You can adapt it. And what we did is we just took this, gave it to some instructors, and we ran this course inside of Adobe, and it was like a multi-day course, and it was very successful. And the third one is to make industry connections. Right? I'm very well connected in C++. I've been on the standardization committee for like 10 years. I've been to all kinds of conferences. I know who the people are. I know who the actors are. In Rust, I'm in a different area, right? I don't know a lot of the people here yet. And so we had to make a conscious effort to go to conferences like this and talk with people, to take part in the Rust Foundation effort. So now I'm part of the T-Lang interop group, which is doing C++ and Rust interop. So that's step 2, and we've done that. Now we're in the step 3, which is socialization, right? So we're in the middle of this step. We created an internal meetup so that there's once a month, we have someone coming in to talk about Rust things, or usually someone internally talk about Rust things, so that people can upskill, right? We need to make it easy for folks to get gradually acquainted with Rust. And having a meetup internally is a great way to do it. Gradually communicate an ergonomic development story, right? It has to be ergonomic. You have to, it's so much better to use the carrot than it is to use the stick, right? Show, hey, it's really easy. You want to use Rust in this new project? Like, it's easier than using C++, right? You want it to be that ergonomic. Provide support, training. We have it set up to where if some team wants to get some kind of training in Rust, we can do the comprehensive Rust course for them. And number 4, requiring Rust for new high-performance safety-critical components. What do I mean by a safety-critical component? Anything which is reading untrusted input, I would say is safety-critical, like a JPEG reader, a PNG reader, PDF reader, any kind of like new file format which you are reading off of disk that could potentially be provided by someone on the internet, that's safety-critical. And I would say that at this point in time, using C++ for that kind of a project is reckless and inappropriate, right? Why would you put your users at risk of having vulnerabilities when there's an alternative sitting right there, right? And so this is really important that we do this like starting right away. And step 4 is the new normal, right? This is where we want to get to. The expectations that system engineers have Rust proficiency, whether it's through the course, where they learn independently, where they learn it from somewhere else. The base expectation is that if you're a system level engineer, you have a level of proficiency in Rust. And that's where we want to be in Adobe. We want Rust to be the default choice for new work. So it wouldn't be like, hey, should I use Rust for this new project? It's more like, is there like some kind of special circumstances that would make you want to use C++ here instead? And there's always going to be those kinds of projects, right? If you're working with a large code base and you need to tweak something in the C++ legacy code, tweak it in C++. Don't like force people to rewrite that stuff in Rust, right? But if you're going to do something which is going to require multiple files and you're going to do like a sizable thing, that should by default be done in Rust. And the third thing with this step is the Rust platform team, right? Creating a team which is going to be responsible for the Rust tooling, the Rust infrastructure, the Rust community, people to reach out to. Like if you need help, if you want to get a Rust expert to communicate with or sit on your team for a little while, that should be made available for you. So that's step 4. And so there have been challenges, right? This isn't easy. First, you need to have patience and persistence with management. And this actually isn't as bad as it sounds, right? Management gets it, right? If you talk about the upcoming legislation, if you talk about the demographics, the graphs, like the data, like they get it. It's like, okay, yeah, we need to do something about that. Developers are actually a little bit harder, right? It's harder for me, right? So I'm C++ expert. I've been doing it for decades, right? I really know what I'm talking about with C++. When I move over to the Rust zone, now all of a sudden I'm a newbie again, right? And I wouldn't consider myself a newbie now, but I'm nowhere near a Rust expert like I am a C++ expert. And when you move from like really knowing what you're talking about to I really don't know what I'm talking about, that's a hard mental shift for a lot of people. And so you've got to be patient with that. And just like, look, it's going to be tough, but we are going to help each other along and we're going to get there together, right? That's the message. Don't fight the people on Reddit who really want to, stick with C++. Just look at this as an evolution of your person as a software engineer, right? We're not language people, we're software engineers, we're making products. And to be a good software engineer, you have to take on and learn the newest technologies. It's just how it is. The third challenge that we've had is that it can be easy to underestimate the infrastructure costs of these things. You have to account for that. Microsoft is also as well, has determined that they have like big infrastructure costs in terms of like moving to Rust. Account for it, plan for it as part of the expense. Don't whitewash it and say like, oh, it's not going to be that big of a deal. It's going to be really cheap to move over to Rust. It's not, right? Just build system alone is a really huge deal. And that's not talking about CI and all the other stuff that go along with it. And then finally, C++ Rust interop is a pain point. And in our experience, it's been definitely a pain point. But this is improving very rapidly. So just to give you a little preview, so we've been investing a lot in C++ and Rust interop. And we've been using Zengar, which is an excellent, excellent C++ Rust interop solution. And right now, Zengar has an IDL that you use to expose Rust to C++. But what we're working on, and we think that we can deliver by the end of this year, is eliminating the IDL layer to where you can just call Rust code directly from C++ without having to do anything. And here's just a preview of that. This code you see up here, this is C++ code using the Rust PNG library under the hood. And generator.h provides all the stubs that you need to be able to use it. And it looks kind of like Rust code, right? You see the unwrap and stuff like that in there. We're just calling the Rust code directly. And so that is where we're headed. And I'm very, very excited about that. But that would be a completely different talk. So this is the conclusion of my talk. I'm very much looking forward to enjoying the rest of the conference with you all. Again, my name is David, the cancer, Sankel. And now we'll be taking questions. Thank you.
Thank you, David. Do we have any questions? Any partai? Can I just have a mic runner? We've got another. I'll turn on 3. Just might need to turn it on. The mic guy will just turn it on. Hang on. Is it number 3 on the bottom? Yeah. Yeah, I'll repeat it then.
Yeah, I will be loud.
And short and distinct, eh? Yeah, okay, Kalpa.
You mentioned it's fairly safe to introduce in the new code or where it benefits the most. That's clear. But what about actually the bridging with existing code? Whenever you modify existing code, you still introduce. There is high risk of introducing vulnerabilities when you modify existing code. What about the approach of modifying existing code with injecting Rust gradually and replacing it by eating it away?
So if I can just summarize, because you've got people online for the live stream as well. So while there is interoperate working together, the code, what is the impacts of modifying that previous code and the vulnerabilities that you might open up there? Is that good enough? Yeah. It'll do. That's what he said, live stream people. Okay, great.
So there definitely is an aspect of that, right? If you, especially on the interop layer, if you're doing manual interop, like making your own C functions and things like that, that's like unsafe Rust code if you're doing it in Rust, right? So there definitely is the risk of vulnerability is there. And then also you're going to be modifying C++ code, which can introduce vulnerabilities. To get the drastic reduction in numbers that we're looking for, that isn't that big of an issue, right? Because just the fact that the majority of the new code is being created in Rust means that we're going to have a reduction in vulnerabilities, but it's not going to be perfect. We'll still introduce some vulnerabilities because we're touching that C++ code. The idea of introducing Rust gradually by little snippet here, little snippet there, I haven't seen yet a good enough interop solution that would allow that kind of a thing. And I also worry a bit with doing that kind of introduction of having the programmer have to have all the complexity of Rust and all the complexity of C++ in their head at the same time. So for us, our strategy is much more try to find the more coarse units rather than the granular units. So that way, when you're in Rust, you can think about Rust, and you're in C++, you can think about C++, and you don't have to do a lot on the borderline.
So I saw that in the last slide, maybe we can go back to that one, that you had the calling into Rust and we have the unwrap. What sort of behavior are you expecting to experience there? Are we expecting to sort of have enums from Rust accessible into C++, or would the unwrap sort of trigger a C++ panic, and in that case you might want to have like a try-catch block, or sorry, I'm not a C++ programmer, so I don't know if you use try-catch, but something like that. Like, what would the story be there?
So in terms of unwrap, like the idea here is that this would do exactly what it does in Rust, which means that it could abort, it could, do a panic, like unwinding. This is just kind of sloppy slide code. That's why unwrap's being used at all. But I think that the intent is that you would use these APIs from C++ like you would Rust. So if you have a result type, you're going to want to be able to, well, you can't do pattern matching in C++, but you'll do like some if conditionals in order to be able to check which branch you want to use and such.
Jump, Tim, jump.
So when I have done interop between Rust and C++, and particularly C, we end up finding that we're beholden to the C ABI and how C lays everything out. Have you found, in your experience, a way to not have that be the de facto default ABI for the interop, or are we just kind of stuck there until we're all the way over onto Rust and we've migrated away from all of our C++ in 20 years?
So with Zengar, it's definitely following the approach of using a intermediate C ABI layer. But it's very basic. It's like passing void stars back and forth to communicate. For us, it's mostly transparent to us. And with link time optimization, this stuff can even be removed. But we don't have a solution outside of using that C ABI. C is kind of like the Latin of programming languages. Like everybody's using this for interop everywhere, and I don't expect that to change much with the Rust C++ interop.
Hi, hello. It's working. On the chart for C++ developers that also know Rust, I noticed it didn't grow in 2024. Do you have an idea of what happened then? It's okay if you don't have an idea. I would just thought it was curious.
I have no idea. Some group of people got really upset. I don't know, it's really strange. Another interesting thing is on this slide, how come there's so much interest in the C++ in 18 to 24 range?
Lack of experience.
So lack of experience is what was said out there. Like video game development, they don't know about Rust. Like, I think that the best theory I've heard is that they're in EDU, right? They're kind of, maybe they hear about C++ as part of their curriculum and stuff, and maybe they don't hear about where C++ sits in the wider ecosystem until they get out of college and work for a few years. I don't know. But yeah. What's that? Oh, it's the old people teaching them at university. Maybe. Yep.
What's your recommendations for developers in a large organization who aren't in a position like involved in a team like yours, which I guess more access to management to be able to have conversations like this about strategy? For the people who are sort of at the bottom of the food chain in a large organization, how do you recommend, what do you suggest is the most effective way for individual contributors to advocate for Rust internally that is has a chance of effectiveness in filtering its way up through management?
That's a good question. So, everybody has their role, and they're in this like box, which is their role, and there's an expectation that they stay within that role. And me personally, I don't really do boxed in, right? So I get slapped down all the time for doing things that are like outside of my role. But I would say that it's really, it doesn't matter what your role is if the information you're presenting is compelling. If you go and you say, hey, I have a concern, there's some data here that I would like to explain to you all. I mean, I've laid it out for you. You can use these slides and just say, I think that there's a concern here and maybe we should be addressing this, and here's a proposed plan. Or you can get some other engineers to agree with you, but basically building a really solid case that you can't shoot down is your best ammunition for that kind of thing. And I think it doesn't really matter what your role is, because you might get an executive that's like, hey, I'm gonna help support you and help get this to the next level and such.
Hey, I see that Rust's kind of one of the cool languages, but Zig and Go also seem to be sort of surfing the same wave, if you like. So I'm just wondering what your thoughts are about those two languages, and why has Adobe chosen Rust, say, over Go?
So I think Go is a fantastic language, right? But it's not exactly in the same space as C++. I consider Go as almost like a Python, but with types and higher performance. And it's really great for those uses, and we use Go internally all the time. It just isn't like, it doesn't have as high performance as like the C++ or Rust, or like the scalability kind of features that those languages have. So I wouldn't think there would be like a Go, like a product like Photoshop written in Go. So it's just like different use cases. With Zig is not memory safe. So that's just like, it's a non-starter for us at this point. Yeah.
When adopting new technology like this, a lot of the time the pushback from more experienced people or people higher up in management is that, oh, but we just are worried about the unknown unknowns. We're not sure, what things might be around the corner and might bite us later. Now, I've been using Rust for a number of years, so I know not to worry about this nearly as much. But how would you recommend sort of addressing these concerns and fears that folks have that are preventing having nice things?
Like worries that like, oh, we can adopt it and then find out later that there was some big issue and now everything goes to crap? Yeah. I think that the best thing that you can do with that is just point to the evidence of other people having success in this area, right? It's like, boy, I mean, if we went and we tried to adopt Rust and we had a really big issue, that would be extremely rare, because that's not what people are reporting. So that's probably your best bet to address that concern.
You've talked about like big teams and how you scale up there. Do you have any advice for smaller teams where you can't just you don't have a build system team? You're just using CMake and Cargo and corrosion and things like that to interop. Like I have success building tooling because I can do that. I have autonomy to do that myself. But if I have to get another person on board, it might be like a third of my organization has to get up to speed on Rust.
So you're talking about in the context of like, okay, you're a small team, not part of a big organization, and you want to like introduce Rust into that team. Like, what advice is there? Well, when you work at that really micro level, I think beer is a really good component. Look, let me come here. Let's talk about this. Just work the social thing, and it could be easier or it could be more difficult. At that scale, it's really hard to do things. But I think generally the things that are convincing for scale are usually also convincing in the smaller thing, right? If you're working on a piece of software, just ask the question like, how long is this software going to be living for, right? Do we expect this software to still be in use in 10 years? Or do we expect it to be kind of thrown away in 2 years? If it's thrown away in 2 years and you really don't see a lot of benefits for the memory safety, and everybody knows C++, then maybe it's best to use C++. But it really depends on the situation. It's kind of contextual.
Last question up the top.
Hi. How decisive was the publication of these sort of NSA and government documents in terms of Adobe's adoption of Rust? The narrative you presented was kind of, we weren't going to use Rust, but then these things were published and we reconsidered it. Was that a way that you and the engineering team who wanted to use Rust kind of pitched it to the executive, or was it the executive who saw this and then said, we need to address this? And as a related question, do you think that Adobe would have adopted Rust in recent years or now if those documents hadn't been published?
It's really hard to say with hypotheticals. But I will say that these documents being created led to us definitely having to look into this again, right? And see, like, is there really a danger here? And where we landed at Adobe, like, there were two possible ways we could have landed. One could have been, look, we need to do this in order to avoid legislation which is going to affect our bottom line. But we found that at Adobe that that's actually not very inspiring. The thing that we really care about is our user safety. So the regulation, whether it's there or not, like that's up to governments. Despite whether or not there's regulation, we want our users to have the best and most safe code that they possibly can. And that's really where our push is. So even if none of this, legislation pans out and there's actually no danger, like we still care about our, customers. It's like a legit concern. So I think we would continue on the same direction either way. All right, I think that's the last question, so.
Do we have any super quick last burning questions? No? Okay, let's give a warm thank you to David. Thank you. Okay. Our next talk is Panic at the Disco by Jonas Kruckenberg. Jonas is passionate about software for good, open source, and cybersecurity. He previously helped make application development more accessible at Toadie. Now he's developing K23, a next generation operating system. Outside of technology, he sings in classical ensembles and enjoys hiking. Okay, bye. So let's give a warm welcome to Jonas. So now's the time to do all your shuffling. We might do some interpretive dance at the front here. There is water outside here as well if you're feeling a bit thirsty and want to get a quick drink. There is bathrooms out here too. You ready to go? That should be your mic. All good? All right, we're ready to go. E te whānau, let's crack into it.
All right, good morning. Good morning. How are we feeling? Good? Good? Yes, yes. Come on. Yes. All right. All right. Also, welcome internet friends up there. I can't really see you too bright, but welcome. If you, well, yeah, let's do it. Let's do a quick raise of hand. Who has used C++ before? Yeah. All right. Cool. Who has used Rust before? Hey. Who's excited about Rust? Hey. All right. Great. Cool. If you have used Rust before, you will have seen this, right? The humble panic macro, or you might have seen one of the cousins, the unreachable, unimplemented, or to-do. Or you may have even seen one of those, the extended family of assertions, right? Or, as we've seen previously, unwrap, expect. All of those do different things, of course, right? But the one thing they have in common and they share is that they will, under some circumstances, print a nice, helpful backtrace, right? And then cause your program to exit. And usually, that works, right? That's cool. But that should make you suspicious, right? Because if you learn to program, then it's always like, hey, it prints a nice magical backtrace, and then it's done, right? And magic really is the word that should make you suspicious. What should make you even more suspicious is this. Have you seen this? Have you used it? Sometimes, yeah, cool. Catch and wait, what it allows you to do, similar to C++, it lets you catch a panic and turn that into a result that you can then just use as a thing. And that should make you really suspicious, because how can I turn a crash into something I can just use as a value, right? That's kind of weird. To me, that's really weird. And so, have you ever wondered how, right? How exactly does this work? How exactly is it printing a backtrace? Like, how, right? Well, let's read the documentation, right? This is from the Rust by Example book. Highly recommend. The panic macro can be used to generate a panic and start unwinding its stack. While unwinding, the runtime will take care of freeing all the resources owned by the thread by calling the destructor of all its objects. Cool. Question answered, right? Bye. No, of course not. This doesn't answer anything, right? Because, like, first of all, start unwinding its stack. What? You know? And then, like, freeing all the resources, calling the destructors, you know, still, like, how? How does it do that, right? How does this work? And this is exactly what we're going to be doing, right? Roughly, the next 30 minutes are going to be two parts. Part 1, stack unwinding. Part 2, destructors. It's going to be fun, I promise. Let's go. The stack, right? Probably the most used data structure in existence. Consists of a bunch of stack frames growing downwards, right? That's sort of important to remember for the next couple slides. The stack always grows down. There's an arrow for that if you get confused at any point. And stack frames is what a function uses for its data, right? And just to understand exactly how that works, I've brought you an example function. It's really exciting. Yeah, it just takes in a number, multiplies it by itself, gives you the number back. Now, don't be scared. Don't freak out. Don't leave. We'll read some assembly. Don't panic. This is risk 5. I find it easier to read than any other assembly, and it's also less insane than x86, so this is what we will be using. And usually when you read the assembly sort of output of a function, the only instruction you really care about for a simple function like that is this one, right? The multiply takes in the argument, multiplies it by itself, stores it back in A0, right? Input, input, output. That's our square function, right? Done. This is not what we care about today. Today we care about all of this, right? Because all of this, what this is the prologue of your function that's responsible for setting up that stack frame, right? And then the epilogue, which is responsible for the cleanup. So let's see that in action, right? Let's see how that works. So first instruction of our function, right? Adding -32 to the stack pointer. What they will do is take our stack pointer, move it down, make space for a stack frame, right? Then we store the return address into our stack frame, right? Then we take our frame pointer, we store it into that stack frame. Lastly, we set up our new frame pointer to point at the start of that stack frame, right? Pretty simple. Now we're set up, we can run actual useful code, which is, the multiply. Now, when we're done with the function, we load back our return address, we load back our frame pointer, and we free the stack frame again, right? And then we jump to the return address, and we're done. Boom. You just read assembly. Congrats. What you will notice, and that is really important, is that this previous stack pointer field, right, that link sort of points always to the top of the previous stack frame. And does that look familiar to you? What data structure is that? Yes, this is a linked list. Nice. So basically the stack is just one big linked list of stack frames, right? And so if we want to walk our stack, right, to do the unwinding, we start at sort of the bottom frame and then we walk the stack. Boom, linked list. Cool, nice. Problem solved, right? Except for that's not actually how computers work anymore, sadly. Because at some point, we figured out that having this previous frame pointer in our stack frames is like a waste of space and waste of instructions, of cycles, right? So most modern ABIs just omit that. You see the problem? There's no linked list anymore. Da-dum. Too bad. So we can't actually walk it, right? Because we don't know where our previous stack frame actually is. And usually, if you're the compiler, that's fine, because you have generated the code, you know the stack frame. But as a debugger, or as the sort of unwinding mechanism, as the runtime, we actually don't know that. So this is a big problem to us. How do we get back to the frame pointers, right? All right, let me introduce you a section in your executable, right? If you've ever used object dump, right, that is sort of a dump of all your ELF executable sections. And towards the end, you will see one that's called EH frame. And that's the one we care about today. EH frame is basically one big table of sort of structs. It's more complicated than a single struct, but structs called FDE, frame descriptor entry, right? And what that basically does is for a range of your executable, it describes how to recover the stack frame, right? And it does that by defining a whole bunch of opcodes. You can see one that essentially says, hey, the new value of register X is at register X plus 2. Or you can see one that's the second one from the top, right? That's the new value of your CFA. That is at this specified register, RCX plus 16, right? So there's a whole bunch of opcodes like that that sort of let you recover the state of your stack frame and then sort of, be on your way. One more kind of fun fact is that these look harmless. You can also embed dwarf expressions, which, if you're unfamiliar, dwarf expressions is sort of an instruction set format for a sort of stack-based Turing-complete virtual machine in your debugging information. So your debugging information is Turing-complete, and you can actually run programs in it, which is great. But using this information, we can essentially define a function, right? I named it EH frame lookup, that you give a stack frame to with all its information, and it will basically point you to the next stack frame, right? Oh, so too quick, sorry. So, that was loud, sorry. So using this function, basically we can walk the stack again, right? Instead of, traversing the linked list directly, we do it indirectly through this EH frame lookup function, which will jump to our sort of ELF EH frame section, look up the new stack frame address, and we're good. Cool. This might be and I'm throwing this out there, love to be proven wrong, the most overbuilt, over-engineered linked list in existence. It's a Turing-complete linked list, which is great. All right, part 2. How do we now that we can actually walk the stack, how do we find and call the destructors, right? The drop implementations. For that, I will introduce you to yet one more cool niche thing that's in your code, which is the personality routine. And that is a defined function with a very specific signature. You can see the signature on the slide. The signature itself is not really all that important. If you ever wanted to do this yourself, now you have it. That's not really the point. What it does, and I will show you in more detail in a minute, is it lets us we give it a frame, and it tells us what to do, right? And conveniently, for every stack frame that we walk, the EH frame info also tells us where this function is located, right? Very convenient. We just get an address, we know where it is, we can call it. So, what we do is we walk the stack, right? And we pass in our stack frame to that personality routine, and it gives us a sort of return code that instructs us what to do. Either like continue or abort or do whatever. Now, that personality routine itself is also not magic, right? If you can, if you have a minute and come to me after the talk, I can show you the exact implementation in the Rust standard library. It's not magic, it looks ugly, but it's there. And the way that this function figures out where your destructors are is using something that is called language-specific data. And this is sort of specific to LLVM. Unwinding and this whole thing I showed you earlier with the dwarf expressions that language, very much language agnostic. The language-specific data is sort of something that LLVM uses. GCC might too, but if you do your own thing, you can definitely do your own thing. In essence, language-specific data is one big sorted table of call site structs. And I will show you in a minute what that looks like. Also provided conveniently, very nice, they thought about it, by the EH frame, right? Every frame also points to this special region in your executable. Now, a call site looks like this, simplified, right? It gives you an offset into your executable where that call site struct applies, and then a length for how far in your binary that actually applies, right? And then it gives you a landing pad type and the address of a landing pad. Now, landing pads are just functions that your compiler generates for you. You never see them, you can never use them. You can see them if you disassemble your binary, but essentially a landing pad is just generated code. And there are two types of it, right? A catch and a cleanup. The easier one is the catch landing pad. Essentially, for every catch unwind that you use in your source code, the compiler will emit one catch landing pad. And that does exactly what you would expect it to do, right? If we see the landing pad is your function, right? So it will transfer control from the unwinding mechanism to your catch unwind. The second, sort of a bit more involved, is the cleanup landing pad. And that is for for all of the drop implementations that you have, right? All of the boxes, all of the vects, all of the strings, everything, your custom drop implementations. Those, for every scope or every stack frame, they will be aggregated into one cleanup landing pad that just calls all those methods. And that is exactly what then, in the end, finally calls your drop implementations, right? This sort of landing pad stuff. Now, putting it together, there's yet one more complication, but I promise it's the last one. Unwinding actually takes place in two phases, right? So we walk the stack twice. There's no real reason to that, aside from that's just how it's defined. The first phase is we search for a catch pad, right? So we walk up the stack and we try to find a catch pad. The second phase is called the cleanup phase, and that's where we actually call all the destructors. And so what we do, right, back to our stack and our personality routine, we walk the stack, we pass in the stack frame. The personality routine tells us, hey, please continue unwind. So we do, right? Pass in the next stack frame, and our personality routine tells us, handler found. And handler found means we found a catch unwind, please stop, right? This is where this panic will stop, essentially. So we go on to phase 2, right? Cleanup. We pass in the stack frame again, and the personality routine tells us install context. And install context just means, hey, here's this landing pad, please call it, right? We done that, we pass the next stack frame, and it tells us handler found, as happened in the first phase. And that means we reach the catch handler, we're done, right? We transfer control to that catch handler, and boom, unwinding complete. What I want you to take away from this, and I see a bunch of very confused faces, is you don't need to be an expert in this, right? There are probably 5 people in the world that are experts in this, and they get paid a lot, so you don't have to know this, right? But what I want you to know is this is not magic, right? This is very much not magic. And especially in a language like Rust, where a lot of this stuff is explicit, I want you to take away that if someone says this just works magically, that is suspicious. Don't trust them. Dig deeper, right? Because nothing is magic. This is not magic. Panics are not magic. Don't be afraid, right? Don't be afraid to dig deeper. Do it. You will find cursed stuff, but you might be able to do a talk about it, right? So that's it. Thanks. This is me. This is where you can find me. And we have plenty of time for questions. So ask away.
Yeah, there's another mic around the corner. So we'll have one here, and then I think there was one over there. Yeah.
So you mentioned that you can put programs in your dwarf.
Yes.
What is the coolest thing you've ever seen stuck in one of those programs?
So the fun thing is they defined it. No one ever uses it. But yeah, this is a challenge. So if you do something really cursed with this, let me know, right? But the kind of funny thing about dwarf expressions is that it's really complicated, and it takes up a whole sort of section of this really long standard. And they sort of defined it in the expectation that for a really optimized code, we might need this. And then turns out it's really complicated, and actually no compiler really wants to implement it, at least to my knowledge. Yeah.
Okay, we've got another question on mic 4. Can we turn that up?
Does it work now? Yeah.
Yeah. Sweet.
Thank you. It was very interesting. I will come from the past on this, and would like to learn a bit from you now. 10 years ago, when I was involved in the performance profiling development stack sampling for Intel, I remember our lib unwinding expert, maybe one of those 5 you mentioned in the world,
Probably.
actually mentioned that there is a lot of magic there, because I remember that there was actually no clear specification on how to unwind, and the reason for searching was exactly that. They tried to apply heuristics to find out the exact frame boundaries. And I don't know if LLVM changed that.
Yes.
And also, I remember the complexity of just-in-time compiled injections, like transitions from GVM or some C# runtimes, caused complexity there. And basically, the lesson I learned from there: never trust panics, never panic. It's dangerous, and the code running in the context of after the signal to the application that it's got the panic mode, the drop functions should be as minimal as possible. So, I mean, what changed in the last 10 years that it's not valid anymore?
Nothing. It's exactly like this. except for, so with this whole stack walking thing, right? That is sort of the foundation of unwinding, and there's a number of ways you can do it, right? Like the thing I mentioned at the very beginning of just like walking the linked list, if you force frame pointers, that's the easiest, right? And there's a good case like some Linux distributions actually switch their sort of precompiled modules from not having frame pointers to always having frame pointers, because it turns out like modern computers are fast enough and we don't actually need to do all this. And then it's really easy, right? Second more complex thing is like you don't have stack pointers, frame pointers, sorry, and you need to do all this like, dwarf EH frame like bullshittery. If you don't even have that, you can still do stack unwinding. And the way what that is called stack scanning. And that is you look at the memory and you look through all the bytes and you find something that vaguely looks like a return address.
Yeah, exactly.
And that's your return address. And that, with obvious downsides. I don't know if lib unwind from LLVM actually does that, though. I don't think it does. It shouldn't, at least. But you could if you wanted to, for sure. And there is like precedent of doing that. The other thing you mentioned, that it's not really defined, very funny. It is actually not really defined. The specification for EH frame says it's sort of an old archive document from the Linux Foundation, somewhere kernel.org/whatever, really deep down, plain text. And it has a sort of a disclaimer at the top that says, this looks a lot like Dwarf's debug frame format, but it's not. I'm not going to tell you what the difference is. Figure that out yourself. And that's sort of about it. Also very funny, who knows what Itanium is?
Yeah.
Yeah, all right. So Itanium, the failed sort of 64-bit processor architecture that Intel tried to do in like the early 2000s, late 90s. That is where all this comes from, right? The unwinding, like the de facto specification for all things unwinding is the C++ Itanium specification, right? Bad things happened. So like all of this is very much sort of like folk knowledge and like, but you would be surprised. A lot of the compiler things are just like do whatever GCC does, and that's like the standard. And it's definitely the case here as well. Yeah.
Thank you for this. As far as I remember, Intel supports some of the unspecified features for the try catch in C++ to actually work.
Okay.
That's what I was told. I don't know.
Yeah, that could be the case. Yeah.
Yeah.
There's some for sure.
Yeah. I don't remember it, but I grew up with the saying, magic is simply science we don't understand yet, and that very much feels like the case when I'm listening to this talk. Yeah. I wonder if you sort of learned a lot of this when you were working on the K23 OS that's mentioned up there, and I have actually seen that talk.
Yeah.
And
cool.
I was wondering if I could go a little off topic and ask, what do you think is the application for a like WASM complete operating system? Because I don't know.
Right. So for context, the reason why I've been doing all this is it's a project called K23. It's a sort of WASM runtime on bare metal. That's kind of the idea. And turns out that, panic abort, right, which is the other option of like just crashing without a backtrace. It's really inconvenient for development, right? Actually having backtraces is kind of nice. And so all of this work, writing a custom unwinder, digging through all of this is sort of what I did to make that project work, right? To your question, the reason why I think it's interesting as sort of an experimental approach to operating systems is that first, I don't want to sort of, I don't want to deal with the sandboxing issues that, existing operating systems have. I don't really want to deal with like, hey, is this compiled for x86 or for Arch64? Did I download the wrong binary? What is this? I don't want my mom or my grandma dealing with that. But then also, one thing that sort of came up really early, and that what makes me most excited about it as a technical sort of project, is that when you integrate the usually, right, you have your compiler, that targets an operating system, right? But turns out when you take the compiler and sort of make that the operating system itself, that shifts a lot of the sort of trade-offs and a lot of the things you can do, right? So that, for example, comes very handy when you want to do sort of security prevention and defense in depth. ASLR is much easier, like randomizing the layout of your executable. That just comes naturally when you're a JIT compiler. You can also do cool things like, dynamically using CPU features when they're available or when they're not. Sort of, jumping to like polyfills and software implementation and stuff like that. And so it's just like it's a really interesting field to see where you can take things, right? Where like the operating system has been sort of a really well-defined, well-established thing for the last 40 years. But I think we can do more, do cool things, change that. All right. I think we have time for one more.
One more question? Speak now or forever hold your peace.
Or later.
Or in the collaboration space.
So you talked a lot about how the current systems work and that they were defined in the early 2000s for unwinding. I just wanted to ask, is there people working on improving this standard? Is there a better way?
No.
Is there hope in the future?
So for context, I've cut the slides for time, but my unwinder is about 10x smaller than libunwind, right? It is 1,200 lines of code, which is not a lot. Unwinding actually isn't as complicated as you might think. The reason why all of those existing implementations are so massive and so complex and so horrific and so untrustworthy is that they have to basically cater to every language in existence, right? Like libunwind has to be so generic as to be, to work across C++, Rust, and basically every other language, which also means it has to be really, really generic, which limits the optimizations you can do. And it also can never change ever, right? Because every language in existence that does any kind of like panicking or exception handling or whatever depends on this and the way that it's specified. So I don't know anyone that works on this, and I expect it to it would be really hard to do. But it would be great to see. Like definitely, it's not there's a lot of improvement potential for sure. Yeah. All right. 40 seconds on the clock. I think we made it. Break.
Cool.
Thank you.
Massive thank you to Jonas. Cool. All right, I now stand between you and Kai. So let's get this out the way quickly. Kai, or what we call food. All of our Kai is actually vegetarian or vegan. But if you gave us specific dietary needs, your Kai will be named. Okay, te pai? We have 30 minutes to break. You may see some signs that refer to wharipaku. So a wharipaku is a toilet in te reo Māori. And our toilets are on either side of the main hallway. So please use whichever toilet you feel comfortable in. I am going to say, though, that for the women here, we're going to have great time in the toilets. There will be no lines whatsoever. We can pretty much have 4 toilets each. If you are looking for water, it's in the black units outside here. So next to them will be the plastic cups. So please reuse where possible. We don't want to destroy our lands out here. We're now going to break. And I've actually... Do I get extra money if we're super on time? That's all right. I'll ask in my negotiations later. We're now going to go to a break, but we'll be back here, ready to go at 11:15. So plenty of time to get your coffee, plenty of time to go to the break. Go check out the collaboration spaces, and we'll see you back here at 11:15. Cool?
So,
Yeah,
how
for
about?
sure.
I'll go on this side.
Come down. And do you have your presentation on your own device
Yeah, I do
too?
it as well.
Sweet. I'll just try to do interpretive dance while you
Yeah.
guys hopefully it works really well. So just, you got the handheld mic here if you want it, so you guys are number 2.
Yep.
And you just turn it on and off here. These are the easy ones.
Mhm.
Whereas the runner ones are very hard to turn on. And
Yeah.
off.
Cool. So you can just like turn it off and put it down and everything. That's fine.
Yeah, do you guys have timers on your ones?
I do not have a timer on mine.
Oh, yeah, cool. So my understanding is that they come down here. I'm not sure they got the timer running, but if it doesn't come up, I'll probably just hold up a 10, 5-minute,
cool.
2-minute. Yeah.
Nice.
And that will be the time to the end of your presentation. So, like if you want questions, it's probably better to have a more 10, 5.
Yeah.
These
are our 2 speakers for the next slot.
Hello.
Hello.
Are you both on stage at the same time?
No.
Oh.
Yeah, I'm first.
So, English is hard.
It is, eh?
Are you presenting? That's PowerPoint or keynote?
I am presenting
And then Tom also has his as well.
Yeah.
So I was just talking about, here's the handheld for them,
Yeah.
so they'll be number 2. You won't want the lectern at all? And is the timer going?
Yeah, it was in the last one.
Oh yeah, cool.
I don't think it ran to the first one, just because we were dealing with
Yeah.
a few little hiccups.
As there always are.
What's a tech conference? Where else you technical?
Yeah,
issues, right?
exactly.
It's always the way.
Yeah, let's check it out. Oh, no. What are you presenting at?
There's a web page. It's written in March, I guess. This is
Nerds love it.
Yeah.
Are you MacBook Pro too, or are you?
I'm a MacBook as well. No, just USB-C.
No, so you're right, yeah.
Yeah, sorry. Yeah. And no audio. It'd be bad if some Slack notifications came through while I was presenting. Yeah.
A bunch of my colleagues have got annoyed with me playing Baby Shark. It's like my test song. And then when I run PowerPoint checks, I just run my phone, plug into USB-C now, and just run Baby Shark with words.
Yeah.
And so I set my ringtone to be start off with the normal Apple ringtone, and then it goes into the Baby Shark version of the ringtone. Yeah, that will be a time. So should I grab a mic for the start of the next session, or for running the questions?
Yeah, so they're just behind there. So maybe at the end of their talk. Yeah, because it might be they go over time and then we have to. Yeah, just a little on top of a box type thing. So just to check, Anders as well. Is it Anders Rasmussen? Is that? Okay. Anders.
Yeah.
I know. Oh, yeah, cool. Anders.
Anders is fine because that's what I usually introduce myself as.
Anders Rasmussen.
I have had issues with people trying to spell my name if I say it any other way.
Oh, yep, yeah. Where does it come from?
Danish.
Danish.
Scandinavian.
Yeah. Oh, cool.
So yeah.
Yeah, my sister-in-law is from the Netherlands, and so while her name looks like Eileen, I can't even say it properly, and I struggle so much because I'm like, you're doing so well with Te Reo, and I feel like I should be able to do this.
Yeah. And then my last name in Danish is Rasmussen, which
Rasmussen.
is
Kapai, okay. And then Anders, is that it?
Yeah, Anders or Anders. The accent doesn't really matter.
Okay. So I saw the little pronunciation in your bio, which I was like, sweet, love this. And I'm assuming it's Tom Simpson.
Yeah, that's very white.
Yeah, okay, cool. Yeah. Just making you feel like you're welcome
it's
here.
All good.
Yeah.
It's all good.
Cool. Okay. So I stole your profile from LinkedIn and just reworded it because I don't want to call you out, but you didn't provide one. So
Shit. Oops.
I was like, who am I going to introduce?
Doesn't exist. Yeah.
That's what. That's all good.
Oh, sorry.
That's what the internet's for.
Yeah, exactly. Sorry about that.
That's all right.
Easy. You will be stalked.
Yeah. Anders.
So you up first?
I'm up first, yeah.
Perfect. I like it when it's that easy.
We should do that all the time, like get the second person to test first and then the next speaker, because then we can just leave it set up.
Can we mute the beacon?
There is lots of space down the other side as well if you want to spread out a bit more. Are you all good?
So for the first one, you'll be speaking.
Oh, so we're not having Rob anymore? All right. As we come back, I want to just remind everyone about the Code of Conduct as an active part of this conference. If you need to report anything, we have online reporting tool, or you can talk to anyone with a green lanyard, preferably not me, but someone else with a green lanyard, because I'm busy at the moment. But details are on the back of your lanyards too. It's not that I don't care, I do care. But next we do want to give a massive ngā mihi or thanks to our sponsor IDverse for helping us to make this event possible. Your support is deeply appreciated and means we can bring this international talent to Aotearoa, as well as showcasing Aotearoa to the world. So we are going to welcome Matt from IDverse to come kōrero and share with us some of his thoughts. Big warm welcome.
Well, good morning. So my name is Matt Adams. I'm the CTO at LexisNexis for our IDverse product and the co-founder of IDverse as well. So about 6 years ago, we decided to endeavor to create our whole back-end and front-end in Rust. I was not met with what I thought I would be met with in terms of reception. I had a lot of people come up to me and say, why would you do that for? it's kind of career-ending stuff, creating a whole massive system and recreate it in Rust. Fast forward a few years later, we completely re-engineered our whole system. It's a neural network that's about 10 billion parameters. It's a computer vision system as well. And what it does is it helps prevent ID fraud. Every day, in fact, over the last couple of years, there's been 100 million IDs that have been stolen and leaked online. And we set out to basically stop that and prevent that, to protect people and socially awareness around this, as well as for individuals to be the owners of their identity. So we've created a suite of products for ID verification as well as authentication. And we've got a team in Sydney, Australia, and around the world. And we are basically out to keep plugging this network and making it better and better. And we're actually hiring here today as well. So if you're really interested in joining a team of pure Rust engineers, computer vision experts, and neural network experts, do come and see us at our booth. And yeah, we've met many people here today that have been quite amazing. So yeah, if you would like to join and be part of this amazing work that we're doing, do come and see us. So that's pretty much it. I'll leave it at that. Thank you very much.
All right, for those of you who wanted to make Rust a job, a Nate, there you go. Not that I'm poaching on behalf of anyone, but your employers might get a bit upset. So, our next talk is Designing Superconducting Magnets for Fusion Power by Tom Simpson, who I was referred, when I asked him if that was how he said his name, he goes, yes, it's a very British boring name. But Tom, nothing boring about that. Tom is an R&D engineer with a background in physics. His passion is in applying cutting-edge physics and engineering techniques to design things that make the world a better place. He specialises in working on projects with low technology readiness levels, where there is an abundance of juicy technical problems and a decent helping of creativity is actually needed to progress. So far in his career, he has been heavily involved in the field of high-temperature superconductivity, notably working with a team to design a world-first superconducting diode. So let's give Tom a warm welcome to the stage. I have warned the speakers that if they don't get their tech checked beforehand, they have to do an interpretive dance. So that sort of scared them into making sure their tech all works. Ka pai.
Cool. Yeah, so welcome to my talk. I want to start off with a little bit of a confession. I was asked to do a presentation here at this conference, at a Rust conference, and decided to bring a presentation basically about designing magnets instead. So there is a reason for that though. We do actually use Rust at Openstar, and it is one of the things that has allowed us to develop our magnet so quickly. But to understand why, it takes a little bit of context. So this is the presentation that gives you that context. So essentially I'd like to start off by just talking about what fusion is, for people who aren't aware, go into why it's hard, the different ways that people are trying to do it, what we're doing at Openstar, and then finally the tool that we developed to optimize our magnets. So, fusion is the energy source of the sun. It is the process of combining smaller, lighter nuclei into heavier nuclei, and in the process, releasing a lot of energy. And the sun is actually the root power source of pretty much everything we do here on Earth. So even things like wind power is produced from the sun heating up the Earth's air and then moving it around. Fossil fuels are also technically solar power as well, because the energy had to come from somewhere in the first place. The only thing that isn't is fission power. But the reason why we're interested in fusion power is because the energy density of the fuel, so the hydrogen that you initially start with, is about 10 times greater than fission, which is itself about 100 times greater than traditional energy methods. So we're really interested in essentially trying to harness the power of the sun here on Earth. So we start off by looking at what does the sun actually do. The sun goes through a reaction called the proton-proton chain. So essentially starting off with about 6 hydrogens, combine them together over various stages, and releasing a helium at the end, releasing some energy. This all takes place in the core of the sun. So the solar core has a temperature of about 17 million degrees and a density of about 160 tons per meter cubed. And then produces an amount of energy, or amount of power that's so large, it's not really worth comparing it to anything. The number is so big. However, if you were to look at the density of that power generation, so the watts per meter cubed, that number is only 27 watts per meter cubed. And for the avid gardeners amongst the audience, that's less than a pile of compost. So just the process of turning or decomposing your pile of dung into something else is actually more power dense than the core of the sun. So if you actually wanted to bring this down to Earth and create a fusion power plant, say 500 megawatts, which is the industry standard, you'll need a sphere the height of the Eiffel Tower, which also still has to be 17 million degrees at the same density, and because of that, would weigh about 3 billion tons. So we can't do this. We need to think a little bit more creatively about how we bring fusion down onto Earth. So the core of the sun is actually a very bad fusion reactor. The reaction it uses is very unlikely to happen, so this is a plot of some of the more common fusion fuels. I've missed one here, but it all follows the same trend. So the proton-proton chain, the initial reaction, is very unlikely. If you were to try and do it on Earth, you would pretty much die of old age before you collect enough data to figure out how likely it is. Also, the core of the sun is actually pretty cold, if you think on the scale of what's going on here. So what we need to do is move to higher temperatures and choose a different fuel. The fuel that we choose for initial pilot fusion plants is the mixture of deuterium and tritium, which are both heavier isotopes of hydrogen. Deuterium is a hydrogen with an extra neutron, and tritium is a hydrogen with 2 extra neutrons. You combine them, and you create a helium atom and a neutron with very high energy. So I've got the units in mega electron volts here, which doesn't really mean a lot to you, but just mean that that number is big. And I just want you all to remember this fact that the neutrons are nasty, and we'll get back to this later though. In order to actually get a stable fusion reactor, we can't let the hot gas at 170 million degrees Celsius, in the case of actually creating a reasonable fusion reaction using DT, hit anything. If it hits anything, 1, the thing would immediately melt, and then 2, the plasma would cool down and no longer have any fusion. So we're going to leverage the fact that at these high temperatures, you've added so much energy to the system that you've ripped electrons off from the atoms in your gas, making it electrically charged, which means that if you pass it through a magnetic field, it will begin to curve. The magnetic field will create forces on the particle, causing it to rotate and sort of orbit around the magnetic field. If you then place this in, say, a curved magnetic field environment, such as like the field around a bar magnet, these particles will then follow the curvature of the field. Which means that if you set up a scenario where you have these field lines that close on themselves instead of hitting any kind of your device or anything like a wall somewhere, these particles will theoretically never leave the magnetic field. So you can confine the plasma at the high temperatures without it touching your walls and cooling down and causing damage. This has been the main focus for a lot of fusion research. So there are 2 major magnetic confinement schemes, the tokamak and the stellarator, which essentially both are pretty similar, slightly different ways of doing it, creating very large, strong superconducting magnets that wrap around a plasma that create field lines that sort of orbit around and close on themselves, which then confine the plasma and allow you to have fusion and these really hot gases. The stellarator is a very similar thing, but it's a lot more complicated for reasons I'll get to in a second. But there's also a third kind called inertial confinement, which I wanted to touch on briefly because there's one of the things that's been in the news recently, where instead of having your gas be around for a very long time and keeping it off your walls, you heat up your fuel so quickly that it doesn't have a chance to hit your walls before it's finished fusing. And they do this by firing giant lasers at it. You might have heard recently, or I think it was like last few years, that the National Ignition Facility in the States were the first group to produce more power out of their fusion reaction than they did putting directly into it, which is a big milestone. But as it turns out, all of these devices are about the same distance away from actually achieving commercial fusion. The reason for that being inertial confinement is actually not very efficient, so the actual goal of how much energy they need to produce is a lot higher than other fusion schemes. Stellarators are insanely complex. Like if you look at the coils on the slide here, they are really wiggly and wobbly, and that's part of how they keep the plasma stable, which means they need to be massive in order to actually get a reasonable amount of reasonable cost of electricity. And then tokamaks are probably the most well-researched out of all the fusion schemes. However, they have this nasty tendency that if you were to run the plasma, they are not very stable. So this is a video of a disruption in tokamak. So sort of the plasma turns on, and when it turns off, you see all these sparks coming around. So this was an uncontrolled turn-off where the plasma slammed into the walls of the vacuum chamber, and those sparks are bits of molybdenum and tungsten that have been melted off the side of the chamber and flying around inside the chamber. So if that happens in an actual fusion power plant, you need to go in there, repair the walls, and then come back later, because if you don't have those first wall surfaces, you end up melting a bunch of other stuff, and it's not good. This can take, in a tokamak, months to just disassemble the thing, and then you need to go into this kind of radioactive environment, make the repair, and assemble everything back together. So it's actually, there are reasons to suspect that tokamaks might not be economically viable in the long run. So this has sort of made us try to go for a look to nature to see, like, how does nature confine a plasma? And one of the clues that we see, not in everyday life, but like here on Earth, is the aurora. So the aurora are caused by charged particles hitting the planet, which means that there must be a plasma somewhere confined in the Earth's magnetosphere. And this is something that actually is common to all magnetospheres, where if you were to look at them, you'll see a large area of charged particles, which are bouncing between the poles. So when I said before that the particles are orbiting around the magnetic field lines, as they get towards the poles, the magnetic field increases, which causes the particles to bounce back and forth. This is a reasonably stable situation. There's also a bunch of turbulence that I won't get into that keeps it all nice and high pressure, or high-ish pressure. However, there is a limit to what you can do with this scheme. If, say, you have some external energy source, such as solar wind, these add high-energy particles and also heat up the particles in the Earth's magnetosphere. So they get more energy, they get really hot, they move really fast, and then they go through that mirroring area and hit the poles of the Earth, which is how you get the northern lights. So instead, what we can do is just create an electromagnet, which already has a hole in the middle. And what this does is set up a lot of closed field lines, and these field lines, as I said before, allow the plasma to get really hot without touching anything. And so this is essentially what we've done at Openstar. Our device is called the levitated dipole. It is a dipole magnet, which is the name for the shape of field that we're generating, which is levitated inside of a large vacuum chamber to replicate the physics of planetary magnetospheres. Our current device is essentially a technology demo. The chamber is about 5.2 meters in diameter. It's reasonably large. And the magnet about 1 meter in diameter, which is going to be levitated inside. We haven't levitated it quite yet, but we have turned on plasma around this thing. The magnet itself is about 5.6 Tesla, which is about twice as strong as an MRI machine. And the first plasma that we got was just an electron plasma, so the ions and the nuclei that you need to produce fusion weren't really that hot. Once again, this is just a technology demo. It was about 300,000 Kelvin. So we built this really quickly in the scale of fusion experiments. Essentially starting from nothing, we had this experiment in 2 years, which is actually unheard of in the scheme of fusion systems. But the question then remains, how do we scale this to a full-scale fusion plant? These are not very hot plasmas. They are not, the ions aren't even that hot. And the magnetic fields are not that strong. But also, like, why do you need strong magnetic fields in the first place? The key thing is that to get the hot temperatures, you need to get to high temperatures, but then also you need high densities in order to have a high reaction rate. This means you need high pressures. And pressure, like if you have a very high pressure gas, that always wants to expand and dissipate over your space. So you need a restoring force, which is now in the form of a magnetic field, in order to retain that pressure. So the higher the pressure, the stronger the magnetic field. And it turns out, in order to get a magnetic field, a pressure's high enough for commercial fusion, you need a magnet that's about the scale of 20 Tesla, which, for reference, is strong enough. If you were to put it on an aircraft carrier and lift it, it would then lift the aircraft carrier with it. So it is no small feat, but it's sort of like the business that we're in fusion. Magnetically confined fusion is building very strong magnets. This comes with a few downsides. So if you have a strong electromagnet, you need to have a very high current, or a very large current. And these two things tend to interact, much as just a charged particle moving through a magnetic field. There is a force that's generated. And that force is in the form of a massive radial force. So this magnet that we're building is constantly wanting to explode, which is not ideal. So this is a video of a strong magnet. This is about 1,200 Tesla, so not quite. It's very much in the extreme end of things. But essentially, what's happening here is that they turn on the magnet and intentionally make it explode, because it is just like the forces are so large, they just want to get that 1200 Tesla for a small second to do some research. But this explosion was powerful enough to knock the blast doors off the room, which is kind of fun. And the purple smoke is just the arcing from the current we're going through. So we don't want to do this. We need to design a magnet that actually retains the structural forces, or essentially a structure that retains the hoop forces that we are generating in the magnet. Another aspect as well that we need to take into account when we're designing our magnets is the fact that this thing is levitating and therefore is completely disconnected from the rest of the world, which means that we need to have a bunch of electronics and control on board the magnet to service a bunch of things. And electronics don't like strong magnetic fields. So how do we sort of close that loop? Essentially here at Openstar, we've come up with a way of essentially designing the cross-section of the magnet, which you can see here on the slide, such that there is a region in the middle that is, the contour follows the magnetic field lines and is essentially self-shielding. So we have this region of very low field inside the magnet that's been set up as an optimization problem to then create this area that we can put all of our electronics and all of our power supplies and all that kind of thing for the magnet. This is a photo of our current device Junior, which, without any context, sorry for that, is a little bit confusing. Essentially, the coils are on the left-hand side of the slide, and then there are essentially a space in the middle with all the electronics, which people are filling around with there, and there's some more coils on the outside, and then there's coils that go on top to sort of seal everything together and create this magnetic shield area. And this has allowed us to essentially just put all of our control, our sensing, everything on board the magnet and not have to worry about magnetic field too much. And then finally, this is the thing about neutrons I mentioned earlier. DT reactions produce very high energy neutrons. And if you're not aware, neutrons are like the final boss of radiation. So a lot of things tend to come in and just bounce off and change the chemistry a little bit. It's not super bad. Neutrons don't have electric charge. So they don't bounce off things. They sort of interact directly with the nucleus. And in so doing, they have a variety of interactions. So the most common one, and probably the thing we don't have to think about the most, is the scattering event, where essentially you can think of like a billiard ball. It's bouncing off another billiard ball. That's fine. It just transfers heat. But the really interesting and annoying things is when the neutron comes in and interacts directly with the nucleus and it gets absorbed into the nucleus. And in so doing, it can fundamentally change the element that the nucleus is, making it radioactive, doing a bunch of really nasty things that we don't want to do. But this is also, since it directs, like as it's just a side tangent, this is a paper that was released recently by a company called Marathon Fusion, where essentially they are proposing the use of neutrons to perform alchemy. So chrysopia is the process of artificially creating gold. And this is not a massively crackpot idea. This is real science. The neutron comes in, interacts with the isotope of mercury, transforms it into a stable isotope of gold, while also producing more neutrons they can do more useful things in your reactor. Anyway, that's kind of fun, but we don't really want to turn our magnet into gold. We want it to produce fusion power. So we need to add some shielding. So the shielding is essentially very thick layers of tungsten and boron carbide. Essentially needs to be really thick because the neutrons tend to go through material really easily, and these materials are very good at slowing down the neutrons and then absorbing them later. The issue with this is that it then interacts with the plasma physics. So as you add more shielding, you move your plasma further away from your magnet, which means that the restoring force that keeps the plasma in place is now weaker, which means you can only sustain lower pressures, reducing your fusion power density, and in this case, making the reactor a lot larger. So we need to think about all these things together in order to design a fusion magnet. We need to make sure the plasma is dense enough that the thing is not super expensive to build because it's reasonably small. But then we need to think about the neutron shielding because of that, and that has flow-on effects to the magnet design, which then flows and flex the plasma, and it's all interconnected, and it's pretty nasty. And it's especially hard if you're trying to optimize for a specific performance target. So essentially what you need to do is solve all of these things at once. So we start off with an outer profile, optimize that zero field region on the inside, solve a plasma physics model to then figure out how much fusion power we're generating, solve a neutronics model to solve the transport of the neutrons towards the magnet, and then eventually solve a mechanical FEA problem to make sure the thing doesn't explode. This by itself isn't super useful, so we need to add an optimization step. So we use an evolutionary algorithm called differential evolution to then go through and iterate through designs of magnets to then find the optimal magnet for a specific cost function, whether that be total fusion power or minimum size for a given fusion power or something else you want to think about. And so this is where the Rust bit comes in. I'm not a software engineer, I don't know if you could tell. When I was designing this, there's so many different things you need to consider in this design that I don't want to have to go through the pain of using Python and everything being really slow. I wanted to just be able to think about the problem and then just write the code to solve the problem. I didn't want to have to be thinking about the code too much. Which you can write fast Python code if you use NumPy, but NumPy has the issue of you need to think of everything in terms of matrix operations in order for it to be fast, which just adds an extra layer of thinking on top of whatever you want to design. So I didn't want to use that, which goes towards like C and C++. But then those things, I don't like having to deal with dependencies. That was mentioned in the first talk. It's awful. I also don't want to have to think about, in this scenario, of just like having to constantly manage my memory and dealing with dangling pointers and all that kind of stuff, which will lead to weird bugs, which will stop me from learning things from the model. So this is where the Rust came into it. I decided to use Rust for this. So this is a screenshot of the program that I've written using Ratatouille. That's a very cool library. Yeah, so essentially, the reason why I use Ratatouille is so I can run it on a remote server. I wanted to have a UI so I can see what the optimizer was doing. And essentially takes in a bunch of inputs, runs through all those models I mentioned before, and then creates a magnet that's the given size, shape, and everything to optimize for either fusion power, yada, 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 all that kind of stuff. Recently, we've been optimizing to try and make the next device easier to build, which is a very complicated, weird plasma physics thing. But essentially, the reason, like Rust has allowed me to only focus on that, which has been so freeing in terms of like a software development process. I've done some scientific coding stuff before, and it's always been like, oh, how do I have to go back and change this? Oh my God, that's such a pain in the ass. But in this case, it's just been so nice to go like, okay, I can just write whatever I want, knowing that it will work pretty well initially and be fast and all this kind of stuff, which has just made the iteration process for this really fast. So essentially, this screenshot is from a version of the code that's about 2 years old now. Not 2 years old. It took 2 years to get to this point. But we got a working version of this in about 2 weeks, which we then get getting results from, and then just been constantly iterating and learning things from it, which has been like a really fun process. And eventually, we end up with a magnet. So this is one of the outputs of the code with a little extra details in terms of neutron shielding. But essentially, you end up with what the magnet looks like, how much structure we need. There's a massive block of steel there, but eventually you would machine that down to make it a little more skeletal to reduce weight. And then also the large amounts of neutron shielding, what kinds of materials you would need in that neutron shield in order to protect it and keep everything at reasonable temperatures and make it last a long period of time. So yeah, I mean, that's all I had to talk about today. I'd like to open up for questions. Thank you.
All right, so this time I now have a couple of runners that'll come forward and grab some mics, so I don't have to run up and down the sides. Is there anyone who wants to? All right, so we've got a couple, one on one side up the top and one on the other side. What numbers have you got? 3 and 5 are the mics. Let's see who can get there first. Yes.
Hello. I'm curious. So that's you've explained the physics of containing the reaction into that plasma and the magnetic fields and all that. How do you actually extract the energy out of the reaction and make it useful and send it to the grid?
Yeah, that's a great question. It's one of the most boring parts of fusion. Essentially, we're building a giant kettle. But in a little bit more detail, I don't have. Actually, wait, hang on. If I go back to the first slide, I can point to things. Sorry, give me 1 second. Cool, there we go. So essentially, I didn't mention this before, but one of the isotopes, this is a very roundabout way of getting to your question, but it will make sense in the end. One of the isotopes of hydrogen, tritium, is not available on Earth. It's only really produced right now in fission reactors, but that's not sustainable. The rate of production is very low. So we actually need to produce our own our own fuel while we're using these reactors. So we have this tritium breeding blanket, which uses compounds of lithium, and those lithium gets bombarded with neutrons and then turns into tritium. We want to maximize the number of neutrons that turn into tritium, so essentially every reaction produces 1 neutron, and we need to have more than 1 tritium being produced per neutron in order to get build-up of tritium inventory so we can build more plants and keep this thing fueled. In so doing, our breeder blanket is also the main heat extraction source of our fusion reactor. So if I remember back to their reaction, most of the energy of the reaction comes out in that neutron, which then, therefore, as it gets absorbed into the blanket, deposits all of its energy there. So we flow coolant through that, then use that to essentially, through a few steps, eventually spin steam through a turbine. And that's how you produce electricity.
Cool.
Just before our next question as well, I just want to let the live stream know that we are aware of some of the issues with the presentation and the audio. So we're just going to go try and get some team onto it. Yep.
All right, so I have two questions. The first one, you mentioned that you're generating your own tritium. I believe the moon is supposed to have a fair amount of tritium. I was curious how that compares for the economics of tritium production. And then the second thing I was curious about was how radioactive it is to be in the room with that, with the reactor.
Yeah, two very good questions. So the first one, the moon is a good source of helium-3, which is a decay product of tritium. So eventually there was tritium at some point, and now it's got helium-3. I didn't have the reaction on before, but deuterium helium-3 is the second most reactive fuel source. And it is better because it doesn't produce as many neutrons. Oh. I'll keep answering the question. So so like it would be kind of fun to build it on the moon because you already have essentially a vacuum chamber there. It's a very low vacuum there, but the amount of mass that this thing has means that it will be very expensive to get to the moon. So probably not the best economically. We'll probably be like, we'll have spaceships going around the solar system by that point. So that'll be kind of fun. Your second question about the radioactivity of the device. When it's on, it is probably going to be the most radioactive places on Earth. However, that's a little bit scary. When it's off, it's not radioactive. The fuel itself stops producing electricity, or stops producing radiation. So it doesn't have the option or the possibility of having this chain reaction that you'd see in a fission plant. However, that being said, with DT, those high energy neutrons, as I said before, can create things that are radioactive themselves. So you still don't want to go near the thing after it's turned off, but the half-lives and the actual activity of those decay products are relatively short, which means that you can leave it for a few months and then it'll probably be fine. You have to be worried. You have to be careful about material selection though, because that's not true for everything. Yeah, cool.
Do you have one over there? I have a question. The turbulent, I heard there's something called a turbulent pinch with the different pressure regions within the confined plasma. Could you explain that a little bit?
Yeah, sure. So this is part of the turbulent stuff that I didn't want to super get into in the presentation because it sort of bogs things down a little bit. But the reason why a lot of the other fusion schemes are unstable is because they experience turbulence. Dipoles are unique because they are stabilized by turbulence. It's the completely opposite way of thinking about things. So we actually want turbulence to stabilize our plasmas. The turbulent pinch is essentially like we have this profile that equalizes entropy everywhere. So essentially making it as random as possible, and that happens to be centrally peaked in terms of pressure. When you get any variation on that, they will set up convective cells, like you heat up water and it starts like convecting up and down. Similar kind of things, but transporting energy inwards and outwards in order to go back to the stable profile. So I don't know if that has helped anybody think about turbulent pinch, but it is just a turbulence phenomena that essentially transports energy back towards the center core of the plasma instead of transporting out towards the edge. Hopefully that answers your question.
Hi. Obviously, you've got the magnet in the center. It's an electromagnet, right? So it's got its own power, like batteries inside it.
Yep.
And it's levitating. Does it power the levitation, or is that provided from, I don't know, other magnets outside?
Yeah, sorry. I did forget to mention there is a second magnet. That is the magnet on top. So it's not shown in this plot specifically because we haven't designed our top levitation magnets for our fusion devices yet. But there is a second magnet that provides the levitation force. It's very weak. Essentially, because this core magnet is so strong to confine the plasma, we only need a very weak magnet at the top in order to provide the levitation force. So the actual power requirements for that are pretty low. So I get the top definitely, we have the external power supply on board that provides the levitation force. The power supply is on board the core magnet just to make sure the magnet stays charged.
Cool. So we got second to last question, and then we'll have our last question here.
G'day. Thank you for an amazing talk so far.
when you are doing the Rust side to kind of solve these numeric problems and do the differential evolution stuff you mentioned, what are you using for the linear algebra side of things? Are you mostly, you said you don't like thinking in matrices. Are you using any kind of libraries in the ecosystem to do this, or are you just kind of doing the math in there yourself?
Yeah, so that's actually one of the things I was going to mention in this talk is the lack of linear algebra library support in Rust for scientific computing. There is stuff there, but it's not very standardized, which is annoying when you're coming into this and like trying to figure out what you're doing. Luckily, for a lot of this, I didn't have to think in terms of matrix multiplication. There are other ways of solving some of these problems. The FEA is definitely matrix multiplication, in which case I had to use some random, obscure, sparse linear algebra library, which I didn't very much enjoy using, and I really wish there was an alternative. So if anyone in this room would like to write a nice linear algebra library, that would be great.
I noticed that in a lot of the pictures that you showed, there was like lots of metal around in the building, and my question was like, are there any interesting like architectural or design challenges related to that? Because like, presumably you don't want random metal things flying towards the magnet when you turn it on.
Very astute of you. So yes, we are very careful about what versions of steel that we use. Luckily, in our current device, it's not strong enough to really attract to the ceiling beams. But if we were to build a 20 Tesla magnet, we need to worry about that. So yeah, there are types of steel that are not magnetic or not very magnetic, which we tend to try and go towards, but they aren't the best mechanically. So it's sort of like the trade-off between those two different things has been really reasonably interesting in like the entire fusion industry of like trying to figure out exactly what metals to use, because apart from the fact they need to be non-magnetic, they need to not contain certain elements that will get very radioactive if they get hit with neutrons. So it's been like the material science of actually selecting which steels to use has actually been quite interesting as well, where we haven't quite got there yet.
All right.
Cool.
That's it. Tom with the very non-boring shirt as well, by the way. Give him a warm applause. It might be too early to call this, but I feel like that's the best shirt of the conference. Our next talk is To Make Your Own Smartwatch by Anders Rasmussen. Anders is a generalist programmer with almost 20 years professional software engineering experience, a Viking by birth, born and raised in Denmark, living in Australia with their wife, their wife and 2 3-year-old beagle puppies, which hopefully there is pictures of them. Anders picked up Rust around 2017. They contributed to open source and started using it for electronic projects in 2020 during the lockdowns, trying their best to convince employers to invest in Rust in a long-running side quest. So please give a warm welcome to Anders.
There you go. Thanks.
Is it live, Tempting? Can we pop it up? That looks like it.
Thank you. Yes. I sadly do not have any pictures of my puppies in the presentation. I'm sorry about that. I actually forgot what I had written in my introduction. But I do have plenty of pictures, and my wife, who was with me earlier for touristy things, picked them up today from their daycare. And so she sent a video of them in the car, and they looked very happy to be picked up. So that's very exciting, and I'm looking forward to seeing them again. Just fishing out the thing that we're going to talk about today. This is a small 1.28-inch round display. It runs Rust natively. And this title is sort of a little bit of a gotcha. This is and then we draw the rest of the owl at the end of it. We're going to talk about a tiny, tiny bit, which is getting touch to work on a screen like this. And for that, I found a crate called the Device Driver Crate. It is developed by Dion Doctor from Netherlands. I'm not going to pronounce the company name correctly. It looks like Tweeter Golf, but I think that's not quite right. But let's get into this. So a bit of an introduction, background in embedded and device drivers, because it might seem a bit intimidating at first. Then I'll go through a walkthrough of implementing the driver, which surprisingly isn't that difficult, and you'll see, but then we'll also go through what challenges there might be, and then a bit of a conclusion. I was going to do a live demo, but I'm not trusting the demo gods today, so see me after the talk during the lunch break at the room at the back, and I'll show off the demo. And I'm also going to be working on getting Ratatouille to work on the RP2040 device that I have, because it's not quite working yet. But that's basically going to be the rest of the owl in Ratatouille. So yeah, as Amber said, my name is Anders, or Anders, if you want it in Danish, and a software engineer, done a lot of different stuff, mostly web development, but I've been interested in electronics since I was a kid. I've pulled apart a lot of stuff, to my parents' dismay. Most of it got put back together, but I'm not quite sure if it worked. And yeah, I also start a lot of projects. As said, I picked up Rust in 2017. Thought it was a nice language to learn. It was that or Go, and Rust caught my attention mostly. And then it sort of lay dormant. I was working in JavaScript at the time, and the company I was working at said, yeah, you can start doing some projects in Rust, but it never eventuated. And then lockdown happened, and as probably a lot of us, we were like, what are we going to do with our time? And in Melbourne, we had some lockdowns where we were allowed to go outside for half an hour a day. It was pretty hectic. We could go to the shops very, very sporadically. Like, it was pretty bad. So I decided to pick up electrical engineering again. I did try to become an electrical engineer at uni, but I dropped out because I was burned out from school. So I just did software engineering instead. But then, yeah, lockdowns came and I picked up a project. It was mechanical keyboards. I designed a low-profile 30-key split keyboard, and I was going to use Bluetooth. It's going to be great, and then there was a chip shortage. So I ended up picking up the cheapest, smallest chip you could find, the STM32, G0, and it's nothing, but Rust works on it, and it worked out of the box. I just had to have a debugger, and I had to plug it in, and then I was good to go. So that's what I did. The project's still not finished. I designed an enclosure for it, and then the chip shortage ended, and I got distracted by buying other things like these things. I have another one here too, a more bare bones version. You can see, well, you can't because it's small chips on the back. So yeah, and then I decided at the start of the year, because I got laid off my previous work, that I wanted to get back into Rust and like push that as my profile for recruiters to sort of like hire me. And to do that, I wanted to find a project, yet another project, that I could do to sort of like hone my embedded skills, because I wanted to get into firmware development And I wanted to sort of like reach out to hardware, software companies that do those things. And so I was like, okay, there are a lot of examples, and it's always like blinking LED. And it's always on like one specific board that you have to buy, and it's like this massive thing. But I'd already gotten these dev boards from Waveshare, and they were like $20 in Australian dollars, so like 15 US dollars. And so like, yeah, that was really cool. So I decided to look into what it would take to write an example for this. And I was like, I had my IKEA stand desk, and I'd seen a guy working to get that work. So I was like, all right, if I have this little round thing, I can use it to select different heights in that. So I was like, okay, but is there a Rust device driver? And I was like, not really. There is, but it's not great. And the documentation is sort of straightforward. So I was like, good work. We'll do that. We'll make an example. So that's what I did. I wrote out a device driver. That didn't take too long. I wrote out examples for ESP32 and for RP2040. And that worked out great. And then I was like, okay, let's make a blog post, and let's make a presentation. So this is what I did. And yeah, why embedded Rust? As I said, picking it up back in 2020, I found it really easy using ProBars to get Rust running on a device and debug Rust. And then the memory safety, of course, like I've used C++ and C programs, and getting that running on embedded was always such a chore. You'd always have some weird issue. And I was like, I like Rust, let's do it. Rust also has the type system, which really helps us when we're setting up all of our device drivers, because in hardware, you need to do things in a certain order for things to work. If you do it out of order, the actual electricity won't run correctly. And Rust's type system helps us in this. It really just gives us the confidence that when you press run, like cargo run, it'll flash it onto the device and it'll run. And you can get trace output. It's just great. So that's why we chose I chose embedded Rust for that. And as well, the ecosystem back in 2020 was like blossoming. Now it's a flower that's growing. It's really great, and it's nice to see all of the work that's going into that. And yeah, went through wide device driver. When you're working with things like these, especially new devices, a lot of the documentation is a PDF from a Chinese company that you have to machine translate to get things out of. And then you gotta like make sure that things work correctly. Again, that the hardware is initialized correctly. And so as a challenge, that's why I wanted to see how hard can it be to write a device driver. And as it turns out, with the device driver crate, it's actually not very hard. So I think we should start to get into what the device driver crate is. The device driver crate is a framework for describing the protocol. It lets you say what kind of memory layout things seem to have. By saying seem to have is that when you talk in embedded, it's like writing to RAM. So this is where the unsafe stuff comes in. It's unsafe to write to RAM that isn't RAM. But the device driver and all the embedded HAL stuff hides all these things away from us. So as implementers, we don't actually need to deal with this. So this is the great thing about using an abstraction like this. as well as giving us those things, it gives us a way to easily generate documentation. So the device driver crate, when you set up all the sort of code for building it, it also generates documentation, and all those things are also type checked. So if you write some documentation in this DSL that's in the crate, then that will also get type checked. So that's pretty cool. So let's meet the device. The touch chip is called the Heinrichsrand CST816S. It is one part of a family of chips, I think, where as a hardware implementer, you'll like call up the company and say, I want a chip that can read some number of fingers and have these sort of traits, so to speak. The issue is that that also means that the driver implementations on the web differ in slightly subtle ways. So I looked through several different C and C++ implementations, as well as a Python implementations and a Rust implementation. And they're all slightly different, even if they're claiming to be for the same chip. So I'm not sure that I got it right exactly what they can do. But the thing is, this chip is very responsive, and it doesn't use a lot of power, so it's perfect for a smartwatch, for this little thing. It has a low power mode, and it uses I2C, which is a fairly simple electrical protocol, and like just needs a couple of wires for that. The documentation for this is also great. It is in English, so you don't have to machine translate it. And it has a way to wake up the target host MCU. So that's really great. It does make it a little bit tricky to do it, but we'll see how that ends up working with this. I'm going to show you the data sheet for the register definitions, because this is a thing that we gotta keep in mind. As I said, writing to hardware in embedded is like writing to RAM. So there's going to be a lot of hex addresses. And as you can see here at the top, we have a register called gesture ID. It is hex 01. So it is the first address. And you send it a 8-bit, or it gives you back an 8-bit data. So with the way that the I2C works is you send an address and it gives you a reply back. So the host MCU is the one responsible for sending out things and then receiving things back. And here is the way that the data is meant to be interpreted. And so you can see here, the gesture ID is a number, 8-bit number, and it has a value either 0, 1, 2, 3, 4, 5, B, or C. And could anyone think of a Rust structure that would fit for this? That's right, enum. But there is a little bit of a twist with this one, because it's not a complete enum. This one is wholly. It's missing some bits, so this is a little bit, we need to deal with that. But we can also see we have a finger number, which is just a number. It'll be your finger, but no one has 16 fingers. So it'll be, for this one, I think it can support 5 fingers, and some can support 1 finger, and others 10. It just depends on what the hardware implementer wanted from the chip. So yeah, and then another part about this one is the RP2040 chip is here. The one I have here with the case is an ESP32. This one also has a Wi-Fi, and you get that all in a bundle for about the same price as a pub meal. So do you want to eat or do you want to play with electronics? One thing though, with developing for this chip, especially the RP2040, is that in this configuration, it doesn't have any debug output. So you're just praying. It's a little bit weird why they didn't choose to do that. So you're just praying that it works. And if it doesn't, then you pull your hair out. So I don't recommend using this for this particular one, just because of that. There are better boards to deal with that. I have another one here. This is an ESP32C6, much better. And this one also has debug out. I know some other people in the audience might have the RP2041 and has run into debug issues with this. But let's get into implementation walkthrough. Device driver exports a macro called create device. And it is a macro that has a DSL in it. DSL is domain-specific language. And it is it does sort of look like some YAML or some JSON. You give your driver, so when you declare this, this is the struct that sort of translates what comes into Rust structures. So you have to give that a name. We call it CST816S, because that's what the device is called. And then it has a few sections. So DSL contains the main bulk of our stuff. It has a config that's global for the whole chip. We only need to know that the register address type is U8, so the gesture ID tag, the 0x01, that is only a U8. There are some other devices that might use a different size for that. But that's very important to set here. Otherwise, the device won't work. Then next, we define our registers. So registers is a memory location. In a normal CPU, they're a register like we saw with like the assembly code. Like registers sit in the CPU. Here, they're kind of like a virtual thing. So we make a register for the chip ID, for instance. We can inquire the chip, hey, what do you think you are? Like, what's your sort of device name ID? And it can reply back. So we set it up with, it needs an access type. So this creates the type for like, if you want to read only, write only, or read-write to that register. So the device driver crate knows how to generate code for that and to select what kind of type is available for that. And then we have the address, so that's 0xA7. That is the address for that specific register. So for the gesture ID, it was 01. And then the size of bits that will return back from it. We have to say that that's 8, so 1 byte. And then we map the value. So value, uint, that's the Rust type we want out. And we're mapping those individual bits in the range 0 to 8, 8 exclusively, so index 0 through 7. So that's how that works. And then that gives the device driver crate enough information to basically translate out for us. We don't have to do any bit shifting here. We don't have to worry about endianness here. There is a possibility to do that, but by default, it's not really necessary. So I mentioned that gesture ID was a little bit special. Since it is an enum with holes in it, we have to implement it as a try. So that means that it's using the same pattern as try types in Rust, where it might fail. We're pretty sure it won't fail. We're pretty sure that the device won't send something back that's wrong, and we can't send anything to it that's wrong. But in any case, we still have to deal with that. So that's why the value is set as uint as try, and then we give out those different things as values, and then we have to map it 0 to 8 again. We can also give custom conversion types to the thing. So for instance, the interrupt request pulse width is a thing that the device can do. So it can, when you press, and it has been in sleep mode, when you press it, it'll send an electrical signal to the MCU. And if you set your MCU up to handle interrupts, which means being in a sleep state, and there's a bit of a hardware thing that's like, oh, there's a rising signal here. I should wake up the CPU, and it should handle that. That's called an interrupt handler. The device can be told, hey, pull this line up for this amount of time. And it's, again, it's a field that we have to write to, and it's a byte. But we can create a type that says, we don't have to deal with it not like saying that it's from 0 to 255. We could say this is an amount of time. And the documentation specifies what like an increment means. So we could implement a type that converts the value. And here, for instance, the pulse width has to be between 0 and 200, so we can't go over that. So we can make a type that won't compile if the value is wrong. So basically, Rust helping us enforcing these expectations that the chip has, even though the chip doesn't know what Rust is. It's probably some custom logic, but it just knows that it can't have a value that's higher than 200. And so this is really great. And so to use that, we'll just implement from for the type for U8. And Rust is like, great. So we're just using all of Rust to do that. And then in the DSL, we just tell it, use this custom type instead when you're transferring into the Rust thing. So we've done our base layout of all the registers now. And now we need to couple together the device types with talking to the device. And this is done over a bus. Not a school bus, but sort of the same way. A bus is a type of layout of wires on the hardware. And it's either a serial bus, which means that you have basically one wire and bits go down serially, so there's one after the other. Or parallel bus, where you have lots of wires and all the bits go next to each other down the bus. For this device, because it's very small, it uses a serial bus. It uses the I2C, but there are many examples of other buses, PCI, SPI, which is serial parallel interface, I think, and UART, that I can't remember what it stands for. But I2C is integrated circuit, which is this weird name, and is a serial protocol with, we have low-speed peripherals. So yeah, we don't need heaps of fast data here. We just need reliable data. 2 lines, there's a clock line that tells the receiving device, hey, some data is on the data line, you should read what it is now. So it can go from very low speeds up to around 1 megabit per second speeds in proprietary formats, also more than that, but in normal normal open standard I2C is like 400,000 kilohertz or something like that. So that's good enough for us. We don't need too much. I2C also shares the lines between the peripheral devices. So you have two lines that goes to a lot of different things, and the central host controller just sends the address of the device out. And so all the peripherals will see there's a message, but if it isn't for them, they will discard it and they will go back to sleep until the next thing. So to do that, we need to implement some interfaces, register interface, and use embedded HAL. And we just need to give an address for this device. It is 0x15. It's a 7-bit address, because this was made a long time ago where bits were precious. There's also a 10-bit interface address, but no one really uses it. So we can have 7-bit worth of devices, but usually not that many. And then we just implement the bus, so impl I2C, so that's the embedded HAL trait for I2C for that device. And then we have to tell it how to read a register, which is I2C write read, which means I need you to write to the bus and then wait for the data to come back. And then we have to make a write function where it's a little bit more complicated, because we have to have a transaction where we write the address and then we write the data. But not too much more. And then we're done with that. And then handling errors, as you saw, it's just Rust. So we just use result types for handling errors. We can do whatever we want in the interface between the device driver and the code that uses this. So we can make it as pretty as we want or as ugly as we want. And we do that in the high-level driver. And we can do pretty much whatever we want in this stage. And then I wrote an event method. So we'll go through this because we don't have much time left. And here, like when someone touches, we have an event, and we'll check, did we get a interrupt on the pin? If not, we don't do anything. Otherwise, read the X position, read the Y position from the device, and the gesture, and get that out into a struct, first a point struct, and then a touch event struct. And then we have things working. So that's it. I'm going to do the live demonstration down in the other rooms, because, yeah, that's it. Any questions?
We probably have time for one quick question. Anyone have that burning? There's one right up the back. Is there any chance you can run this up? Okay, we're going to see who can get there faster. Oh, sorry.
Hello, hello. Interesting talk, thank you. Simple question, what happens if you panic in the driver? I saw there were some unwraps there.
If you panic in the driver, then for it's up to the person who uses the driver what's happening. So you can, when you set up your project to run on the thing, you can set up what kind of panic handler is built into the device. So when you write an embedded program, you need to deal with a lot of these things up front. So there are a lot of different ways to do it. You can halt basically just stop the CPU, or you can use a bit more sophisticated debugging where you can use ProbRS to get the traces out. But basically, there will be a panic handler built into the firmware, but it's up to you to set that up.
We probably have one more sneaky question. No, or not. We can just go to the live demonstration, which will be down the end. So let's give a warm thank you to Anders.
Thank you.
So Anders will be down in the collaboration space with all the goodies here. A few things just before we break for lunch. If you are spacing out and your brain has entered into another plane, we have a quiet space. You can actually head upstairs and make use of the mezzanine floor. There are tables and chairs up there so you can have some space and time to decompress. We went through a lot of science, a lot of electrical engineering. I get it. We have an hour for lunch, so there's time to hang in the co-creation space or brave the weather for a walk, but I think the weather's still quite fine, isn't it? I don't know, I've been in here all day. But we need you back at 1:30, so we're going to try and kick off really quick because we want to honour your time, our speakers' time, and make sure that we give them all great space. So, kei te pai, all good? We'll see you at 1:30. Let's go. All right, let us kick off. And I would like to acknowledge for our speakers that are about to talk that we are hitting the food coma sort of stage of the conference event. And so I think I'm pretty excited because it sounds like we've got some pretty cool speakers coming up who will hopefully light up and keep your attention span during this very difficult period in our conference time. And that's not to whakaiti anyone else, just saying I would fall asleep, so we need lights, music, and anything else that will keep us awake. So I do have some notices that we need to quickly go through before we can kick off. One, the first thing, please wear your lanyard. So we have had someone come into the conference venue to try and take jackets. Don't know how many jackets they were trying to take. May have looked like they were from Alaska, but we need to make sure that we know who you are. So don't be upset if you don't have one of these and one of our team challenges you, or the event team as well, because they're now aware of some of those issues. Secondly, our coat rack, in collaboration with the previous notification, has now moved to room 2, just to be a bit more secure, so we can make sure that your coats are there when you return. Kapai? Right. I am going to help you a little bit. We're going to do a quick 5-minute breakout sort of session, but you have to stay where you are is pretty much the key thing. So I want you to turn to someone who you do not know today. I'm going to help out you introverts and socially anxious and socially awkward people. Turn to someone you do not know, and I want you to introduce yourself with your name, where your ancestors are from, and who you would pick in your zombie apocalypse team and why. And we don't need thesis whānau. We just need a quick, because of this. All right, so I'm going to give you 3 minutes to have those conversations. You're adults, so I'm going to work out. You can match yourselves up. About a minute left, e te whānau, so make sure you switch over if you haven't shared the love. All right, 30 seconds.
5, 4, 3, 2, 1. All right, we're going to bring it back into the room right now. So did anyone have this amazing zombie apocalypse person that they absolutely feel like they have to share? I'm disappointed in all of you right now. I at least wanted some goss on what's going to happen. So that's cool. We were going to have a mic, but no one's brave enough to share. So instead, we'll go into some... I was very lucky to get to see the tech testing that we did just before the break. And our next talk is from Ruby to Rust, building a live performance tool with Rust by Jack Purvis. So Jack is a full-stack software developer based here in Wellington, so he's one of us, Etefano. His hobbies include creative coding, live coding, DJing, and VJing. He loves creating software and live visuals, and we'll be speaking today about how those will come together with Rust. So let's give a warm welcome to Jack.
Testing. Sweet. Thank you for the introduction, Amber. It's really great to be here at RustForge. I've been super looking forward to this event all year, so it's great that's finally time. Yeah, super grateful today to be talking about a few of my passions: creative coding, live coding, DJing, VJing, and Rust. Yeah, so the kind of aim of the talk today is to share with you how you can use creative coding to make live visuals, and the software that I created to do that in my own practice. And importantly, why I chose to rewrite that software from Ruby into Rust. I'll also share some highlights of the Rust code that I wrote, and maybe you'll learn something and you can apply it in your own projects as well. So let's get into it. Well, what even are live visuals? Well, it's all about making pretty images in live settings. So these are the visuals that you see projected on screens or LED panels at gigs, events, music festivals. They're often designed to complement music, and they're often dialed in by a live performer, though you also see them in like art installations and things like that as well. These images here are of some of my own work. The first three are of me VJing at a music festival, while the bottom right one is me live coding at an algo rave, which is where we write code live as part of the performance practice. My visual style was pretty abstract and geometric by nature, and that is mostly because I generate all of my visuals in real time using code. So let's talk about creative coding. Unlike regular programming, the aim of creative coding is not to do something functional, but more to express something. It's to create artwork, it's to create animations, music, lighting, or even live visuals. So the whole idea is to leverage code as a tool to enable artistic output. It encourages playful programming, where code is not only written, but also tinkered and interacted with in interesting ways. So this here is processing, which is a popular language and framework for creative coding using Java. Some of you may have heard of it or even used it before. So on the right you have the interface where you write little scripts. They're called sketches. And then on the left you have the result of running that sketch, which is some visuals. What I really like about this kind of creative coding is that it's really simple. The API is pretty easy to learn, and you can get straight into making visuals with minimal boilerplate. And this sort of makes sense, because processing was designed as a tool to teach artists how to code, so that they could be empowered to use it in their own practice. So the other thing I mentioned today was VJing. So what's that? This is like a live performance art practice where visuals are created or manipulated and live to create compositions that complement music. VJ stands for video jockey, which you could kind of think of as like the visual counterpart to a disc jockey or a DJ. So VJs typically work with video footage, they work with pre-rendered content or sometimes real-time content like shaders, and they combine this content together to create an image for the audience to experience. They often use controllers as well, like this one I've got here, so that they can kind of play with the visuals like a live instrument. The image here is actually of an VJing art installation on the Wellington waterfront, not far from here. Not mine, but some local VJs who put it together. It's pretty cool. This is an example of some of the industry standard software that VJs use. This one's called Resideo. You can see at the top there's a bunch of little video clips, and the idea is the performer can easily switch between them. And at the bottom left you have like a preview of what the audience is currently seeing projected. And then there's a bunch of like parameters and effects and things that they can play with as well. So the question that I asked myself when I was first getting into VJing was, how do I use creative coding with it? Well, I'm going to talk you through a few of the options. One of the first ones is to use a tool that supports visual programming. This one here is called Touch Designer, which is pretty popular. It's a pretty flexible way to use like coded content, albeit visually coded. And it's a nice alternative to using like video clips and doing like real-time generative stuff. But this wasn't for me because I like text-based coding. I wanted something more like processing where you write sketches. So what else is there? This one here is called Hydra. It's a live coding environment. And it runs in the browser. You write JavaScript, and you can make these kind of cool images that look like analog video synthesis. And it's, yeah, as I said, a live coding environment, which means that you can edit the code live at runtime and have the visuals update seamlessly, which is pretty cool. So this is great, but it doesn't have that kind of high-level interface features like I want with VJing software, where you can kind of compose different like sketches of images together. And so my search continues. This one here is probably the closest to what I was looking for. It's called Synesthesia. And you sort of have this interface, which is quite intuitive. You can kind of switch between these different scenes and manipulate parameters. It supports video clips, but the draw point was it also supports using shaders. So you can code your own shaders, and then that code can be manipulated in an interface. So you can use creative coding with that. And shaders are really great because you can make some pretty sophisticated visuals with them. But my issue is that I feel like they have quite a steep learning curve compared to like sketch-based creative coding. So with all these pieces, hopefully you can kind of see the motivation for why I wanted to create my own tool. And this is where we enter Visor VJ. So I thought to show it off, I would try a live demo. So I'll just get that started. So you just give me a moment. Should be as easy as that. So the whole idea, one moment. Yep, cool. So Visor VJ, it doubles. I'll switch to it. Yeah, maybe I'll switch to it. Can you hear me now? Sweet. So the whole idea of Visor VJ is it doubles as both a creative coding environment and a live visual performance tool. So the idea is that you can live code sketches in in TypeScript or JavaScript, and then you can kind of take those sketches and perform with them like you would as a VJ. So kind of on the left here, you have, I had to bring my mouse over. So we have a sketch library. So you kind of organize all your sketches into this library. You can kind of preview them. You can kind of have a look at them, play with the parameters, do various things. So these are all coded sketches that can be performed with. And I'll show you what the code looks like. So if we jump into a sketch, I've created an example for the presentation today. So we can go edit code. We get our sketch code. I should probably preview that one. There we go. So we've got a nice red rectangle spinning around. I'll describe the kind of like key components that make up a Visor sketch. So the first part at the top is we have a thing called a drawer, which we need to create. And this allows us to draw things to the screen, like the rectangle there. So you can see at the bottom we call draw rectangle. We pass in some parameters down there. We also have parameters, which you can define here. We've got a slider, excuse the type checking, a slider and a toggle. And then these actually appear in the interface, so the performer can manipulate them live and influence the visuals. And that all comes through the code. And I'll show off what that does in a moment. And then the third key component is this function that we have to export called update. And this is the function that gets called every frame by the engine so that you can create animated visuals as things change over time. Yeah, and there's a few things going on here. We're clearing the screen. If we didn't do that, then it would look something like this. As you can see, I'm like updating the code in real time, and I can execute it and things change. Let's change that number there. There we go. And so there's a few different things going on, like here's that rotation. We can get access to the time. Down here we do our little loop and we actually draw the thing. But yeah, all of this is live and you can edit it in real time. Cool. So the other part I haven't quite talked about yet is this whole right side of the screen. So on the right side of the screen we have the kind of composition interface where you sort of compose your different sketches together to create something that you want to show to the audience. So I'll just scroll over here. So I've got some other visuals I prepared earlier. So you kind of have this bank of sketches that you can easily switch between. So I could bring this one in, maybe this one. And then you get like a live preview of what they're looking like. Each of the layers, these are layers here. So kind of think of it like Photoshop. You can kind of composite them together. You can set different blend modes. And then you'll see the final result in this composition interface. So I'll just bring in those layers using my controller here. And now we've sort of got a thing going on. And all of these parameters can also be manipulated through a controller. So you can either do it in the code or you can map the parameters in the interface to the controller so that you can kind of perform with things live. So I'll just demonstrate that here with the slider. We can sort of attach that. I can pick a controller on my interface, create that, done. Now I've forgotten which one I did. There we go. That's all happening live. Thank you. So I thought I might just VJ for a bit just to show you what that looks like. So we'll bring that over. And I was going to play some music. I assume they'll dial it in. We'll give you the... Oh, I've lost it. Audience experience. Nice. You can kind of do like a masking effect. Sort of got some kind of built-in effects as well, so you can kind of do like mirroring and things like that. Change the colors as well. Sweet. Okay, now we had a bit of fun. Let's get back to the talk. So, Rust. Where does Rust come into this? So I made a decision to write the software in Rust. But before I can I might switch to this if that's all right. I need to kind of rewind a little. So you may remember the word Ruby was in the title of the talk. So there's a reason for that. And that's because I originally wrote the software in Ruby. Yeah, so I started developing it back in 2018, which when I was pretty into Ruby programming at the time. I was using it at work and things like that. And so I built this app. It looks kind of similar. You can probably see similarities with what I just showed you, except the main difference was you actually wrote live coded in Ruby this time. And it was a good choice at the time because it's a dynamic language, which I needed for live coding. So it's really important to be able to change things on the fly in a performance. It also provided a lot of like reflection and metaprogramming abilities that were useful. So how that was implemented was I used something called JRuby, which is Ruby implemented in Java, so it runs on the JVM. And this was especially important because I was actually using processing as my graphics library and creative coding API. So to actually turn processing into a live coding VJing environment, the quickest way to do it, with my experience, was to wrap that with JRuby. Yeah, and then I also used Electron to turn it into a desktop app and built a web-based interface with React. Now the stack actually worked pretty well. Yeah, making use of processing was just really good for testing the idea and just seeing if it could work. And I would say it was a success. I've been using it in live performance for about 6 years. Yeah, so that was all great, but as you may guess, there were some limitations. So I'll just talk about those for a moment. Yeah, what were they? The first one was maintainability. So the Ruby app was fairly difficult to maintain for various reasons. One of them was I was quite coupled to processing. I had to do a lot of trickery to like work around the kind of core loop that it wanted me to use. So that was, yeah, lots of monkey patching and things like that, if people know what that is. Yeah, it was also the dependencies were fairly dated, like using OpenGL was the renderer when it's sort of deprecated, and there's definitely bugs in the Java version and things like that. So I was sort of like stuck with, I couldn't really do much to get around those issues. Yeah, and also just the whole nature of the code base being untyped in the back end made it really difficult to refactor. Performance was also limited due to the nature of interpreted language. Running on the JVM has some optimization, but there's also, it's like really slow to boot up and has garbage collection, which like stutters the frames, so the audience sees that. Not great. Another thing was extensibility. Big monolithic code base, hard to extend. I really wanted to break out the kind of core engine so I could open source it, but that just didn't seem possible with how it was implemented. And the final part I'll touch on is security. While it might not seem like on the forefront for a VJing app, it is when you're talking about sketches that run arbitrary code. So ideally you would have some sandboxing to stop users from running malicious code, but it didn't have that because it was just JRuby. Yeah. Now, while a lot of these issues could have actually been resolved by spending time, I kind of felt like some of it was a bit more fundamental to the technology choices. And so that was why I was motivated to rewrite Visor. And of course, I chose to rewrite it in Rust. So I'll talk a bit about how the Rust version works and why I think it's better. So the first thing I want to talk about is this package I use called Dino Core. This is a Rust interface to the V8 JavaScript engine. It's what powers Dino, which some of you may know is like a spiritual successor to Node.js. For Visor, it means that you can do your live coding in JavaScript or TypeScript. It also provides a sandbox for code execution, so it's way better for that reason. But I think the most interesting thing about Dino Core is its ability for you to write these extensions in Rust that you can call from JavaScript, which is super powerful because you can basically have a high-level user sketching script language, like for sketches, and then you can offload a lot of your intensive work to Rust, especially like where the GPU is involved and things like that. So I thought I would illustrate this with an example because I think it's pretty cool. So yeah, here we have a Dino Core extension written in Rust. It's called my extension, and it defines one operation that returns a frame count. It also references some JavaScript files. So this is what the JavaScript looks like, which forms the other half of the extension. The frame count is a function that we define, but it also pulls in this frame count operation that appears magically from the Deno core namespace. So Deno kind of embeds that for us, and then we can use it in the JavaScript. And then we just assign that function, the frame count function, to the global scope. Next, we need a main function to kind of create a JavaScript runtime. So that's what this is here. We create a JavaScript runtime, we pass in our extension that we just defined, and we load some JavaScript code from the disk, and then we run that code in the runtime. So say we have the script here, so you can imagine, yeah, this is like the sketch code. It calls the frame count function and it logs it to the terminal. So if we run that, we get our frame count. So this is pretty neat, and this example really only scratches the surface of what is actually possible with this. And you can probably imagine how it's quite useful for something like Visor, perhaps even in your own use case. Something else that I thought was pretty cool with the new implementation was a plugin system, which I implemented using traits. So the idea is that you can define a plugin, and it has a Deno core extension that it has to be able to return, which means that every plugin can define its own JavaScript API, as well as a number of Rust operations that back that up. And then they can also supply some callback functions that hook into the kind of core life cycle of the Visor engine. So you can kind of do various things at points in time or store state and stuff like that. And so this is great because it means that people could write their own extensions. I even wrote all of the kind of core sketch APIs in Visor with this plugin architecture. Something else that's kind of neat is that you can load them at runtime using something like libloading, which I think could be fairly useful for if the user wants to load a plugin from their sketch code, they could use this. So you don't necessarily have to compile the plugin statically into the app. The system was also pretty cool because it meant that I could open source the underlying engine, and then the VJ app is actually just a plugin. So the next thing I'll introduce is Nano. This is a creative coding framework written in Rust, sort of like processing. It's pretty cool, worth checking out. I found it has a really flexible kind of drawing API, which was kind of an advantage over using processing, because with processing I was kind of tied to how it wanted me to do things, but with Nano I can just draw stuff and then take that and do whatever I wanted with it. So that was really great. The next thing was, so it uses WGPU for the graphics rendering under the hood, which is a kind of agnostic, safe, portable graphics API written in Rust, and it's based on the web GPU standard. So that means that under the hood it'll run Vulkan or Metal or DirectX depending on your architecture, but you only have to write your graphics code in Rust, and you get all of that for free. So I think it's pretty cool. It also underpins the Bevy game engine, which some of you are probably familiar with. I'll just quickly talk about how I bring the whole engine together now. So the whole idea is that we have each sketch running on a dedicated thread. Each sketch has its own runtime, so it's all sandboxed. The sketches communicate with the engine using Tokyo, using async channels. Every update, each sketch creates a number of draw commands using Nano, and those all get run in parallel. The engine then awaits those instructions and compiles them and renders them to a window using WGPU. So kind of simplistically, this is what the kind of core loop looks like. And this is a nice improvement over the last version because it was single-threaded before, and now it's multi-threaded. So the sketches run in parallel, and all the GPU work is handled nicely sequentially. So one thing I haven't really talked about yet is windowing. So how do I do that? Here's Tori. Tori is a desktop application framework written in Rust, sort of like Electron, but I think better. So it runs Rust on the back end, and then I can use a web view on the front end with React. And it's kind of quite security conscious by default. Speaking of front end, another thing that I thought was pretty cool was the ability to generate types of Rust that you can use in your TypeScript code. So I'm using a library called TypeShare. So say you have a Rust type, like an enum in action here that has various things that you can call from the front end. You can annotate it with typeshare and serde, run the typeshare command, and then you get some TypeScript types that you can use in your front end. So I've fully typed the whole front end for Visor with this method. So back end to front end it's all seamless. So that makes it way easier to maintain. So what's the result of all of this? Well, for one, the code base is now way more maintainable. It's based on newer libraries. It's fully typed end to end, and I have better control of the underlying engine. Easy to refactor, easier to create new features. Performance is also improved. The backend runs natively, multi-threaded. Computationally intensive work is offloaded to Rust, thanks to Dino Core. And this ultimately means better frame rates, better resolutions that audiences can enjoy. And the software is also extensible by design. Yeah, and security is also improved. So yeah, overall, I'm like super stoked with how the rewrite went. There was a lot of experimentation and prototyping that went into it, but I think it really, the result speaks volumes of what is possible with Rust. So yeah, I hope you can find some inspiration in this and perhaps even use these techniques in your own projects. I'll just quickly race through this for time, but if you're interested in using Visor, the app isn't quite out yet, but there is the engine is available on GitHub if you want to check it out. You can use it for creative coding. You can use the engine in your own code. Yeah, and those are the links. Yeah, feel free to check them out. Thanks for listening to my talk.
Okay, we have time for one super quick question, distinct to the point. Oh, of course it's on my side.
Hi, you briefly mentioned Bevy Web Engine. I've seen a few people have ideas on interesting ways they can use Bevy. I was just wondering if you'd thought about using that for some visualizations and like 2D to 3D and that sort of thing.
Absolutely, it's on the roadmap. In fact, that's kind of the next thing I want to do. Nano is actually looking to refactor to do the same thing. Kind of staying up to date with WGPU is a challenge because it's still quite new and it's evolving. And so, yeah, they spend a lot of time keeping up to date with that, but Bevy has a lot more critical mass. So that's like a big reason to do that for me as well. And of course, then I get 3D rendering materials, shaders, all sorts of things. So yeah, definitely thinking about that.
All right, another round of applause for Jack. All right, I am going to, there's a bit of a tech shuckle here. So what I'm actually going to do is read some poetry while we do this. And then we'll get the next speaker to come set up, and then on top of that, I will then introduce him before getting into it. So I'm going to be sharing some poetry from a very good friend of mine. Some of you who live in Wellington might know him. His name is Chris Cormack, and he is from Kaitahu, Kati Mamoi and Waitaha. Chris Cormack has led a career that weaves technology through culture and knowledge for over 20 plus years. Try not to be too distracted from the giant glowing ball beside me. So he weaves technology through culture and knowledge for over 20 plus years. As data is a taonga, data sovereignty has been a reoccurring topic of interest in his work. In his role as kaihua wairi matahiko at Catalyst IT, Chris often ponders the complex dimensions of data sovereignty as it manifests within our digital infrastructure. The questions surrounding where and how our data, particularly Māori data, is stored, accessed and governed are becoming more important. This poetry that Chris wrote talks about the impacts of generative AI. Generative AI, the newest extraction machine, taking without consent, giving without consent. Trained on our stories, our art, our knowledge, regurgitating approximations stripped of Māori. Technocrats build their empires of data on server farms consuming rivers and power, while somewhere in the Pacific, islands drown under rising seas their algorithms helped create. They harvest the fruits of collective creativity while calling it intelligence, calling it progress. But what intelligence exists without whakapapa? What progress comes from broken relationships? These tools become artifacts of cultural memory. But when we ask under whose tikanga they operate, the answer reveals the same colonial master. The real question isn't whether these tools work, but whether they uphold our fundamental values. Kaitiakitanga, manaakitanga, whanaanotanga. By these measures, most remain utterly koretaki. The digital future we need won't come from Silicon Valley's exploitative imagination, but from our collective resistance and creation. Grounded in tikanga older than their empires, when we understand our data has whakapapa, when we demand tino rangatiratanga in digital realms, when we refuse to separate technology from tikanga, then we begin to imagine truly liberatory tools. Until that day, the question haunts us. If we use these extractive technologies, enriching technocrats, hastening our demise, maybe we deserve it, but our children do not. Those in the countries we exploit do not. Those whose water feeds the server farms do not. Those whose minerals fill the circuit boards do not. Those whose futures shrink with each prompt do not. And on that happy note, I am going to be introducing our next talk. Rust and Colour Embedded LED Art speaker is Mikey Willams. So Mikey is a Node.js turned Rust developer who lives here in Te Whanganui-a-Tara, Wellington, so again, one of us. I'm just saying, the brightest and the loudest come from here. Tamir. He helps organise Art Hack, a creative tech event every Thursday night, and is an aspiring solar punk interested to peer-to-peer networks. So let's give a warm welcome to Mikey. Do you have the other mic?
Is the other mic?
It's just here, and it's on. It's fine.
Cool.
Hello, everyone. Thank you for the introduction. I'm going to talk about how to use embedded Rust to make LED art. So you already heard about me. That's my family, my partner, my 2-year-old daughter, and my cat. They're very helpful in all this. So I made this LED cube. That's what you see here. I'm going to talk about, how I did it, how you could also make LED projects if you wanted to, and things I learned about embedded Rust. So previously, this is not my first LED project. I made some LED suspenders. They were pretty cool. I made this LED tetrahedron. So this was like 2018, before embedded was really a thing. But it was what gave me a lot of the ideas that will feed into what I am doing here. This was a tensegrity. So tensegrity is like a concept from Buckminster Fuller of having struts, which are like compression, and ropes or things that are tension, and you can kind of create impossible looking structures where struts aren't touching. But this was LEDs, LED tubes. So this is about how Rust plus LEDs is magic. In essence, it lets you have high-level abstractions for low-level systems. Like you need to have precise timings, et cetera, but we can do it in a really nice way that other languages I don't think offer as well. And we're going to have to do no STD, so no standard library. You can't have threads or channels, or you have to use this restricted core, and then no alloc, which means it's even harder. You can't use box, you can't use vec, can't use map, or any sort of data structure that incurs a heap allocation. You have to have everything on the stack, so all the memory has to be known up front. but I'm going to say it's no problem. Everything will be fine. You just won't be able to rely on some of your existing fallbacks. You have to learn new patterns. So I'm going to start with kind of the final code. And this will just, it doesn't have to make sense, but it'll lay out, this is the high-level abstract system. We're going to build up the cube. This is the code that runs the cube. We're saying, okay, it's a 3D thing. The layout is a cube layout. It has this noise pattern. It has a WS2812 driver. And yeah, we're looping, similar to what Jack was doing, looping to update the colors. So breaking those pieces down, sorry, going back, we have like the LED driver, the layout, the patterns. We're going to go through those pieces one by one. So LEDs, they emit light, and then our eyes perceive them as color. So what are RGB LEDs that are inside this thing? Basically, we tricked a little rock into emitting light. And they're very tiny. Like, they're tiny things that emit light. You have to diffuse them, otherwise they don't look well. If you've seen this on the co-creation days, they're really blinding. But there's 3 of them, 3 tiny things right next to each other, and that's red, green, and blue. And why do we have those colors? It's because we have 3 photoreceptors in our eyes that most closely match those 3 colors, which means that we don't actually see all light the same. If you see a rainbow, we're not actually perceiving all of the wavelengths. It's just triggering those 3 photoreceptors, which means we can just use red, green, and blue lights, and it will trigger them in the same way, and we can make up any color. So with LEDs, they can only be fully on or fully off. There's no half on. So if you want to actually dim an LED, you need to have it fully on for half the time and fully off for half the time. And you might think that that would flicker, but we don't notice it. If you do the flick on and off fast enough, it just looks dimmer. And so that's how LED dimmers work, is they're actually just changing that pulse width modulation. Then if you change how much light, how much photons are actually being emitted, our perception of brightness is not linear. So if you linearly increase the photons, you don't linearly, our perception isn't linear. We're actually really good at perceiving low light differences. We're hunting at night, we need to go out into the forest and perceive those low amounts of photons and that difference between that. But also we can go outside during the day and have the sun shining on us, and so we have a high dynamic range. But if you want to have a system where I want to double the amount of red, and that to mean double the amount of perceived red, then we need to do what's called gamma correction, where we kind of invert the curve. So that's called sRGB, and there's a few other parts, but that's what we think of as RGB, HTML colors. If you increase the red, it increases the perceived red. But for LEDs, you need to think about the linear color, because LEDs are emitting photons, and when you control it, you're doing the pulse width modulation. Then you have other color systems like HSV, hue saturation value, which is a nice way of using colors. There's newer ones, like people who got into the color perception theory, like OKHSV, OKLab. But Rust enables us, we can just have a trait that converts between all of them, and you can use whatever you want. So we have a struct for all those and just convert between them. Addressable LEDs. So those are the things that are in this. You might have seen them before. The little board that we were given has one of these in it. If you've seen strips of LEDs, that's what these are. So a WS2812 is what I'm using in here, and that's an example of this. You talk to the first LED, it talks to the next LED, et cetera. So it's you're filling up a bucket, and then after you filled up the first bucket, then you fill up the next bucket. But sorry, you're only filling up that first bucket, and it's overflowing into the next bucket, and so on. So you're talking to one LED, but you need to know the order of all of them. And on every frame, you provide a color for all of those. So clocked LEDs, there's kind of 2 types of LEDs, clocked and clockless. So clocked there's 2 wires. These are the ones that I got into. they're SPI, essentially, the like master out slave in for people who do embedded. But they have 2 wires, and when the clock is controlled by the thing writing to it, when the clock goes up, then the LED will read what's in the data. So the writer's kind of controlling the dance, and the LED is just being controlled, and when the clock goes up, it reads the data. And then, you know, you send bits with like 0's low and 1 is high. But then manufacturers realized that you could make things cheaper by just removing the clock, and you just have 1 wire. So to send data to the LEDs, you need to have very specific timing. So on the spec sheet, it says, okay, if you want to do a 0, you need to be high for this amount of time. So on the WS2812, it's 0.4 microseconds, and you need to be low for 0.85 microseconds with a tolerance of 150 nanoseconds. So it's very specific and very precise, but microcontrollers can do it. You just have to figure out how. And then if you want to send a bunch of bits, a bunch of wires, then, a bunch of data for your colors, you just kind of, you have a template for what 1 is and what 0 is, and you just do that. So, bring in some Rust. If every clockless LED is described by the timings, then we can make a trait that has all these associated constants that encode those timings. And then if we want to implement, say, hey, this WS2812 LED, we can then implement that trait, provide all of the constants, and then we can implement all of our drivers based on this trait, so they'll work for any LED chipset, which is nice. For this controller, which is the ESP32, which is on the board that people got, it has this RMT peripheral, and it's meant for like TV remotes. You want to send some waveforms to like a TV remote receiver, but you can actually hook it up to any pin, so it's perfect for, we want to have very precise nanosecond precise waveforms. So this peripheral is really handy. So we can take our LED trait that has the constants, we convert it into, you know, there's a clock for the peripheral of 80 megahertz. So we have to figure out how many clock cycles does it need to be, you know, for the 0 high, for the 0 low, et cetera. So we encode those as pulse codes. And then when we write write some color data, we're then taking the input, taking that color byte, we're then going to have the bit position, which is like if you think about it in binary, those are all the numbers in which everything is 0 except for 1 position. So we'll bit and that with our color byte, and then that will figure out if it's a 0, that's our 0 pulse. If it's anything else, it's a 1 pulse. So this wraps up our LED part, and this is our driver trait, where interesting to note here is like the pixels, we can't just use a vec because there's no alloc, so we have to have this generic I implements into iterator, and an iterator of colors, because we can't have an allocation. And then maybe the thing writing the colors writes one type of color, and the driver wants a different type of color. We can actually use the from color trait to just automatically, we say, okay, the colors coming in are just convertible into the colors that we want, which is nice. So that was all LEDs and colors. Now, how do we lay out these LEDs in space? And this is something that I think more LED stuff can do, and it's what I wanted to kind of add to LED libraries. A lot of things think in terms of arrays of pixels. It makes sense for like an image or a video. Those are just arrays of pixels. Our screens are arrays of pixels. But instead, I'm interested in what if every pixel had a position in a 3D space, and you think more in terms of a graphic shader, that given the position in 3D space, given the time, what color should I be? So this is what I did for this project in 2018 using Rust. I wrote software that it knew the position of all the pixels, and then as the time would happen, on every frame, it'd get the time and figure out the color for every pixel. And it looks cool. Like, I think it looks cool. Compare it to, for the tenseggrity, I used WLED, which at the time only supported 1D. So all of the struts are just one-dimensional. They're all kind of the same. It also looks cool, but it doesn't look as, like, I want the colors to like flow through space. And other people have been trying to make cubes with WLED, so they added 2D support. So people would take like a 2D mapping and map it onto their 3D shape. The cube looks cool, but the animations have like seams where the colors can't go across the whole shape. Then for like the sphere, someone made a DIY Vegas sphere, and when they were doing it, they had an opinion that the sphere to the right was not suitable because the pixels are further apart at the equator and closer together at the poles. And because they wanted to project a video onto it, well, you know, computer screens are all equidistant density. So then it would look warped. But for me, it's like, what if we just think about it differently and use kind of a graphic shader approach to things? I think it can still look cool. I think that sphere to the right could be made to look cool. So to describe our space, we have in 1D, left is -1, right is 1. It could have been that left is 0, right is 1, but I arbitrarily decided this. Bottom is -1, top is 1, and back is -1, front is 1. The reason I did -1 and 1 is because I want 0 to be in the middle. Again, totally arbitrary, but I just had to make a system of how LEDs get mapped into space. So if we have like a 2D grid, each of these panels on the cube are these panels. So there's 6 panels on the cube. And you map the LEDs in space with the X and Y. But notably, it's not just the positions, but you also need to know the order of all the pixels. So you notice like the zigzag of the pixels. That's how the hardware is made, and your software needs to know that that's how the hardware is made. So that you know when I'm talking to the 17th pixel, here's where it is. So the layout trait that we then get to, you need to implement a shapes function that returns a shape. I'll get into what shapes are, but a shape has a function points, which returns all the points of that shape. So for free, the layout trait will give you a points function that combines all of the points of all the shapes so that you can get all the points of your layout. Now, a shape is an enum. It's the way of describing like where your LEDs are. So you could just describe a bunch of different points, but you could say, okay, it's a line with this density. It's a grid, because I'll manage the zigzag for you. It could be an arc. Now, something that took me a bit to learn was normally if I wanted to make a points function, and so I have this enum, I want to return an iterator for every case in the enum. Normally, so that means there's going to be different types of iterators being returned. Normally, I would return a box of a dyne iterator, but you can't do that because there's no alloc. So I've been learning a lot of cases where I would have used box of dyne of a trait. Instead, you can do just an enum, and there's some boilerplate where you have to like implement the same thing over again, but enums are really efficient. So in this case, returning an iterator for every type of the shape is just an enum that has a sub-iterator for all of those types. And because all the sub-iterators implement iterator, then the enum implements iterator. So that was our layouts. Now I'll get to the animation patterns. So we have the LEDs, we've laid them out. Now we need to make them do some color. So essentially, this is a function tick that's called on every frame. It's given the time, and it will return a color for every LED. Similar to a graphic shader, similar to like what Jack was doing with Visor. So you have this pattern trait. we see our tick function, where it's, given the time in milliseconds, returns iterator of colors. Now, I wanted this pattern trait to be generic over all possible layouts in any dimension. So normally, this was another thing that really broke my brain. So if you're implementing pattern for any layout, like you want to make a rainbow pattern, and you want it to work for any layout. So you have your generic layout, and you say, okay, this will work for any 1D layout, implements layout 1D. But then you also have a 2D version, so implements layout 2D. Rust won't let you do this because it'll say there could be a generic layout that implements both layout 1D and layout 2D, even though if you know that's never possible. So you have to use what are called type markers that you basically mark so that there's no possible overlap between the generic. So we're using the dim as a type marker to say this is 1D and the generic could never possibly overlap. Now, to make the pattern that we're doing here, it's called the noise function. Noise functions, if you ever played like procedurally generated games, commonly used to like generate terrain, take like a top-down 2D view of some terrain. Given the X and Y, it returns a random numerator. Sorry, I've skipped a part. Noise functions return random numbers, but those random numbers are smooth across nearby points. So if you took like a 2D thing and got a random number, you could use that as the elevation, and it would be smooth, get those rolling hills. So in our case, we could do a 3D noise function, given the X, Y, Z of the LED position. That would be a static noise thing. We could add time to it. We could add time to like the X direction, but then it'll like move in the X direction. So even better is we could add a fourth dimension, time, and then so if we imagine some random color space that's just all colors, all possible colors randomly, our LED cube is moving through this 4-dimensional color space, and that's what you're seeing. And I don't know what it means, but it looks cool. Noise pattern, you implement the tick function, takes in the time, returns the iterator of colors. The layout, you have a points function. So yeah, we're given the layout here. We have the points function. We're going to map over every point. We're going to pass in X, Y, Z of the point plus the time, and then we're going to pass that into the noise function to sample the noise function to get a hue and a value, which we'll use for OKHSV. And that's how these colors are made, which I thought looks cool. Like I'm really into it. So control, like we have all that. We've gone through the LEDs. We've gone through the layouts and the patterns. Now we want to like put it all together in a cohesive way. So you can make a struct that takes all those pieces and, so it has like the dimension, the layout, the pattern, the driver, lots of generics. Also, you could add like the brightness or other things you want to change. If you made this initially like with a new constructor, the problem is like you have a bunch of types and you have a bunch of values, and it just becomes like those generic types and the developer experience of trying to write it does not make sense. So instead, I made a builder pattern, but if I look on like for crates for builder patterns, none of them could do what I needed. I need ones that are like generic over types and values. So I learned some tricks. You start with like your control builder. So this is all the generics, the dim, layout, pattern, driver. I think of like each of a generic as a slot, and we're gonna fill in a slot at every step. So we're going to start when the control builder has only empty slots. Now, using the unit type to mean an empty slot was like something that I found from this person, Hanno Braun, who's making Fornjot, a CAD kernel, and he made a stepper motor library that did this. And I was like, because I don't really understand how it works, but basically that is an empty slot. So when all the slots are empty, then we have a new 3D function that will return control builder again with the dimension 3D in the dimension slot. Now, for filling in other slots, so like filling in the driver slot, all of the other generics will just pass through, but the driver slot is empty with the unit type. And then we have a function with driver that's been given a new driver as a type and as a value, and we return the control builder with that type and with that value. So basically, we're building up our pieces step by step, filling in the type slots and values as we need them. So at the end, all of the slots should be filled. We can then do kind of the generic, like the trait constraints. And if all those trait constraints pass, then we have our build function, and then we return the control struct. So it's just a much nicer way to build that. So then now we've seen this code before. We're building a new 3D with the cube layout, with a noise pattern, with the WS212 driver. And then we're going to loop getting the current time and passing that into the control.tick function. So let's say you saw this and you're like, cool, I want to get started. That's what I want to help people do. I did this because I made a library that has all of these things I've talked about. There's also lots of things I couldn't have time to talk about. But it's called Blinksy, trying to be, an LED driver to advance what's possible with LEDs. It also includes desktop simulations. So if you, I wonder why it's not moving. But basically, you can, you can simulate, because the desktop is just a driver, then you can look at what the layout is and you can visualize your pattern. So it makes it really handy so you don't have to actually flash to your microcontroller every time. I've also made template projects, so if you wanted to get started, like I have a 1D rope template projects. These are like really easy to get. Also at the conference, hit me up and I have. Would love to like help people get into it. These microcontrollers, the Gledopto, basically this company made controllers for that WLED, which is like an existing project, and I realized, well, it has an ESP32. I could just put Rust on it, and it worked. Also, if you wanted, I found this, another like off-the-shelf thing that you can get, that you can make like 3D patterns with. But yeah, basically, you could find me in the other room or anytime in the conference. I have different LEDs, and I would love to help people make LEDs. Or if you're watching this, reach out, and happy to help. So that's me. Thank you.
Do we have maybe one question? I'll accept two if they're quick, to the point, distinct.
Should be pretty quick. Hi. So the with your cube, is it basically just like you're visualizing a three-dimensional continuous space, and then it's just the intersection of the? It is. So it's just the surface.
Yeah.
So can you do any sort of topology?
Yeah. So you perfectly understood it. Where by defining, like you're making patterns generic over any 3D space. So you're describing them in terms of the 3D space. Then your layout just determines where are the actual pixels in that space, so that you can make any then topology. You can make spirals and whatever. That's kind of what I want to see, is like what's possible with that. I think you can make cool art installations. Thank you.
Can your code be applied to the Hub 75? protocol for LED matrices. Are you familiar with this?
I'm not familiar. So is it something to control like the big LED bulbs?
I'll show it to you later.
Yeah, but basically it should, I'm assuming it will be able to work to be a driver. So the idea is that drivers are supposed to be pretty generic so that anything could be a driver, including like, yeah, the desktop simulation. I wanted to do DMX as a driver so that you can control DMX lights. So I'm sure you can control what you're talking about, and that would be great.
That sounds like a co-creation collab that we could do today. Yep, mean. All right.
Thank you, everyone.
Massive round of applause. All right. Yeah, I was going to say turn the blinking cube off just to give our other speakers a fair chance. So our next talk is Tackling Complexity, a Test at a Time by Elias Junior, who's going to join us on the stage. Elias is living in Japan and building cybersecurity tooling in Rust. Elias previously worked at Huawei, Ireland Research Centre in the Cloud Reliability R&D Lab. He has also contributed to projects such as AWS Redshift. Yep, feel free to come up. And financial systems for companies like Stripe, currently working in the cybersecurity field in Tokyo, Japan. So warm round of applause. You're missing out. Don't leave. Cool. All good to go?
Yeah. So, hi, everybody. My talk is not as cool as like LEDs blinking or VJing, and I think I'm bringing us back to work, like on work-related things. So you guys are going to hate me for the next half an hour. I'm super sorry about that. But I just wanted to say that this talk is not about TDD. I don't want to build this talk on top of old dogmas or even try to impose new ones. I just want to share what worked for us in a specific project, talk about the intuition behind the tests we did, and also talk about a little bit about the Rust crates that we used that were super helpful. So a quick about me before we start. Most of my working life, I spend building cloud-related things, such as working on AWS, on the Redshift team at Huawei Observability Infra. And in 2019, I learned Rust. And my background is not C or C++. So Rust, for me, was a way to learn about low-level programming and systems programming while having a great friend, the Rust compiler. I moved recently to Tokyo, so if you are there and want to grab a matcha, please ping me. And as you may have noticed, I'm not an English native speaker, and in real life, there is no subtitles, so I tried to put the most important ideas into the slides. Okay, so let's jump in. So in a company I was working for, we had this ETL pipeline written in JavaScript. And we were rewriting things in Rust, and we needed to consume the same data source, a REST API, for another reason. So we thought, why not rewrite this one as well? Since it was written in JavaScript long time ago, everybody that worked on this pipeline left the company, so we are not even sure how it works, or even what is the source code. Yeah, scary times. But the thing is that this pipeline, the data that was right into the database was used by several other projects. So we needed to make it as close as possible as the original pipeline. And even if we notice a bug, we may need to replicate the bug. This is all because there is this law that says that our observable behaviors will be depended on by someone if you have enough users. This pipeline was running for years now, and software written in different programming languages were using it. So the chances of people relying on things they shouldn't was pretty high. Okay, so let's start with the E of the ETL, the extract part. And the extract part was actually super simple. We send a GET request to a REST API. We parse the response, that's JSON with CERD, and that's it. Real life version of this is a little bit more complex because we need the endpoint to be configurable. There is a header for API token. But other than that, it's pretty similar to this. And this is so simple that raises a question. Should we write tests for this? And when I ask this question, what I'm really asking is, should we just mock that function and test the color? So we return different response, different errors, and see how the color behaves? Or should we mock the REST service and actually test the extract function? Just so I know that people are listening, who would vote for one? Can you raise your hands? Okay, who would vote for two? Okay, I will assume the rest of the people will vote for doing both. So the thing is, I was told in the past that we should not test functions like this, mainly because we are just calling a crate or a library that is already tested. And we should spend time testing things that are more helpful or more meaningful. And the main reason for that is because we don't want to end up testing a mock that we wrote based on our understanding of the service, which is the same understanding we use it to write the code that's using the service, and that in the end of the day may not look nothing like the real service. But maybe we should take a step back and ask ourselves, why do we write tests, right? And I don't want us to stop and think what we have read about it, what we have seen in talks, but like, or even why managers have told us, but like, why do we as individuals write tests? So for me, I'm not a very confident person. Speaking here in front is very hard for me. And tests, for me, is a way to have this type of anxiety handled by the machine. So when I start coding and my mind starts to ask myself, does this line breaks that weird edge case we found last week? Well, hopefully there will be a test for that, and I can just run. That makes my life much easier, much more stress-free. And if I wanted to maintain the observable behavior of this ETL pipeline that was running for years and was almost a black box, I need tests. I need to offload all those concerns to the machine. And remember that simple function. Yes, there was a bug there, or a problem at very least. And the thing is, the legacy software running in production was fine. It didn't have this issue. And the software I was writing was fine as well. I mean, I had run that thing like hundreds of times, and I never saw that problem before. So I was somewhat hopeful. Like, maybe it's not my fault, right? Maybe the service is doing something crazy. Maybe they're updating it. I don't know. It's not my fault. But yeah, when I retried with the same input, I had the same issue. And by the error, it does seem like this is a problem with insert. So I could very well just grab the response body, save it in a file, retry the third parsing, fix the issue, and leave it as a test. But the thing is, I wanted to make sure that this thing would work in the future as well. And sure, today is the body, but tomorrow, I don't know, it could be a header, some weird header that they are returning now, it's breaking us. And there is this really good crate called 8CPP mock that allows us to record response and requests and replay it later. It works kind of like taking a photo of our interaction with the service. And the cool thing about those photos is that we can also use as documentation, for example. Of course, in real life, we would like the APIs to have proper documentation, but that's not always the case. This one, in specific, had a documentation. It was just very incomplete. So these photos really helped us. Another thing is that when the observable behavior changes, we can easily diff both the new photo and the old photo and know for sure what's happening. So we could fix things faster on our side and also report bugs that make sense for the people that owns that API. And to use that crate is actually quite simple. We start our mock server. We define where we want to forward the requests to and which requests we want to forward. We also need to define which request and response we want to record because we are not forced to record all of them. And one thing that I find it really nice is that it will only record the request headers that are explicitly set. So that means that we will not save by mistake API tokens. And because these requests are also used by the mock server to later know which response to reply to the incoming requests during your tests, you don't want to record things that change per each request, such as request date time. Then you can use your code as you normally would. The mock server has a helper method called URL that tells you which endpoint should you connect with. And then you just need to set where you want to save that requests and responses, which is a YAML file that I will show you later. Just a quick disclaimer. I know that we shouldn't be using alpha things, but I am using for these slides the 0.8 alpha version of the crate. It has been around for a little while now, I think since the beginning of the year, because the previous version does not have that feature. Anyway, to play back is quite simple. You just need to pass the YAML file you record on the previous step, and you just use your code as you normally would. The YAML file looks more or less like this. So the when part is the request. So you can see the path, you can see the method, and you can see the single header that I requested to record. That then is the response. So you can see the status, 200. There are a bunch of headers that wouldn't fit the slide, so I remove it. But you can see at the Git repo of this talk. And the nice thing is that it is so easy to take those photos that every time something new happens with our service, we can take those. if there is a bug in production, we can record it and try to reproduce, so we can reproduce it locally. We can rerun this 100 times if needed, and later we can leave it so that in the future we don't repeat the same issue. And I just want to super quickly go through the bug or the problem we just have seen. So the API that this ETL pipeline was consuming was returning some paths from a system which can be UTF-16. But they promised us that it would only return UTF-8 responses. So they were probably doing some pre-processing on their side. The thing is that in UTF-16, you may need two 16-bit code units to represent sum10. And for some reason, this API was sometimes returning either the higher part or the lower part of this pair. And you can reproduce a similar problem with this example. And the thing is for us was that we were marking that field as a string, and a string in Rust must be a valid UTF-8. So CERD was, with reason, complaining and saying to us, well, you broke your invariant. This is not UTF-8. And this is valid, I think, for most cases. But for us, it wouldn't matter because we are not touching that string field in our code. We are just using it to flush that data to the database. So we didn't matter for us, the string. And also, when we are saving this in the database, people that were reading from there, they may not need to have a valid UTF-8 as well because they have seen this behavior before, right? So they either didn't care, maybe they had, if they care, they did had workarounds, or they may need the original data. So the solution for us was to just use bytes buff because we could then just flush those bytes to the database. Anyway, let's move on. So the transform part of our ETL pipeline was a much more complex version of this. We received something that looks like the API item, and we process it, and we transform in something that's only meaningful for us internally. And the Golang community normally does something really cool on their tasks that really makes sense here. That's table-driven tasks. And the idea behind is that you define your tasks as a table where you have the description, the input, and the expected output. And you reuse the logic between all those rows. If you need to add a new task, you just add a new role. You don't touch the task logic. And I'm going to show you the intuition behind this, but you shouldn't use the code I'm going to show in production or in a real code base because the assert macro, they stop the task execution, and that's not what we want, but I will show you some crates later on to use instead. But this is the idea. You basically have a vector that's our table. Each item is a role. There we have our description, the input, and the expected output. We loop through it. And we basically give the input to the R function and assert different things about our output. If you want to add something, a new test case, we don't touch the for loop. We just add a new item to the vector. And there are a few crates that can help us write that type of tests, such as RS test, parameterized, and test case. All of them have a similar idea. You use macros to define the different roles, let's say, of the tasks. And your function works more or less as a template in a way. So this is expanded to something like this. And as you can see, each one of the task case is their own function, which means that if one of them fail, we're still gonna see the results of the others. For completeness, this is RS test, and this is task case. And we are almost at the end of our ETL. We have now the load part, the part where we throw data at the database. And there are people that always tells us that we should focus on unit tests. And there are people that say that we should actually be focused on integration tests, with tests that runs against our real external resource, such as a database. And there are pros and cons on both. But for this specific project, it was quite important for my sanity to test against a real database, because we were a lot of times just throwing bytes at the database. I didn't tell you this, but some fields we were serializing it as protobuf. So I just wanted to make sure that we could retrieve the data correctly from the database. But the thing is, when you have this type of external stateful resources in your tests and you're sharing them, you normally don't want the tests to overlap, because you're normally setting the state of the world, running your code, and then stating the final state, right? And if you have a test that runs in the middle of this, it makes your life much harder. And for that type of test, we have a crate called serial test that helps us to make sure that tests won't overlap. And you can mark tests with either the serial or the parallel tag. So tests with serial won't run within each other, but the parallel can run at overlap between themselves, but not with the serial tests. Tests that are not marked with neither of these macros can run at any time, and no assumptions are made. So we can relax now, right? We have done everything we needed. We test all the letters in ETL. There is nothing more to be done. We can just push the code to production and forget about it. But we want to keep the same behavior as the previous legacy software. And that thing is mostly a black box. And we cannot also trust our own code, because a small difference in a crate or how things are handled in Rust may cause a big difference later on. So one way of handling this is to have both the legacy pipeline and the Rust pipeline running in parallel in production. And we keep comparing both of the results for a little while. If there is any difference, we ping an engineer, and the engineer can take a look and see if it's acceptable or not. When we have enough trust in the new pipeline, we can flip out the softwares to read from the new database and throw away the old legacy. And I know I promised to not tell dogmas or rules, but these are the ones I normally try to follow. So if I need to create a mock, I try to use tooling that helps me to create it based on the real thing and not the voices in my head. I try to use table-driven tests when the setup is quite similar between all test cases. If the setup is super complex or very different, I normally don't bother, because it is way too hard and the code looks terrible. I try to think very well about what I need to test and why I'm running a test to know if I should use a real external resource or if I'm okay not using it. And of course, tests don't end when you ship the code. Sometimes we do tests in production. At very basic, we should have dashboards with metrics regarding our new feature or our new product. And yeah, that's it. I'll be around the conf, so if you want to talk about Rust, tests, or cloud, find me.
All right, we probably have time for one question. Don't all put your hands up at once. No? All right. I'm sure that's just because we're standing between them and afternoon tea. But you'll be here for the rest of the conference too, so you will be able to hit Elias up, have a corridor, and we have to get back to work sometimes. Sometimes. All right, we are now going into afternoon break. So we have Kai. You're going to have, what's the time now? I don't want to lie to you and tell you 30 minutes. You have until 3:30 p.m. I'm going to be the hard taskmaster. You have 28 minutes, all right? So need you back here at 3:30. Remember lanyards, please. Please always wear this. Code of conduct, how to report is on the back. Make sure you're back here. Have fun. Make sure you're all fueled up. We're ready to go for the last bit. All right, hoki mai. Let's come back into the conference. That was more for people outside than you guys. You guys get the gold star. There is room, lots of room over on the other side as well. Or if you want to huddle together, you're more than happy to do that. Too many more people out there, do you think? Okay. All right, we'll give it a few minutes, but I am just going to go through a few things. Just to remind us all, we do have Discord there. So Discord is really great for arranging social, food, collaborations, hackathons, you know, whatever you want to do on there for the evenings. Please make use of it, or, you know, you could simply turn and talk to each other from the great zombie apocalypse teams that you've been building tonight. You're welcome. But other than that, we're going to just see if there's a few more people coming in. The next session is really going to be about networking and storage. We're going to buckle in e te whānau because we have to get through 4 talks. The doors will be locked. No, they will not be. But I did pre-warn you to go to it. So this is your warning. But I think we might as well just crack into it because we're going to, I'm sure we'll lose a few minutes with a few questions and whatnot, and I want to make sure that we give our speakers the mana that they deserve for their talks today. So our next talk is Building Storage Systems with SPDK and Rust by Nick Humphries. So last May we started with 0 lines of code, and today they've built a fully S3 compatible object storage system powered by SPDK. Exaba runs everywhere from Raspberry Pi to exabyte scale clusters. This talk shares why they chose Rust, how they tackled SPDK integration, and the lessons from building memory-safe, high-performance storage. So let's give Nick a round of applause, and let's welcome him to the stage. Okay, good. Is that on?
Test 1, 2.
It might just need to be turned on.
How's everyone doing? What an awesome set of talks this morning. It's pretty cool to see the range of technology from embedded all the way through to the testing side. So I've thoroughly enjoyed all of the talks so far. Hopefully you're still awake. It's getting to the late end of the evening. So I'm going to talk to you about how at Exaba we are building storage systems with SPDK and Rust. I'll talk to you about the architecture that we're taking, how we can run the same code on a Raspberry Pi for high-performance storage, all the way through up to exabyte scale clusters. I'll take you through some of the high-level components, and I think that we've got a pretty unique story as a company. We started about 14 months ago, so we've had the joys of starting from scratch, diving straight into Rust as a team. And even our CEO is programming, so everyone's a coder, everyone is contributing to the product. So a little bit about myself. So my background, if I get it right. I grew up in the South Island. Even though I have a love for the outdoors, I taught myself how to code and spent a lot of time inside on the computer as well. I started a software development agency while I was at university, and then luckily last year, Stu, our CTO, approached me and was like, hey, I'm thinking about doing this thing with object storage. Why don't you join forces with us and come along on the journey? And so that's where my Rust experience really started. Before that, I'd been playing around with Rust a little bit in the embedded space, actually. I just got really excited about being able to build a product in Rust. So joined forces, merged the company in, and now we are on this journey to build high-performance storage. So our mission, we want to build the most reliable, simple object storage designed for service providers and enterprises with the ability to scale up, down, and out. And basically, in a nutshell, we want to enable sovereign data storage. So sovereign means a lot of different things to a lot of different people, but what that means to us is that you can buy your own hardware, install some software that no license is going to be revoked and it stops working, and you can just continue to run that indefinitely, and it's your data, you own it, you can walk around it, it's not going anywhere that you don't want it to go. So what is object storage? Not everyone is across object storage, so I'll break it down a little bit. There's essentially three main categories of storage. You get your block storage, your file storage, and your object storage. Most people will be familiar with file storage. That's what you have on your Windows or Mac computers. That's your NFS. Your block storage is essentially your raw hard drive. So you plug a hard drive in, it provides you a block device, and you can then put a file system on top of that. Or alternatively, if you put a lot of block devices together, you can get object storage. And the reason why object storage is growing rapidly and really taking over the large-scale data market is because it's high performance, it has an unmatched security, it has built-in immutability, so you're not at risk of traditional ransomware. You can do lifecycle rules, so you can say, I only want to hold on to this file for 60 days, and it automatically deletes itself after 60. And it has tiering support as well, so you can store data you're frequently accessing on high-performance NVMe, or you can put your archive backups onto tape. Interestingly enough, it was also the first of the two services that AWS released as well, alongside EC2, so it was EC2 and S3. And now S3 has developed into an industry standard API for object storage. So there's a number of object storage solutions out there, and they all support S3. Some of the different use cases for object storage. Admittedly, ChatGPT did not want to only mention web content once, so ignore that down the bottom. But the rest of these are completely valid. Maybe you say web video versus web image, but it can be used for almost anything, and where it really excels is where you've got a large number of files, and typically if you're doing a lot of transactions or you're needing it organized in a global namespace aspect. So if you've got web content, you don't want any kind of duplicated file names just because you're going to a different server. You just want to say, hey, this is the file. There's nothing else that you're going to get if you point to a different IP address. So why Rust? For us, because we're starting new, we did have the choice. We obviously looked at a number of different options. There's one more there. But these were really some of the top reasons. It's memory safe without garbage collection. A lot of the alternatives in object storage space are built in Go. However, with the garbage collector, you can get unpredictable performance and not consistent performance. Fearless concurrency with some limitations. Multiple targets, so we wanted our object storage to be able to run everywhere. So x86, ARM, power, and we wanted to be able to get C performance with modern tooling. So a little bit of history on our team. We were born out of another company that essentially was specializing building a high-performance hardware full-stack storage solution, and that was in C++. And so by starting afresh, we kind of reevaluated and we're looking at, well, how can we detach ourselves from specific hardware and deploy a solution that will work across multiple different targets. And Rust was really the only obvious solution there with being able to support multiple targets much more easily than in C++. And the last piece there, sorry, the animations are painfully slow, it is stumbling me. Faster refactors and fewer Heisenbergs. So what I mean by that is if you are refactoring your code, you can basically change a whole bunch of things and the system will just work again because the compiler will typically pick up on if you really screwed something up. And so you get much more predictable refactors throughout your development. And that's really important for us as a startup as we're constantly seeing a performance bug here, rewrite that entire piece. Oh, sweet, it's working again. Move fast, there we go. Where we started, 0 lines of code, goal of a S3 compatible API, small team of storage experts, and over 50 petabytes of storage. So as part of that previous company, we acquired a lot of hardware, and we have now set this up in a data center, and so we've got about 50 petabytes just to play with for testing. We're not a cloud service provider or anything. We don't sell any services online, so this is just for our internal testing purposes. And it's pretty fun spinning up a machine and just seeing petabytes of storage. I found that quite entertaining the first time I saw that. Running everywhere is a key part for us. So we ship a Docker container that can run the entire storage system, or we can install it directly as a binary on a number of nodes and set up an exabyte scale cluster. It's the same code base, supports NVMe, hard drive, and eventually tape, with some exceptions on specific tape modes right now. And we've tested support for x86 and ARM, and we're currently testing on PowerPC as well, albeit will take a little bit more work to get that refined nicely. The only kind of hardware constraints that we have is we expect some kind of fast NVMe and resilient to write for the metadata drives. As long as you have that, you get really good performance out of it. So SPDK, the engine room of the storage engine. It is built in C++ and is maintained by the community, specifically some companies such as Hitachi and Intel. There's many more contributors as well, so I don't want to discount anyone, especially in just free community members that are supporting SPDK. It runs in the user space and it uses a polled I/O approach, which provides you very low latency and very high performance. It's essentially what drives most high-performance storage systems to date. Now, the way that we were using it is that we're basically doing Rust wrappers and FE5 bindings to integrate with this library. So that comes with its own sets of challenges. One of the biggest challenges was bindings. So Rust enforces strict memory safety, as we all know. And this clashed with some of SPDK's packed structs and bit fields. And so we actually ended up, for the bindings that were generated, having to use some block lists and manually by hand setting up some of those bindings. SPDK is also not plug and play. It expects you to work within its architecture and you need to follow its guidelines to a T. This doesn't map nicely to Rust's async model, and so there's quite a steep learning curve in getting the two different behaviors to work nicely together. The setup target, so the setup is also non-trivial. So when you're trying to set up NVMe over Fabric's targets, it involves a lot of steps, and small tuning changes make a significant impact on the overall performance. So you really need to have a good understanding of what you're doing and be very methodical about the changes and parameters that you're setting. The threads need a lot of care. So SPDK likes to pin its threads to core 0, but just by default, and you have to make sure that runtime threads avoid clashing with SPDK's pinned cores. Otherwise, you can kind of freeze the entire system and it just comes to a halt. And finally, the packaging is quite painful. So SPDK can generate CPU-specific binaries, so you quite often end up having to compile on the target that you want to run it on. So being Rust, nicely compiling everywhere, it's not too much of a pain, but it does mean that you can't really easily ship pre-compiled binaries. So on the architecture of the solution, in a nutshell, we can break it down to C nodes and D nodes. C nodes meaning compute and D meaning data. The C nodes provide the points to connect into the storage solution. So each of these typically will have its own IP address, and as an API consumer, like using an S3 SDK, you can connect to any one of those C nodes and receive data from any of the D nodes. It's horizontally scalable. We built a DNS service to go along with it built into the system. And for context, if you query S3, AWS's S3 on the s3.aws.com, I think is the domain, you'll get 17,000 different IP addresses if you iterate it fast enough, or for long enough, I should say. So our CTO decided to figure that out, and for about a week he was just DNS query after DNS query, just sitting there trying to figure out how big it was. So there's some other components of this that we won't dive into in detail today, such as like the key management system, which as an aside, because Rust is cool, we've been able to support post-quantum encryption out of the box, which is pretty novel. Yeah, a lot of different components that go into it. So on the DNS resolver side, in order for you to have an API or SDK that goes and can actually get the full performance out of your storage cluster, you need to be able to make sure you're talking to multiple C nodes. If you're uploading a terabyte size file, you're not going to do that in a single upload. You're going to do multi-part upload, and if you want to max out your bandwidth, you need to target multiple different IP addresses. Quite often the SDKs out of the box, which we'll go into a little bit later, don't support multiple IP targets as well. So they'll just kind of point to one and just try the multi-part against that one node. Basically to support that, we built our own DNS resolver. So you point the name servers to the domain name that your cluster's running on, and the service will pick up the rest. And the really cool thing is about building a DNS service in Rust is that it only took 2 weeks. So a full DNS server, kind of Bob's your uncle, it's done. Doesn't take much work. Also helps when you have an amazing team that can smash things out like that as well. Even cooler thing, I found this, I've already started running, or tried running it at home, is that all the DNS records are stored in object storage as well. So we're kind of already starting to build on our own stack as well. Using S3 and Rust, yeah, so the AWS SDKs are not always performant. There was the issue where I was talking about how it would only go to one IP address in your cluster rather than rotating through and doing new DNS queries each part. Doesn't easily support simple multi-node uploads. And retry and back off for multi-part uploads it wasn't really built in the SDK level. It's quite basic. It just gives you the direct API layer. So in theme with everything that we do at Exaba, we built our own. And so we built a mini S3 SDK that we use for all of the integrations. Onto performance. So this is a screenshot of some of our lovely performance graphs that exist in our user interface, which I'll do a quick run through later. It's pretty cool. On a hard drive-based system, we got 28 gigabits per second read and 55 gigabit per second write. And so that's across 6 nodes. I think this cluster has 8 petabytes of storage attached, 600 hard drives. And intentionally, the hard drives are of varying quality. Some of them are completely dead. Some of them are quite old. They've been running for 5 years. Some of them are new. By having different hard drives in there, we're getting really real-world tests rather than just on brand new equipment. Nothing ever fails. It's fine. So how did we get to that performance? This is where we get into the nuts and bolts a little bit more. Generally speaking, Tokyo can be very hard to debug. GDB shows threads that are stuck in Tokyo, but not in user code. And the console, Tokyo console is not super useful for deadlocks. It's supposed to give you visibility into your async tasks, but it's really not much of an issue when you've built your own deadlock, and it can be very time-consuming to diagnose these problems. Now, on the performance issues on big servers, the Tokyo runtime on many core machines can end up causing a lot of waits. And instead of scaling cleanly, we found that the runtime itself became the bottleneck in our performance. So Tokyo was causing the bottleneck. Flame graphs showed that the CPU time wasted on lock contention inside Tokyo itself was majority of the time that was the majority of the performance issues in our code. And this meant that we really weren't getting the full benefit of the hardware that we were expecting. So our workload is a mix of async disk I/O with heavy CPU work for things like checksums, erasure coding, and encryption. The debugging of this is relatively tricky because you can get lots of different system deadlocks. Now with Tokyo's guidance, anything that's blocking for 10 to 100 microseconds, you should move it to a separate thread. But there are practical problems with that, where you start to encounter async copies and with async I/O. So our solution, we ended up switching exclusively to multiple current thread runtimes. This reduced a lot of the contention. It does require a little bit more management, but it did give us predictable performance and it better aligned with heavy CPU parts of the storage pipeline. Actually, one thing I'll mention more on that one there is that this is quite a common pattern as well. If you look at Cloudflare's Pangora as well, they use the same kind of approach there for performance. And yes, now the cool part. We want to make sure that our storage solution is bulletproof. We want to make sure that you can throw as bad kit at it as possible and it will still work. And so one of the testing approaches is that we are attempting to make a very large USB farm. On this USB farm, there is currently, I believe, I don't know if this is an old photo, but I think there's about 90 USBs that we've got that we can cluster together with the software. And we got 1 gigabit per second right, which is crazy. Now, these USBs vary in age. Some of them are over 20 years old. And USBs are actually a really good test target, because I'm sure if everyone remembers, you pick up a USB, it said 64 gigs, you plug it in, it says 16, and you're like, okay, well, I guess that's it then. Some of them have failed partition tables, some of them are partially corrupted. You name it, they'll lie about everything because the USB standard is horrible. And so it's a really good test approach. It means you'll encounter almost every single possible issue with storage media from USBs. Yeah. Wait, all of those empty slots, if you've got spare USBs, send them our way. We'd love to populate the entire thing. Cool. So on one of the integrations, so obviously object storage is really cool, but just having lots of storage by itself obviously does nothing. You want to put things on it. That's what it's for. One of the integrations that we did early on, or that I did early on, was looking at NX Witness. So for those in the security or surveillance space, NX Witness is used for camera installs. You can connect most cameras to it, and it can support kind of 1,000 camera deployments as well. It can scale up to quite a large deployment. Now, for this integration, they provide a C++ SDK with purely C types for the bindings. And through the experience that I had, I tried CXX and AutoCXX and a bunch of different techniques to auto-generate the bindings, and I found out that it's probably just easier in this instance to manually write these bindings. And there's a few lessons that I learned to make it a lot easier to scale this, because I really wanted to forget about the NX Witness part. I just wanted to get the calls into Rust and just focus on my Rust code. So with those few different paths explored, I ended up on roughly this model. Now, this is simplified code for the sake of fitting it on the slide. But there's a few principles that you can kind of put in here. One of them is to keep the unsafe part of the code as small as possible. So just keep that. Essentially, the way I like to describe it is it's a tiny trampoline between the two different systems. And so if you keep that unsafe code small, you can keep it predictable and you can understand what's happening. And the other thing is to make sure that the panics never cross the boundary. In this instance anyway, this is especially important when you don't actually have any control over the C++ side. It's just it is what you're given, and if you crash, the entire surveillance system crashes. So you really don't want to do that. So you want to make sure that, hey, you just kind of let things continue on. It'll record to its backup media if it's not recording to yours, and kind of not gracefully handle those issues. Cool, and then one of the other ways that we're looking, if you don't want to pay a license per camera with NX Witness, we're saying, okay, well, why don't we just do it purely in Rust? So we have a small partnership with the University of Waikato to bring a bunch of students on board and give them various different Rust projects. And one of those projects is RTSP video recording in Rust. And so to get the students started, I spun together, it literally only took an hour, which is super cool, a proof of concept. It integrates with GStreamer, which is a library. It's basically either GStreamer or FFmpeg for those who are familiar. Those are the two options. And it was very performant on just this computer just here. I was able to handle 50 camera streams recording to object storage just on an M1 MacBook Pro. So that was pretty impressive. It used a smaller bit of local cache, sending all the data to object storage. Cool. I'll try to do a quick local demo. Hopefully this works smoothly. Where are we? All right. That is the wrong window. Problem with dark mode, everything looks the same. All right. So I am going to start our Docker container, if Docker's running. Which will take one moment. Yeah. Come on. All right, give me one moment. I am. Can you make the font size larger? Sure thing. Yep. All right. All right, there we go. So we are spinning up the Docker container. Now this spins up all the various different components. You can see the key management system status sitting in there. And so we will jump over to a web console. So what I'm going to show you is essentially spinning up a new cluster. So there's now the user interface, we use Flutter. We want to ship it to multiple different points, so that was also a nice cross-platform piece. And once we get this going, the joys of live demos. Here I was thinking that doing it locally would be more reliable than online. All right.
Sorry, quickly, is it trying to
Yeah.
use your own hard drive for the storage for the S3 medium, or is it connecting to something?
Yes, it is. Yeah. So it's in this Docker example, it's just using the Docker volume. It's fully local. In a clustered example, it just uses the hard drives that are attached to those nodes. The question was, is it trying to use my own hard drive for it, or is it trying to connect externally or use some external media? So it's using my own hard drive here. All right. So what we're going to do, I'm just doing some troubleshooting on the other screen. Otherwise, we might skip this part. No, I don't, surprisingly. Right, we'll skip that part, and if you want a demo, I can happily do this after it, and I can guarantee you as soon as I walk off the stage, it'll work. And so I'll be in the other room anyway, anytime, and tomorrow morning as well, so feel free to pop by. Cool, all right, so summing up, we think Rust is awesome. We believe that Tokyo, it is a very good async runtime, but it can be complicated and high performance. So you just need to make sure that you understand the ins and outs, pros and cons, and there's always compromises that you're going to have to make when you're trying to squeeze out every inch of performance. And when the animation catches up, thank you guys. And you can move really quickly with Rust. So the ability for us to, within the space of 14 months, build out a S3 compatible storage where we've got, we're heading for general availability at the end of this year, within the space of, say, a year and a half, build that from scratch is pretty unheard of. If we were trying to do something similar in other languages, it would just take probably twice as long, if not more. It also has allowed us to essentially get people across different parts of the system more easily as well. So I am not a super experienced Rust programmer. There's other people on the team that are incredible, and I've still been able to contribute to the code base. So I built the Microsoft 365 sync, and I was able to understand other people's code a lot more easily than when I've dived into C++ code bases, or when I'm a PHP man, don't hurt me, and I've contributed to the PHP source. It's been really complicated. It's been a really steep learning curve, whereas I'd argue that Rust's learning curve is in the language, not in the code base. So it's very beneficial. And there's nothing you can't do in Rust. So we're basically, every problem we're hitting, we're like, for the DNS example, a lot of other solution providers are just throwing Nginx in front of their solution and saying, oh, just use this load balancer. We're saying, no, we'll do it in Rust, and we'll use Rust crates, and we'll do it full stack Rust, which is pretty cool. Now, as I mentioned, we have a partnership with the University of Waikato. It's pretty cool to have this partnership. So our office is actually based in a co-working space on the university campus. Currently, we have a team of about 25 to 30. One of our student interns is actually here today, which is really cool. And we have about 30 masters and undergrad students working in Rust on various Rust projects. So trying to grow that community, trying to get more people involved in Rust at a younger age. And it really surprised me how, so these students, they have the choice of projects from various different companies, and all of the Rust projects were chosen, and all of the Flutter projects and other ones were not. And so it was really cool to see the engagement on people wanting to get into Rust. Some of the projects that we're doing is MP4 ad injection, so that's server-side ad injection, so simple ad blockers can't get around the ads. Sorry guys that love ad blockers. Multi-tenanted serverless compute backed by Docker, so this is the concept where you essentially have not using Kubernetes, just like a little micro kernel essentially that manages your Docker containers and can use them as functions. Multi-tenanted VM management backed by Proxmox, which would then bubble up to the Docker layer. And so these guys have been doing awesome work where they have basically connected to all the different Proxmox APIs and in Rust, and are now doing orchestration of Proxmox in Rust. Pretty cool. And the one I've already gone through, the RTSP video streaming. Now, if you'd like to help me debug the issue that I hit, we would love to invite you to a private beta. RustForge only is the only development community that we're really going out to. So we're in private beta at the moment with limited access to our to our kind of latest releases, and feel free to flick me an email with your interest, and we'd love your feedback. Essentially what we're looking for from developers is understanding, hey, does it work with the other tools that are out there? Does it connect to your systems? A lot of applications are built on object storage. Does it just work out of the box, or are we missing something? The talks earlier about expected bugs and APIs, the AWS standard has bugs in it. There's things that we disagree with, and we're like, well, do we need to implement that bug or not? And then we look at the other providers, and they've all made different decisions. And so there's all of these considerations that we'd love your feedback on, and it would be very beneficial. So thank you very much, everyone. Thank you, RustForge. Follow us on LinkedIn for updates. That's the best place for updates. And thank you for having me.
Thank you so much, Nick. And is your intern here? Do they want to?
Christian?
Yay.
Hey.
Cool. We have a mic, so we're going to go to the first question, and then we might be able to grab a couple more.
Try somewhere up here.
Oh, there seems like there's quite a few questions.
Let's start down here.
Let's just...
Hello. Yep. So you said you're having Tokyo was complex for performance. Did you try using any other async runtimes, or try writing your own?
Writing our own, I believe it was thought about, not explored in detail. Other runtimes were looked at, but no, the conclusion was that Tokyo does provide the tools that we need to get performance. It was just about making sure you really understand the trade-offs in between the different options that you implement.
Cool. Next question.
SPDK, C++, Rust when?
Clarification? Will there be Rust in SPDK? Probably not. I mean, if Intel and Hitachi make that decision, and the other large corporate sponsors of the project, yes, we would obviously love that. It's too big of a project for us to take up and migrate, essentially. So there's a very large number of tools and CPU-specific optimizations, and it would be very complicated to do that off the bat. But, I mean, hey, in the Adobe talk, very good example of saying, hey, just do new code in Rust, and you get good benefits out of it.
Cool. Last question.
Hey there. Yeah, with your multi-compute clusters, how are you, presumably there's a lot of coordination you have to do between those nodes. Like, yeah, how do you go about that? And like, if you add new nodes, is that possible? And yeah, I don't know.
Yeah, that's actually where a huge amount of complexity in the solution goes into, is adding nodes, removing nodes, adding drives, removing drives, and being able to essentially have evergreen hardware. So you just have one cluster and you just slowly rotate the hardware out. It essentially requires consensus algorithms. You have to deal with network splits, other issues like that, and so there is a lot of edge cases that we look to deal with there. Hence why you kind of just have to start with 3 nodes and go up from there. You can do single node with no redundancy, but 2 nodes is basically just mirroring. So yeah, there's a whole lot of considerations and implementation and specific configuration that goes into that.
Awesome. Big round of applause. And I think Nick wins best shoes too. I might be biased, I'm a bit of a yellow fan. All right. Our next talk is Mixed Reality Network Introspection by Dr. Meghan Clark, who is a principal scientist, IoT systems at Resideo Technologies, Inc. She has worked for over a decade on improving interactions with the built environment. Previously, she was a postdoctorate fellow at the University of California, Berkeley, where she worked on novel methods for capturing and visualizing wireless network traffic. Before that, she completed her PhD in computer science from UC Berkeley with a focus on smart buildings. She's an amateur radio enthusiast and would love to talk to us all about IoT and WASM. Hopefully I said that right. Come on up. Give her a warm round of applause. And just while you're plugging out, it was very close, Nick, to an interpretive dance from you while your demo wasn't working. but you are saved by the bell. Ta-da! Cool. Okay, and this is your mic, so all good to go.
Test. Before I get started, actually, I'd like to thank the organizers putting together this great event. It's been fabulous. So thanks so much to Tim and Amber and Tosh and Ben and the rest of the folks at Streamliner providing the AV. Let's give them a round of applause. What does Wi-Fi look like? Some researchers asked regular home residents to draw what they thought their home network looked like. And they drew a picture like this. It's a house with some furniture and crazy energy waves just floating around in the air. Now, if you asked the self-appointed sysadmin of the home the same question, they drew this. This will look familiar, I think, to a lot of us here in this room. And we might think that this is better. But even the network tools that we have as experts still aren't that great for helping us understand the wireless environment. These tools have high cognitive load. You have to sit with them and really dig in to understand what you're seeing. You have to usually have a suspicion for something that you're already kind of looking for in order to find it. They're not for real-time insights. They're not for discovering things that are surprising to you. And they often don't capture the spatial component, which is really important for wireless networking. And it's kind of a shame because humans are really good at spatial reasoning. The human visual cortex is a marvel of evolution. We can be completely focused on something else, and our background processing on colors and movement and patterns can bring something from the background into the foreground of our attention with lightning speed. That lets us dodge predators and spot food, everything that you need for survival in the jungle. But now, we're in the wireless jungle, and we're blind. Wireless networking is still pretty new. The prevalence of it in our homes and on our phones all happened in the last several decades, and our tools are behind. If we could build artificial eyes to help us see the invisible light blinking out of the devices all around us, in this room even, then we could hook into our visual and spatial processing superpowers. So hello, my name is Meghan Clark, and I'm a recovering academic. I did my PhD and postdoc at UC Berkeley in an IoT systems research group called Lab 11. In 2019, Lab 11 had a problem. This was our research space, or about half of it, with the other half behind the camera. This being an IoT lab, I installed smart lights for everyone, so each desk had its own Wi-Fi bulb. A colleague of mine, Neil Jackson, was at the time developing a 10-year battery life indoor environmental sensor. So these measured temperature, humidity, light, and motion. And to communicate, they used Thread, a low-power mesh networking protocol. And each desk got one of these sensors. Because Thread is a mesh, we also had 3 mesh routers in the room. One of those was a border router that could forward traffic from the mesh out to the internet, and the sensors used that to send their data up to an AWS server, which had an MQTT broker on it, which is a publish-subscribe system if you're not familiar with it, but it's very common in use in IoT. To show off his sensors, Neil also made a lighting control application. It ran on a Raspberry Pi behind the camera here. And if your sensor detected motion, it would turn on the light for your desk, and it would use the brightness data to keep the light at a targeted brightness level. So if it's sunny out and sunny at your desk, it would actually dim the lights and turn it off because you don't need it. And if it was dark, it would make the light brighter. The problem was that to debug all of this, Neil didn't even have the nice tools that I mentioned before. He had terminal printouts of the messages that made it all the way up to AWS, and he had waving his hand in front of the sensors and seeing what happened. There are a lot of things that can go wrong here, and a lot of interactions between the physical space and the wireless network that are all invisible. So I thought, wouldn't it be better if you could see the packets? So I made a tool that's like Wireshark, but in mixed reality, and I called it XR Shark. So this is going to be a recording that I took off of a VR headset that I was wearing running XR Shark. So this is me putting my hand over one of the sensors, and you can see it pop off a bunch of packets that go through the mesh and go up to AWS in the cloud. And here you can see there'll be fewer packets, and that's because there's a refractory period in order to save battery. Probably don't need the same stuff triggering over and over. Here's the lighting controller at work. I'm about to dim the lights from the commercial app, so it comes down through the cloud. And here we go. And you'll see the sensors report the changes up to the cloud. And you'll see the lighting controller actually using the local UDP protocol to bring the lights back up to the brightness. So you can see it's not coming through the cloud now, it's coming over the local network. You saw that I controlled the lights through a phone app. So I wanted to track the location of the phone as I moved around the space. So in this, you're seeing me open up the app again to control the lights. It's going to send out a ton of packets because it's doing a discovery process to find all the lights and get all the state of all of the lights. So augmented reality is super great and everything. But what if you aren't there in person? Or what if you want to see historical activity that doesn't line up with what's going on in the space at that moment? I made a VR mode. This lets you see the space from anywhere, anytime. And I could view this from my home, for example. VR also lets you travel up to the cloud. So I made the cloud. I love visual puns. So there's an actual plane where all of the off-network hosts get placed and where they live. And as a child, thank you. So as a child of the 80s, you can see my Tron aesthetic coming through. So how do I do all of this? The visualization is a Unity application written in C#, which runs on a VR gaming laptop connected to an HTC Vive Pro. Remember, again, this was in 2019. Nowadays, it would be the Oculus for sure. The Vive Pro has front-facing cameras for allowing camera pass-through so that you don't bump into things in the real world. But you can turn them on intentionally on purpose, which gives you kind of a janky augmented reality, where the VR is actually overlaid on top of the camera feed. To get the packet information, I needed to instrument the Wi-Fi network. Wi-Fi is a star network, so it's pretty nice. You can instrument the router, and you can get everything on the local network and also that goes out to the internet. So I installed OpenWRT on the router and installed TCP dump on it. And you can take a Raspberry Pi, plug it in over Ethernet, make sure it ignored all the traffic between it and the router, and then took all the packet information off of TCP dump and just streamed it onto that Pi, which would pull the relevant data out and push little messages out to MQTT, which were consumed by the app. Now, this little processor here at the time was written in Go. But if I did this today, I would definitely write that in Rust because it's one of these tight inner loop kind of things that's processing as fast as possible. Go has a garbage collector. So even though this was a tiny program, it's also a tiny rewrite, and I would definitely do that in Rust now. Thread, instrumenting the thread network was much more difficult because it's a mesh. There isn't a single point that you can get and see everything. So I talked with Neil about this. How do we want to do this? We could try to do the same thing where the router, each router ends up reporting out to some MQTT broker every packet that goes through it. But this is a low power network. We don't really want to saturate this network by doubling or increasing all of the traffic that flows through it. And so we kind of cheated a little bit. All the traffic we happened to know for this application was going up to the cloud. And so we modified the routers to send their routing tables up to the cloud as well. And we also modified the sensors to send their first hop router up to the cloud. And from that, we could construct a picture of the mesh topology at any given time. And when we receive messages up in the cloud, we could back out what path it must have taken through the mesh to get there. And that was a nice trade-off between kind of minimizing the impact on the low-power network while still being able to capture all the information. Seen another way here, the thread routers send their thread routing info. The sensors also send their first hop routing info, and that lets us build the mesh topology out in the cloud So then every time we receive a data message from a sensor, we can actually generate these sort of synthetic packets that show each link layer hop through the mesh, and that's actually what the visualizer is showing. These were written in Python. Today, I would definitely write them in Rust for the performance. For the tracking, I used an ultra-wideband system for localization. So this is one of the first eval kits that came out commercially for ultra-wideband localization. It had anchors that you placed around the room and a tag that you could put on assets you wanted to track. And they provide a Raspberry Pi image that you can put on and put one of their modules on. And that Raspberry Pi listens to all of the anchor devices and does the trilateration. Seen visually, you put your anchors around the room, you've got your Pi in there that's listening to the ultra-wideband network, and when a device comes in, the Pi uses the distance measurements from everything and the coordinates that you did have to manually measure. There were a lot of laser rangefinders and people holding things up and to measure these. And then the Pi would push the calculated coordinates out to the visualization. You may have noticed that I did not use Rust in this project. This is a Rust conference. However, I use Rust at work. I love it. It's fantastic. And if I were to do this project today, there are a number of places where I would use Rust. So as I mentioned, I would use it in the processing pipelines. But also, I would use Rust in embedded systems. So at the time that I was making XR-Shark, in that same research group, there were folks working on Talk OS, which is a secure multi-tenant embedded system, operating system. And that's actually my first exposure to Rust, was them swearing about lifetimes. It's pretty hardcore. It's in big name laptops out today where it provides hardware root of trust. It has a very strong security stance. If this interests you, you should totally check out the Talk Foundation. They love contributions. There's also Embassy, which is a fantastic, very convenient, easy to use application development framework for putting onto embedded systems. It supports the ESP devices, and you guys all got one in your welcome packets. Sorry, folks online, you should totally come next year. And also, we had some fabulous talks talking about bare metal embedded systems development. There's a Rust embedded group, and also there's a book that's being worked on that's in progress. So you guys can get in on the ground floor. Again, if this interests you, get involved, reach out, and make those connections. I know there's folks here as well that work on this stuff. So lots of opportunities if you like embedded. For AR, VR, we also had a workshop on Bevy this week. Bevy has a mod out there that provides support for OpenXR, which is an API that each of the main VR headsets understands. And so you can find these demos on YouTube showing it working. So this is really exciting given the performance of Rust versus something like C#. I think this is a really exciting direction. There's also a similar kind of standard to OpenXR that is called WebXR that runs in the browser. So you can go to links inside of your headsets and you can actually load augmented reality or virtual reality experiences that way. And so there's, I think, some very exciting opportunities there if you want to use Rust inside of WASM, inside of the browser, inside of a VR headset. So if you've got this system working, what are some of the cool things that you can do with it? So one of the first things that happened, obviously, is we put this headset on, and I watched someone walk down the hallway in the middle here, and you could see each of the motion sensors pop off its packets as someone walked by, which just gives you a great intuition for how quickly these things are responding, what their field of view is, because not every one of them is responding. Some of the things see and some don't. That's something where, without the headset, you don't see any of that at all, right? Because all the lights are already on, but here you can build that intuition. Additionally, Neil had been thinking about the lighting control application as one sensor and one light, but the first thing you immediately see is that when a single light is changing, it affects multiple of the sensors around it. So it's just one of these things where you get a higher fidelity picture of what's actually going on in your system. Another cool thing that happened is one day I came in and I put on the headset and the thread mesh was all messed up. there were sensors sending data to mesh routers across the room, which worked fine, but it was just suboptimal and very weird that it was doing this. And it turned out there had been a power outage the night before. And when the power came back on, things rejoined at different times, and the thread mesh was again, suboptimal. And what we saw is that over the course of the day, we watched the mesh repair itself, where sensors actually figured out eventually, hey, oh, this router is actually better for me, so that's going to be my new first hop, which was great validation that Neil had implemented the mesh routing protocol correctly in firmware. Another cool story is I was giving a demo of this headset in lab, and an undergraduate walked by and was looking at the picture on the screen showing what I was seeing, and she was like, hey, what is that weird kind of regular ping-ponging between your laptop and the cloud? And we looked at the IP address, and we looked at what was talking to it, and it turned out it was Slack. It was Slack talking up to the cloud. And we looked it up online, and it turned out, yes, Slack uses AWS. And what I like about that story is that this is someone with no technical background, right, who is just using this ability that we have to spot patterns and going, hey, and then being curious about it and digging in. Let's see. One time I was working on the headset, and I noticed in the background that my laptop just started sending out that there was this huge stream that opened up, and that no one was working on that laptop, and it wasn't doing anything, and I thought that was really weird. And it turns out I went over to shut the laptop down for the day, and it said, Windows Update, ready for installation. And I was like, I think I know what that was. A big thing for me is IoT device trust. A lot of people don't like IoT. They think it's spying on them. And I think this is a really big deal, where one of the things that you can see is how often these things are talking to the cloud. So here you can see me, control the lights through the app, and so there's lots of traffic here. But even in between that, you can see when the cloud is deciding to kind of check in on each light and resync with it. You see these kind of one-off things there. And one of the things I noticed is that after a big change like this, the cloud will kind of more frequently check in, and then it stops after a while once things have kind of stabilized. And I think that that's very powerful to see when things are communicating with the cloud. And I also had an Echo Dot in the space as well. And believe me, I looked at it and was like, what is it doing? And it turned out that despite its reputation, it did not send traffic unless you said something to it, and then it sent some packets out. And I think that that changed my impression of the Echo Dot greatly. And I think that's something that would be really important for helping regular people understand IoT activity in their house. This one was this is my last story here, but this was a big deal for me. I was load testing the visualization, and I sat in my office on campus, and I started up Netflix. First of all, it's kind of weird. Netflix had two different streams, but also it went out to this IP address, and I looked it up, and it turns out it belonged to Cal State, which is the community college system in California. And I was like, why is Netflix coming from Cal State? That's very weird. And it turns out that there's an entire piece of public infrastructure that I had no idea existed. So in the United States, there's actually 2 internet backbones that I know of. Maybe there's more. But there's one called Internet 2, which is a high-speed backbone that goes across the whole country that was meant to connect laboratories and research institutions. But they would basically just run this huge high-speed backbone thing and give you like a drop or 2 in your state and say, good luck getting to it, And so what California did was their research institutions all pulled together, they got funding, and they donate their resources, including IP block allocations, to a regional high-speed network that connects not only all the universities and the national labs, but it also connects K through 12 education, all public libraries. I had no idea this existed, right? And then I could go and see it. And that's really important for infrastructure that needs public funding, right? If this is something that needs to go to the voters, if it's invisible to the voters, then they can't tell it's there, right? Wireless is not the only thing that's invisible. And several years ago, we had huge policy discussions about net neutrality across the country. I think that discussion would have made a lot more sense to people if they visually saw all of their traffic passing through their ISP every time they connected to something on the internet. So this has all been link layer and network layer visualization. What about phi? What about radio waves? So these are not my projects, but these are some of my favorite projects that I have ever seen online. This is a project where someone took an ESP8266 and they used the LED, the RGB LED, to visualize the Wi-Fi signal strength. They took a camera, made it really blurry, and pointed it at the floor, and they took the little device and they moved it back and forth across the floor and did a long exposure picture. And one of the things that they found was really interesting is that blue is the high signal strength area, but there's also these weird kind of nulls or areas of low signal strength, and they're persistent. It's not a fluke. Every time they passed back and forth, it was still there. And they were like, okay, let's get a better picture of what's going on. So they stuck the little device on a CNC mill, which can kind of raster back and forth. And they did this in a meter by meter square where they did a row per centimeter. So they just went back and forth and back and forth. And they got this picture. So this is a 1 meter by 1 meter picture of Wi-Fi, which is crazy. I would not have expected it to look like this. But if you think about it, Wi-Fi 2.4 gigahertz has a wavelength of about 12 centimeters. So your wave is like this. And that is big enough that you see patterns of constructive and destructive interference at a macro level. And so Wi-Fi 2.4 gigahertz has this cool honeycomb-like structure that you can see here. And in fact, they wanted to get the 3D picture of that, so they added the third dimension. And here's what that looks like. So this is a 1/3 of a meter by 1/3 of a meter. If you go to this link, the Voxeltastic link, it gives you a little browser thing where you can actually rotate the model and take a look at it and change the visualization. So when I asked the question, what does Wi-Fi look like? Now you all know this is what it looks like. My last favorite project ever is a Canadian hackerspace that used principles of radio astronomy to build a gimbaled radio that they could point around and again raster back and forth to build up a picture over time of what Wi-Fi looked like. And this is what it looked like in their hackerspace. So up top you can see the picture of their space, and down below that's what Wi-Fi looks like again. And again you see this honeycomb structure. You can see where their router is, and they also found routers that they had actually forgotten about, but you can see them. And if they took it outside, put it on a rooftop, pointed it at buildings, and you can see Wi-Fi, which is just so cool. And this isn't creepy because it's just like seeing light come out of buildings. The light, they're not looking in, it's more like the light is coming out, and they're just seeing what's there. Wi-Fi is public. Use your VPNs. So the way that they implemented this is they use GNU Radio, and they also use a bunch of scripts, Python scripts, to do the data processing. And it took forever to generate those pictures once they had collected the data. And so this is, if you were to replicate this project yourself, there's a lot of great things that you could do in Rust. So you can obviously replace all of the Python, which are much more high-speed processing script. And there's also, to replace GNU Radio, there's Rust Radio Crate. So closing thoughts, this wireless thing is all still pretty recent. We could have much more intuitive tools than what we have today. And that future can be built in Rust. I mentioned a number of open source projects that need contributions, especially around radio, embedded systems, and virtual reality. So pick one that sounds interesting and start playing around. My advisor did not know that when we asked for a virtual reality headset originally, we actually had no plans for it. This came after the fact, right? Sometimes you just have to start playing around with the latest technology, and sometimes something fun can lead to something transformative. So thank you.
All right, we have some time for a few quick questions. Anyone? Or you're so stunned that you can't speak right now?
You said obviously that you want to see like more widespread application of this kind of technology with like visual, looking at the packets and stuff. Is there any way you can think of to reasonably do that without having to add all of these kind of peripherals to your Wi-Fi network?
Yeah, that is the question, right? Because it requires all of this instrumentation into the network. It's possible that there are open source projects, potentially for some of the open source router firmware where we can add these things. And if you can do that and build, I think, compelling experiences on top of it, there's a good chance that they would then get sort of absorbed into some of the proprietary firmware. So that's one potential approach. I know that Thread, it sounds like, is getting combined into Wi-Fi 7. Someone correct me if that's wrong. But that means that Thread will also be included in routers, which is provides an interesting opportunity there as well. So you could maybe even do the low network instrumentation too.
Hello. Hi, up here. Thanks, really fascinating talk. I was wondering, could you conclude from that mesh structure of, honeycomb structure of the network, of the signal, that if I'm sitting there at my desk and my laptop is not getting a good signal, if I nudge it right 5 centimeters, things might get a lot better?
So yes, but most Wi-Fi implementations on devices use something called antenna diversity. So you have multiple antennas on there, and they end up just picking from whichever one is getting the best signal strength. So that's why you don't actually usually see the impacts of the honeycomb structure in practice. Though obviously our folks have had to think about it and deal with it.
Cool. Next
It's a good question.
Oh, what number's on the bottom?
3.
Number 3, Mike?
Probably a dumb question, but how do you know the physical position of each of the nodes so that you can actually render it in VR or AR?
That is a fabulous question. That's a great question. So for a lot of the stuff that was static, I manually measured it. It was painstaking, and I wouldn't recommend it. However, ultra-wideband has undergone a lot of improvements over time, and there's this possibility that if you had something like that, you could either have ultra-wideband chips in your devices and automatically do localization. Ultra-wideband, for example, is built into the phone right now. So I had a tag on a phone there. You don't need that anymore, right? It's built into the phone. It's potentially possible that you build it into other devices, but also it would also improve the, you wouldn't have to manually measure locations, right? If you can use ultra-wideband, you can say, hey, there's a thing here, and then it marks it that way. So you could definitely improve, I think, these days, that experience of setting up and configuring the room.
Awesome. We are going to give another round of applause. Thank you so much. Thank you for also breaking our equipment. Just beta testing, right? Just testing it out. Ka pai. A few reflections on that kōrero for me is, one, that our technology will always mimic our taiao in our environment. But also it would have been cool to have these headsets for when Kāinga Ora, who are our social housing provider, wanted to put sensors into homes of their tenants and to measure their temperature, humidity, and CO2, which with that kind of information, you can actually determine who's having sex, who's going to toilet, and every other thing that you do not want your landlord to know. And on that wonderful note, we're going to welcome our next talk, Land of the Long Fat Pipe, The Quest for Faster File Transfers, by Ross Younger. So Ross is a software engineer who cares about systems, reliability, and good tooling. A 25-year veteran of the tech industry, his work has kept telecoms systems powered, enhanced the security of major world banks, and kept emergency responders safe in life-threatening situations. Originally from Scotland, oh, me too, but not me personally, my grandfather, hence the Craig. Ross studied computer science at Cambridge and has been trying to keep up with the technology ever since. He now lives in Christchurch, New Zealand. When he is not busy with client projects or enjoying Rust, Ross likes to make things and take pictures, sorry. I obviously haven't had enough coffee. He has a side interest in communicating with people through broadcasting and video photography. So please welcome Ross to the stage. And then by the magic of the internet. And we're on the home stretch.
Ka pai. Awesome. Take it away, Ross.
Kia ora, Amber. Tēnā koutou katoa. How's everybody doing? I know this is a long stretch, so if anybody wants to take a moment to just get up and have a stretch, that's all good with me. So I would like to start by asking you a question. Oh, I do apologize. This is not showing on me or what I thought it should. Don't you love technology? I might need it to do some interpretive dance. Okay, question for you all. Who of you here have got fiber internet at home? Quite a lot of hands. So I'm guessing that's probably most or all the Kiwis. We are fortunate here in Aotearoa. And internationals probably varies on what's available where you are. But how many of you are making really good use of that fiber, really maxing out the bandwidth? A few hands. So that's the thing. So I had a little bandwidth problem which was affecting my work. I'm going to show you my solution, tell you a little bit about how I got there, and I've got some take-homes that I hope most of you who are already well into Rust will know, and if you're new to Rust, well, welcome, and hopefully they'll be useful to you. So this specific problem is point-to-point file transfer. I needed to move some multi-gigabyte files from a server in Europe to my home in Christchurch on the South Island. It's a long way. Ping time of 300, 320 milliseconds. Yes. I really am going to have to do an interpretive dance here. This is not behaving.
No pressure.
None at all. That is a bit more hopeful. Right. So, on a long file transfer, I normally use SCP, the secure copier. Absolute go-to tool. But on a really long transfer like this, it hurt. So I'm going to show you a screen record. 100 megabyte file. This particular one is coming from a data center in London to my home in Christchurch. I have gigabit fiber. Watch those meters. Up in the top right of the screen, that number that's ticking up slowly, 4.9 meg. It finishes 6.1 megs per second. That is the average speed of the transfer. About 50 megabits per second. But hang on a second. I have gigabit fiber. What is going on here? Why am I not getting anywhere near that gigabit? Okay. This is my tool. A few moments after the previous record, there it goes. Now do I have your attention? Now, that was just one sample, but I promise you these numbers are representative. I've done the same sort of test many, many times. I learned that the internet was really, really variable. Now, 100 megs, yeah, not a great test. Things don't get up to speed. So I did the same thing with a gigabyte. I'm not going to play you the video. Don't have time for that. But these numbers, again, absolutely typical. My tool is running about 5 times faster. Now, if you're quick with your mental arithmetic, you'll see this is still not a gigabit. My throughput, I'm running 300 megabit or so, maybe peaking a bit faster. It's not filling my line, but I am willing to believe at this point that I'm probably contention-bound somewhere else. So, this is a surprisingly simple problem, but it is subtle and complex. What it comes down to is TCP versus UDP. So I'm going to make sure we're all on the same page here. When you move data over the internet, at one level, you have a choice of 2 protocols to use, TCP or UDP. More or less, everything on the entire internet uses one or the other. Most websites, REST APIs, email, they're TCP. YouTube, Netflix, Zoom, other, if you like, real-time AV stuff, that tends to use UDP. So what's the difference? In essence, reliability. TCP gives you a reliable data stream. Your stream is intact. Your packets are guaranteed to be delivered once only in order. And it has congestion control. It tries to make good use of your bandwidth. When it detects congestion, it backs off. It responds to the conditions. It makes your life easier as a programmer if you can live with its complexity and its overhead, and that is the root of the problem. UDP, none of that complexity, but none of that guarantee. A very raw protocol, if you like, but very lightweight. Now, TCP was invented in the 1970s. It is not well tuned for modern high-speed connections. I found that on the internet, the available bandwidth, particularly on a long, long distance transfer, your bandwidth varies from moment to moment, from second to second, in a way that TCP really doesn't cope very well with. There have been some people who have done some good research. TCP doesn't perform so well if your pipe to the internet is really fat. It doesn't perform so well if your pipe to your destination is really long. Well, here in New Zealand, we have long, fat pipes to pretty much anywhere in the world that you would want to connect. We are right in that sour spot. So, obviously, we should move our data over UDP, right? But hang on, TCP gives me all these neat properties, and I don't want to give them up. I'd rather not re-implement them. I'm a lazy programmer, right? Well, there is an answer. Most of you probably haven't heard of Quick. I can promise you, you probably have used it. This is a protocol invented by a team at Google about 10 years ago. It's built into all modern web browsers. It's part of the HTTP3 stack. If the web server supports it, your browser will just seamlessly switch over to it. Great. So what is it really? Well, it is UDP-based. It's got the best properties of TCP, just a bit tweaked and retuned for the modern internet. It gives you that reliable data stream on top of a simple UDP stream. It's got some really interesting congestion control options. And it's got TLS because, hey, it was 2012 or so when they built this. Why wouldn't you build in TLS these days? Great. So how can I use Quick to transfer my files? Hang on a second. I don't really want to set up an HTTP3 server. It's not the most ergonomic. Like I said, I like SCP. I'm a command line kind of guy. So, engineer's hat on. What do I actually want to achieve here? I like the ergonomics of SCP, so I wanted a drop-in replacement for it, or something very close. Security was really important to me. I was working on a project where the firmware was client confidential. I cannot post that on an open web server, and I've got to encrypt it in transit. But it's trickier. So Quick uses TLS, it's baked into it. That's great for securing your data in transit, but how do you do the user authentication? Yeah, sure, you've got some mechanisms in HTTP that you can use, but that's not quite the same ergonomically. Right. I do not want, I realized, to write my own cryptography. I've worked in IT security, I know better than that. So it kind of follows, I don't want to implement user authentication directly, not if I can help it. But TLS, doesn't that imply using public key infrastructure, PKI? I don't want to mess with that. My home machine is behind a firewall. I don't want to expose my desktop to the internet just to be able to get a Let's Encrypt certificate. And I'd really like to minimize my opportunities to have to write a CVE, that's a public vulnerability disclosure, for my own project. I'm not asking for much, am I? Felt like I was backing myself into a corner, these conflicting requirements. Okay, stop, breathe. I imagined myself floating through the fluffy clouds of, well, the cloud. But the key insight here was the major pieces of the puzzle were right in front of me. They already existed. Quick has got the performance that I want. Doesn't have a ready-made user auth system in of itself. Security depends on X509 certificates, which appears to imply PKI. On the other hand, SSH is well known, absolutely battle-tested, secure, does the user authentication, plugs into your server very easily, but the file copy performance sucks. I want the best of both worlds. So, why not? Can I weld them together? So, my solution. First of all, what is an SSH session? Secure shell. You are running a program remotely. Traditionally, an interactive shell. Doesn't have to be. Whatever it is, its input and output are relayed back to you securely over a TCP channel. And that's about the long and the short of it. So, what QCP does first is it SSHs to your destination and runs QCP in server mode. So we have a program that we put there running on either end of this secured pipe. In the pipe, I run a little thin binary protocol. I call that the control protocol. On that, well, if you're going to open a TLS connection, each side needs an asymmetric key pair. So we generate them fresh. It turns out PKI, the public key infrastructure, is not strictly necessary. All you actually need is a way to know that the key that the other side is using belongs truly to them and hasn't been substituted by an evil man in the middle. So, we'll lean into that, exchange self-signed certificates over our control channel, which we already know is secure because we're trusting SSH here. And that's all you need to spin up the quick connection. As long as you can get your UDP packets to the other end, bingo, we've bootstrapped our security laterally from one protocol to the other. So within Quick, we then open a data stream, and we run another protocol on that. I call that the session protocol. And that is your file transfer. Hey, here are some bytes for a file named XYZ, and we can do our file transfer at the speed of Quick. So yeah, top to bottom. That is the essence of my solution. But enough about that. This is a Rust conference. What do you need to know? Well, first of all, so these two wire protocols that I've implemented, I needed to invent them. And the problem that you have in any such thing is you need to translate messages between some format that is appropriate and convenient for your implementation language, so Rust structs. You've got to be able to translate that to a stream of bytes. Here is an extract of a structure definition. Now, when it comes to implementing the wire format, that is nearly all that I had to write. There's just a couple of crates to do the rest. Some of you are probably ahead of me here. We'll use the SERDI serialization system, and we'll plug in an encoding crate. I chose the bare encoding. You decide how you want your data serialized, plug it in. And then you mark your structure as derived from serialize and deserialize. And yeah, I did a little extra work to make it more ergonomic to use, but there we go. So now I can experiment. I can play with my protocol. I can extend it. I do not need to write code that's messing around translating between Rust and bytes. All I have to do is edit that struct def. The compiler does the rest. That is one heck of a force multiplier. And this actually brings me to the first real key point, the take-home point that I'd like to share. Now, in the same way that we used to say, there's an app for that, well, in Rust, there's probably a crate for that, with some caveats. If you look at the problem through the right lens, at the right level, you may not always find something that's exactly what you need, but there's a good chance. So much useful stuff, there is a discovery problem. I looked the other day, Crates.io has, what, 194,000 crates on it now? Some of them pretty old, maybe not well maintained, some of them not very good. Some of them are all right. And it is 2025, you do need to be cautious. There are software supply chain attacks in the wild. I don't know about against Rust, but obviously there is that possibility. So be cautious. You're still running somebody else's build script when you build their crate. Are you sure it's not going to try and steal your Bitcoin wallet? Well, I did find a light in the darkness. I have no relation with Blessed RS, but I found them really useful. In QCP, I've got like 40 or so direct crate dependencies. On Blessed, they have a curated, categorized list of useful stuff. A really good starting point. Okay, it's all very well to say I use these crates, but what did I actually write here? So I'm going to change tack and tell you about a feature of QCP that was really important to me. Rust made it easy to focus on features that I wanted to build and not have to write boilerplate. So Quick has got all these tuning options. It works really well if you tune it for your network. You tell it the round trip time, you tell it the bandwidth. The network theoreticians amongst you will immediately say bandwidth, acronyms, BDP, bandwidth delay product, the trouble of having short notes. It was clear that I needed a configuration system, but it got complex. In a system like this, where can your config data come from? Well, obviously, I needed a command line interface. Excuse me. Drying up a little. I needed a command line interface to be able to experiment fast. Then when I found settings that worked, obviously I don't want to keep retyping, so I needed a config file. Now, maybe the remote machine might have its own config file with some options that it needs to set. So it gets complicated. You need logic to combine these, you need some system defaults to apply underneath. But it even got worse than that. I realized I needed to be able to specify config that varied with the destination, because sending packets to that data center down the road, compared to sending packets to London, these are going to be quite different configurations. So to get the best out of the system, it's got to vary. So I needed to figure out a file format where you can say, yeah, for this host or this net block, use those options. And then when both the local and the remote specify an option, I needed to arbitrate who wins. So all these options. I realized I needed what I call config debug mode. What do I mean? You look at the system and you're like, where did it get this option from? Well, there was a crate that helped me track config metadata, and it's called Figment. And here's the result. This is a reduced output from QCP. We have got an option that's defaulted, an option that came from a config file, one that I provided on the command line. With Figment to help me keep track of that, and another crate that does the table ASCII art pretty print formatting, yeah, we're getting somewhere here. Great, okay, so change tack again. What about code reuse? QCP is a moderately sized project, about 10,000 lines of code that I've written. But there are still times I thought, yeah, I've used all these other people's work. What can I give back? So as well as publishing QCP itself, I ended up spinning out a couple of crates. And in doing so, making them useful, more generic, not just QCP shaped, I had to learn about traits. And that brings me to my next take-home point. And that is traits. Traits are your friends, and I found them to be the key to abstraction. Now, Rust is not object-oriented. Yes, it's object-ish, I would call it. But if you try and use Rust in a fully object-oriented C++-ish kind of way, you'll get into trouble. Much better to figure out and lean into the differences. Traits are sort of like interfaces. There are parallels in many languages. You get to reuse your code. You've got polymorphism. That is to say, you write code once, have it apply to different types. Traits also let you write extension methods for other types. Basically, some supplementary logic for somebody else's structure. Rust has generics, generic types that let you do this. Rust adds lifetimes. So that's a whole new way to achieve some really impenetrable compiler error messages. But, you know, abstractions are a standard computer science thing, and the right level of abstraction will help you keep your main logic clean. I hope most of you are nodding away here. I've been in the software business long enough to know how important that is. And Rust is not magic. You are not fantastically exempt from the need to structure your work appropriately. You probably know all but the most trivial programs will need some kind of structure or they will become unmaintainable. And Rust is just the same. You've got to think about it. But don't get me wrong here. I'm not trying to advocate for working waterfall style, predefine all your structure, your architecture. We are in an agile world. We can iterate on our structure. The shape of QCP evolved as I went. I didn't know at the start that I needed this trait here or that struct there. The shape just kind of emerged. I iterated. That's the key, iterate. Now, speaking of iteration, I'm not going to apologize for flying the flag for continuous integration. I've been using these systems for my entire career. They make it easier to iterate. It's human nature to be lazy, to not want to run the full set of checks. Oh yeah, no problem. So automate them away. There are many things you might want to do as part of CI. It can get quite elaborate, but the basics, with Rust, really you do not have an excuse. Cargo build, cargo test. If you're using Rust docs, build them. Clippy. If you haven't come across Clippy, the linter, I love it. I find Clippy with a reasonably strict config very helpful to keep my Rust idiomatic because I keep slipping back to C++. That's what I spent most of my career working with. In QCP, my CI has gone a bit deeper. I put in the work to automate a few things that I find useful, but you've got to do what's right for your project. Just about everybody will benefit from the basics. So I'm getting towards the end here. I do have one more insight I want to share, circling back to my professional life. So probably most of you know that C and C++, getting the memory management, the memory hygiene right is so incredibly important, but Rust has changed how I think. This is not hyperbole. How I think about memory management has changed. I can look at C++ and think, oh, crikey, the borrow checker won't let me do that. But, you know, that's the state of the code. Quite often it's client code. The client doesn't want to rewrite everything in Rust for whatever reason. So C++ it is. That'll keep me in a job for a few years, I think. So sometimes I think I'm just a sort of digital plumber, gluing things together. But yeah, I've scratched my own itch here. It works for me. There are people out there finding it useful. There's more I could do with it. I've got more features I want to add. I have a correspondent who runs an AI startup. He's using QCP to move his training data between Europe and the US. He's got, you know, many terabytes there, and it's working for him. I'm a convert to Rust. I'm loving it. I'm looking for ways to use it professionally. If you're on the fence, I would say, hey, come on in, because the water is lovely. Thank you.
All right, do we have any questions for Ross? Oh, yep, one up there.
Number 5. Thank you, great project. I'm one of those people who have to move big files from the other side of the world. Do you have integration between rsync, to which you can give a remote shell, and QCP?
Not at the moment, it's on my radar.
Got one. Do your one first, yeah.
Can I do? Yeah?
Yep.
Ross, I think I would like to ask question. The public internet and actually any network functions on the simple idea that clients are configured in nearly an identical way, or not identical, but with respect to the packet loss. And TCP respects the packet loss and adjusts the outgoing bandwidth accordingly so that we can have a fair share, we can have fair share of the network. So now, switching to UDP or any other protocol which doesn't respect that means that you're kind of eating bandwidth from others. And you might remember that in times of the torrents, when they appeared, like you could put down the entire internet for the school while you're downloading a computer game. So imagine that we all start using this tool. We would be again back to the same problem of slow connections, slow file transfers. Like, is it ethical to do this?
Very good question. Well, it turns out that QUIC does use the same sorts of congestion control algorithms as TCP. It is just a matter of tuning. The default congestion control algorithm is cubic, which is the same algorithm as in TCP, just with some different constants, I should say. So, yes, you can argue that it is stealing bandwidth, or, if you like, not being fair. But on the other hand, don't forget that every network has its own traffic shaping rules. QUIC packets are just encrypted UDP flooding around. They are difficult to distinguish from Netflix, from Zoom, from what have you. Those packets are being shaped. So people who are using different services that look differently, they are getting different treatment at potentially every switching point from A to B. So I don't find it particularly egregious to take a little bit more bandwidth when I need, because I know that all those network operators are applying rules to try and defend their networks, as they should. And so it seems to work. I mean, you can change the parameters. You can use some, if you like, some nastier congestion control algorithms, and there are some out there. For me, though, I'm quite content to stick with the defaults that the QUIC team have recommended and see how they continue to evolve it, because this is really, as I see it, their protocol to keep studying. I'm just a passenger.
Yeah.
Are you making use of multiple QUIC streams?
Not yet. At the moment, I am just a single stream for a single file, but that is next around the corner. I do need to play with that. I'm skeptical, but I'm going with an open mind, see what I find.
Can I have another one?
I don't know. Yeah.
You mentioned X509 certificates and them being a bit annoying. Have you come across raw mode in TLS?
No, I haven't.
I think you can avoid the need for X509.
I'll look that up, thank you. It does depend on whether QUIC and QUIC's TLS implementation will let me use that, of course, but yeah, I will, thank you.
Okay, time for one more person. Anyone? No, don't worry about it. We're going to give a massive round of applause to Ross. Okay, who wants to do an interpretive dance while we have our next speaker set up? Is that me? All right, what I'm going to get you guys to do, because we're on the last speaker, we're all going to stand up. Yeah. Can I have the intern mic on? Okay. We're going to stretch up really high, twinkle fingers. Okay, now without smashing your heads on the chair in front of you, you're going to try and touch your toes. We don't want any OSH complaints, all right? Okay, now we're going to twist. Just make sure, sorry, well, try not to push people off the edge of this. Go back and forward. If you can, without poking each other in the eyes, if you can just do the whole, yeah. Again, no OSH complaints, please. Or I might get fired before the end of the day. Cool. Are we feeling more energized? Bit more blood going to the head? No longer going to fall asleep? Great. All right, you can sit down when you... All right, who's had fun today? Yeah. Can we give it up to Nosh, who did all the catering as well, and how delicious their kai was? Who's had too much coffee? Who can see through space and time? No? I feel like we need to have better effort on that tomorrow, Te whānau. What else we got?
Is the sun still shining outside? Oh, you guys have got the best Wellington day. You haven't been blowing off the harbour. And there's no earthquakes either. So, win-win. Yeah, touch wood. Sorry, team. Might be your first experience. I'm already fired as an MC, so we'll just keep going with it.
Hey, can I have a question for you?
Oh, question for me? Yes.
Is this your first experience with Rust, and how are you finding it?
Is this my first experience with Rust, and how am I finding it? Just for the people on the live stream. It is my first experience with Rust. How am I finding it? Well, I was going to sum it a little bit. That I'm finding it like, how would I explain it? It's like you guys do the basics. It seems to, from all the stories that I'm hearing, you guys do the basics well. And so for us, and what we call that is you have a strong whakapapa, like your base is really strong. And so from there, it makes doing all these cool things so much more cooler and easier, because then you're not sacrificing security or other things while you're doing things from the ground. Did I pass? Did I get a pass for that? Oh, yep, cool. I'll take it. Well, I have been an architect across telecommunications and banks in a very past life. I haven't been a developer, but I understand the basics enough to design stuff. Are we almost there? Or am I going to have to pull out the interpretive dance? Or are you just more excited for my interpretive dance? So our next talk is Rust Rocks Literally. And now that I've just said that, I have lost your bio. So Orhun Parmaksız is a Rust enthusiast with a deep passion for open source. He is the creator and maintainer of several command line tools, including git-glyph.org. Glyph? Yep. git-glyph.org. I think that was my Wairarapa dialect there that was getting a bit in. And binsider.dev. As the lead of the ratatouille.rs, is that? Yep. Project, he's committed to delivering the smoothest and most visually appealing TUI development experience in the Rust ecosystem, continuously pushing the boundaries of what's possible in the terminal. Orhun also takes part in Arch Linux as an official Arch Linux as an official package maintainer. The mic's going out. Official package maintainer for some of the most beloved Rust tools. He is sometimes an amateur musician, graffiti artist, and urban explorer. And hopefully, from that, he is all ready to go. No. I'm going to have to bring out the interpretive dance now, team. Can we have a tech team check? Hold up. Itfano might be tech issues. Nope. All right. So just while he's checking that tech stuff and we get it going, who here is not from New Zealand? Hands up. Who here, this is your first time in New Zealand? Ooh, that's quite a few people. Hands up if you've had to travel more than 10 hours to be here. Oh, these are the people we should be thanking because they are still, hopefully, maybe on a different time zone. Yep, massive clap. Is it the first, oh, that's not even English. We're not even going to go into that sentence. Who's first time here to Wellington? Kapai, that's actually quite a few of you. And keep your hands up if you're from New Zealand and this is still your first time to Wellington. Yeah. Where have you guys come from, if you don't mind? Auckland? And this is your first time. Okay, it's a safe zone, judge-free to follow. Christchurch, yeah. There was someone over here. Auckland, but he has an excuse. Te whānau, he was in Australia, ka pai. Any interesting facts? Does someone want to answer that zombie apocalypse team? Quickly, who had a really cool zombie apocalypse team?
So I would want Jesus there, and my partner in crime wanted Dracula there. So that would be a really, really weird mix.
It's a tag team. Jesus was Indigenous as well, by the way. Just throwing that out. Are we good to go, or am I still stalling? Okay. All right, we're going to hand it over. Round of applause.
Yeah, that's all. Thank you. Okay. We're on time, I guess. That's good. Guys, thanks for making it. I'd like to thank you to myself to making it, because it's been such a long journey from Turkey, but we made it. So yeah, first time here. It's a pretty cool place, literally. So just enjoying it. So Rust Rocks. This is not a new black metal band, just like the font. That's why I put it there. But it's gonna be a bit of a story today, as the last talk of the day. Just wanted to take you to a little project adventure. So yeah. But before that, who am I? That's me, the very accurate representation, as you can see. That rat is not real, though. I don't know who put that there. So, as I said, I came from all the way from Ankara, Turkey. I am mostly involved in open source for a couple of years, writing Rust and just building stuff for the terminal. And I've been maintaining Ratatouille for some years now. I'm going to talk about that today a lot. So, yeah. Apart from that, there are some other projects that I'm also involved in. Mainly Ratsila, GitCliff, and other stuff. You can just check out my GitHub handle there. And I am also doing packaging for Ash Linux officially, and just putting your favorite Rust software onto the repos. And for probably longer than I'm into software, I'm trying to become a musician, just want to be a musician. I'll just talk about that today a bit. So yeah, I have a YouTube channel. You can go ahead and check that out. So if you know me from tech scene, you know me from Rust. If you know me from Rust, you probably know me from Ratatouille. So let's give it a quick summary what this library is. What is it doing? Why it's around? So it is a library for building terminal user interfaces, or TUIs, and it's been around since 2023. Before that, there was TUI-RS, and it was unmaintained. So me and a couple of interested people, we just forked it and created Ratatouille as a community project. We have more than, I don't know, we have many contributors. Lots of apps are being built with it. We have more than 8 million crate downloads on Crates.io. There are some apps. I just listed the big ones here. Tokyo Console, if you're monitoring your Tokyo tasks. There's this Yazi app, which is for File Explorer. Dioxys CLI, Altwin, Gitui, a lot of other stuff built with it. And just to give a couple of names, we are being used by these companies, many more. Netflix, OpenAI, OVH Cloud. And it's been just a great journey since 2023, and more people are building apps with it. And now even like, not even, terminal apps, but like more other stuff. So we're gonna get into that. But let me show you what you can build. So this is a pretty good example of a nice looking and just like a traditional Ratatouille app. This is OpenAPI TUI. It's just for browsing your OpenAPI spec and just going to requests and sending requests and just like playing around. And you might be asking, how do you achieve this in the terminal? How is it like easy and so on? So let me just show you. It's actually quite easy these days. So we added this Ratatouille run method. You just call it. It just gives you a terminal. And then you need to create a loop because Ratatouille is immediate mode rendering. You need to have a loop to draw your widgets and handle events. There you go. You're just writing rat to the terminal. And not very exciting. Maybe it is exciting. So yeah, after that, you just handle your events. So this is done by your backend. We don't provide anything for event handling. So you need to implement that. That should be implemented in your backend. So here we're using Crossterm for that. And all in all, it's just like 13 lines of code. Quite easy these days. Or cheesy, I don't know, to be honest. So a little bit of architecture info. We haven't released this version yet, but we've been just promising people that we're gonna release it. It's been some time. But so this is the latest architecture. Before that, we were using Ratatouille as a single crate. Now it is split into multiple ones. For example, we split the core widgets and other backends. And we have a bunch of widgets there. We have 3 terminal backends built in, and anything that implements the widget trait or backend trait is a widget or a backend. So if you have an idea of a widget, you can just implement it by using the widget trait. Or if you want to render Ratatouille on a platform, you can just implement the backend trait. And yeah, so we have this very flexible modular architecture. So we said, why shall we stop that here, right? We should do more with it. So now we're running Ratatouille on a car dashboard. So this is a project where it uses the car and just like, reads the info from a protocol of Suzuki, I don't know. I didn't look in details, but it can show the engine speed, fuel ignition, and like electrical info, all kinds of things. So these type of things are now possible because people are just, I guess somebody did something crazy and then people realized, hey, I can just run Ratatouille on this thing and then this thing and this thing. So it's been like that for the past 6 months, I guess. I have run Ratatouille on PSP. I had this laying around in my drawer, and I was like, I was playing Need for Speed Most Wanted, and one day I'm like, why am I playing a game on this? I should run terminal apps on this. So that's what I did with the help of the maintainers of Rust PSP because it was not working. It was there were some issues, but we fixed them, and now there is literally a Ratatouille example in the repo. So if you need this use case, there you have it. So we call all of this apps or like porting Ratatouille to different platforms, Ratatouilleifying. This is a term that we came up, and sometimes it means like taking a GUI app and just making a TUI from it. But most of the time, I think it as having a crazy app that runs on a platform that is not designed for, but it works because it's super like simple, and like the backends are super simple as well, so you can just implement it. Speaking of that, here's what you need to do if you want to implement backend trait and just run Ratatouille or like draw widgets on some platform. Really, you just need to implement this draw function where it gives you some cells and like columns and rows, and you can just like place them properly on whatever screen you have or display you have, and it just really works at that point. So we had some custom backends over the past year or 2 years. Just to name a couple of them, and now you can run Ratatouille on your bootloader with Ratatouille UFI, which is great. If you need that use case, go ahead. We have Mousefood, which I'm gonna mention a lot today. We have Ratatouille WGPU, eGUI Ratatouille, Soft Ratatouille. So these are like for example, Soft Ratatouille is like you can just render widgets onto anything, just like an abstraction. I'll show you an example. You can run Ratatouille apps in the with Bevy. So if you have a Bevy game, you can just port it to terminal in some ways. It kind of works. I have created Ratzilla for my website. So I'm basically not my website, but I'm still not using it in production, but it works. So you just build a Ratatouille app and you can just port it to web with WebAssembly, and it just works. So here in this demo, this is Mousefood. It's like a ESP32. Actually, I have it here. I'll show you later in detail. But this little screen can now run Ratatouille as well. So yeah. So I said there's this soft Ratatouille crate. There is this work in progress game by one of our maintainers, Jagoda. She's been working on this text-based RPG, and you see these dialogues and other things are actually rendered with Ratatouille. This is not in the terminal. This is made with Bevy, but they basically use the soft Ratatouille to render some certain parts of the game, basically. So if you have that use case, if you want to blend some terminal aesthetics to your app, that's now also possible. And like I said, today I want to mostly talk about Mousefood, where you can run Ratatouille apps on embedded. This is an e-ink screen, and just works. All right, so what's up with Rust Rux, right? I mean, I'm talking about terminals and so on, and Ratatouille. So I'm going to give you a bit of a backstory. So my inspiration for this talk came from buying a guitar. I'm still practicing and still learning. And then I went to a conference in Berlin. It's called Superboot. And there it was like a lot of music nerds, synthesizers, different instruments, whole kinds of different things. So when I went there, it was like kind of like an eye-opening experience. I wrote a blog post about what happened there, and it's called like, "Am I a Musician Yet?" I just like went through each thing that I did there, and one of the things was this module. Don't ask me what this is doing. It's just like there's a knob and makes noise something. But we built this in one of the workshops, and I realized, well, this is quite cool, but yeah, this is quite cool. I should make something related to this somehow. So I have this guitar, and I want to build something embedded, and there's this Mousefoot crate, so let's build some learning tool for the guitar using Ratatouille and run it on embedded with Mousefoot somehow. And I just submitted the talk after that idea, and it got accepted. So at that point, I was like, oh, okay, now we gotta build it. So talk-driven development, guys, do it. Amazing. My last whatever months of my life was just speed running this, so it's been great. So I want to start small and just build a tuner in the terminal first, and just see how it's like to process some signals and like process some data that I can get from a microphone, because eventually I will do that, right? And it was quite easy, actually. You can use a CPAL crate for getting some audio data, and this will just give you like some samples. And here I'm just like creating a input stream, getting all the audio data, and then I can just use chart widget to visualize what I have, and that just worked perfectly fine. Of course, this is like truncated, but the idea is you collect your samples and you give it to the chart widget as points, and you have this amplitude time graph. If you joined the workshop yesterday, we also use the chart widget, so same thing. And this was pretty cool. Like I made this, and I was like, okay, nice. Maybe let's also show the notes so that we can tune the guitar. And yeah, I'd like to ask, like, any ideas what to do after this point? I'm just curious. All right, so yeah, there's this thing called Fourier transform. Ignore the second part. You know, on the first image, you see you get like some something, and then it gives you other something. So it works like that, and you basically go from the amplitude graph to frequency, and frequency means you can actually get the note representation of whatever data you have. So that's what I did. Just used Rust FFT crate. I don't know if there's any other one out there. I just used like ChatGPT for this, to be honest. Like vibe coded it. That worked. So I just created this FFT planner thing, gave my samples, and just run it. And in return, I just get like some FFT samples. To find the note, I just basically like selected the highest point in the samples and did some frequency calculation there, and just like resulted in like, let's say 440 for the A4 note. So that just worked. So at that point I was like getting the notes basically. You see, like this is like the longest, or just the maximum point is just giving me the note. So yeah, I use these third-party widgets to make it a bit more cooler. So this TUI big text is for this big text, and the bar graph is for just having, you know, more beautiful graphs in the terminal. And you can just like customize it like that. It was pretty cool, right? So I started to port this really simple thing to embedded. I just wanted to, you know, have this working and nothing else for now. I started looking around and realized there are two ways as of now. There's this ESP Hull crate, which is bare metal and, you know, no STD, and development is funded by Espressive. There's this ESP IDF Hull framework, which is STD, so you can use the standard library. It's a community effort, and it requires a custom toolchain. So I went with ESP IDF with STD, because Mousewood only supported that back then. But if you're asking, are we embedded yet? Can I use Ratatouille in no STD environments? And the answer is actually yes. Now you can just disable the STD flag and just run Ratatouille apps on no STD. There's a really good talk by Yogoda in this link, just going through each detail how this is possible. So you can check it out if you're interested. When it comes to toolchain, you need to just install ESP up, and then it will install a toolchain for you. The toolchain is called Extensa ESP32S ESP IDF, and you need to override some things in your cargo toml to use the ESP flash, which is for flashing the firmware onto the ESP device. Speaking of device, this is my whole setup. Back then, I had this T display, which is right here, and just this microphone module, again, here. Maybe I can show it to you. Hold on. It's not super visible from far, I guess. So, okay, I need someone to hold the microphone or something. Ooh. Can you help me? Yeah. So this is the device that I'm talking about, in case you're interested. It's quite small as a screen. And then this microphone module is like this, and just like 3 inputs. So you use like the only 1 pin of the ESP. And this was the whole setup back then. I had this thing on the breadboard, so you just plug it in and it works. I'll show you later. Thank you. So at that point, it seems like we got everything, right? Well, we're gonna use not Ratatouille at that point. We're gonna use Mousefood. So just to be clear, so you need to set up some things before you can just port your app to embedded, and it's actually quite simple. You just need to have everything set up for your display target. So each of these devices have a driver. So you need the Rust driver. So you need to set that up, and then after that, you just need to create an embedded backend, and you just create your terminal as usual, and you can just use that later on, just as usual, like any Ratatouille app, you know. So yeah, like I said, you just go ahead and create the backend, terminal, and in a loop, all the same stuff. This should work, right? Well, at that point, I hit a roadblock. I was not sure if I was doing things right, because, you know, in the beginning, all of this stuff is usually wipe coded, like 50%. So, you know, I was using CPAL for the audio samples, and that was giving me the sample rate. But on embedded, you don't get anything like that. You don't use a library that gives you like, hey, this is your device and this is your sample rate and so on. So what do you do at that point? Because I was just like reading samples, and what is sample rate, right? So I just sat down with a more smart friend of mine, and we just like went the old school way, just working on this piece of paper and just like trying to figure out how to get the sample rate and everything going. You know, did some stuff there, and eventually I realized I can just use a dynamic sample rate. So that's not that exciting, but you basically calculate the FFT, and after that you just like take the elapsed time between each sample reads. So let's say you read 512 samples. After that, you get the elapsed time, and then you can just calculate your sample rate, which that worked. I was super happy, but you know, I was just using a lot of these things in the code, creating vectors, creating hash maps. You know, I was just like happy because everything works in the terminal, but in embedded world, that's not the case usually. If you do all of these things, you'll end up using a lot of memory, and things will start to crash. You just get like crashes. You'll get like memory allocation errors and stuff like that. So in embedded, we want to avoid allocations. Started doing some optimizations, switched to microFFT crate. This is designed for embedded. It uses a smaller and fixed size FFT with no additional allocations. Started using this thing to avoid dynamic resizing and use a fixed size heap allocation instead of just like a vector. This is quite interesting. I didn't delete all the logging stuff, but I put them under a feature. So just to avoid like formatting and so on, and just removed all the hash maps. And just run it with release flag. That was a quite of a difference, and optimization level actually matters. So I have these crate specific optimizations now, because if I go above 1, everything crashes for some reason. Because of these things, like these LLVM optimizations and backend bugs and defined behavior in your code, and bunch of things. So you just need to be careful about, you know, what optimization you're using. In other words, it's just pain to deal with these things. But it's pretty cool that you can actually like do these crate create specific optimizations. I didn't know this was possible. I was like thinking, hey, if you have a optimization level set, it's just set for everything. But it's possible like that. And to debug it, I actually like set the optimization level for each crate, like 100 lines of just this in the cargo toml, and just found the specific ones and just ended up with this. So, okay. The tuner was complete at that point. Let me run it. Not sure if you're hearing it, but I just stick this thing onto the guitar because it's small enough. Just playing it and seeing the notes. It's not a tuner, it's more like a tracking tool at that point, but so this worked. I was super happy. Nice. We made something. So it's now it's getting into presentable state. But why shall we stop here, right? So I just wanted to have like an actual like guitar view in the terminal. So I started working on a custom widget, and you know, implementing it was quite easy. You just like need to implement the widget trait or stateful widget trait, and in there I'm just like doing a bunch of Unicode drawing and stuff like that. I call this fretboard, and you can like you have the tuning and your state and so on. So I created this new Ratatouille widget, which is called Ratatouille fretboard. It can be used like this. So you have your fretboard, you have your state, you can set active nodes, you can customize things there, you know, string names, whatever you have. It runs in the terminal and also embedded. And if you have a guitar like this, it also works. So you can just have this working. I don't know if anybody uses an instrument like that, but anyways. So here's another demo. Here I'm not playing the guitar, but like playing a constant note. And you can see that it's updating real time on the fretboard. And one other thing, it just highlights like the different positions of the same note, which is a bit useful, I think. But I guess you see the problem, right? The microphone works, but like, yeah, the microphone works, but you know, can I connect my guitar directly to that? Because you know, it's like all the environment noise, all the stuff coming in, and it just like disrupts the view a bit. And if we have a small screen, we cannot really display everything in there. So it's a bit like a precision game at that point. So I started working on electronics a bit. Found this chip. It's a op-amp, so it just like takes a signal. I mean, in case you don't know, the guitar jack is just like a signal, so you need to take it and amplify it. Otherwise, it's too weak. So this circuit here is basically doing that, just taking the signal and passing it through some things, some resistors there for configuration and like the gain setting and so on. And it was, you know, it was working, but at that point, you need more voltage to have this amplified. So you need a voltage regulator at that point, and just getting quite annoying, you see. And I went with the second one, this buck converter. In case you're interested, this is not a Rust talk anymore, by the way. We're just getting into electronics. But I went with that because the other one, the AMS 1117, it just like super inefficient. It was just like, you know, drops everything as heat. So you plug in your 9-volt battery, it gives you like 3.3 volts, but just like heats up. And yeah, not that great. The other one is, apparently it can give you some noise, but in my case it worked fine. Like I was getting okay performance out of that. So with guitar connected and everything, let's see. So you see I have this jack connected. Just playing something, seeing things on the screen. This is another view where you can see the frequency. And there's another thing coming up. Now, since I connected my guitar, everything was more. Wait a second. Just realized my laptop isn't charging. Everything is working quite nicely after that point, because you basically get the raw signal from the guitar and just you can map it onto the fretboard like that. So the problem at that point was screen was too small, right? I mean, you cannot even see it. One day I met up with my guitarist friend, just like showed him what I got, and he was like, well, this looks bigger on the demos. And I'm like, yeah, you're right. So some hardware updates. I had this screen laying around, like display. So I just went with this one. It could be probably bigger, but anyways. And started using ESP32 Room 32D. This is for driving the screen, because we cannot we cannot use this anymore. This has the screen built in on it. So there you go. This updates, and you need a driver for the screen, right? Wrong slide. There you go. You have your driver. This ST7735. Somebody created a driver, so it just works. And yeah, there you go. The final, no, not the final, better version. So you have a bigger screen. At that point, I'm just like connecting my guitar and just playing everything from there. Yeah, quite nice working real time. I don't know why I did that at the end, but anyways. So, problem. Everything is on a breadboard. Looks horrible, and it just breaks all the time. There's this loose cable that just like ends up with, breaking everything and so on. So, working on schematics, designed this PCB. I actually printed it. I have it here. Okay, let me just hold up. There you go. So came up with this, ordered it from JLC, assembled everything, and it was working. Quite a surprise. Nailed it, I guess. I don't know. Powered by Rust, Resideo, and 9-volt battery. So I'd like to introduce my latest project to you guys. It's called Tweetar, because we don't like GUIs. So there you go. I have the device right here. So there you go. This is, I put it in a case to make it fancy. Just like open it up, and you have the screen. I have this demo video, but I think instead I'm just gonna play the guitar and show you a live demo instead. So that would be, I think, better. So yeah, show me the cheese, right? You can tune your guitar with this, as usual. You can see like the notes being played and so on. There's this fretboard tracking feature, which is like the same thing as I showed you in the other demos. So you can play a note, see it real time on the fretboard. There's a scale mode, which you can use to practice the scales. This is quite important if you're playing solos. So you can just press the buttons on this little device, and it will, you can just configure which scale you want to play, and you can just like practice it that way. There's this random mode, which is quite fun and kind of addictive. Just shows you a random note, you try to play it. Just gives you points. So there you go. Okay, so song mode. This was quite fun to build. You can load your songs onto this in the MIDI format, and it will show you the notes in order. So you just like play the song, in whatever speed you want to play it. It's not like super nice at this point, because you cannot do it with multiple notes, but kind of works, and you can just practice songs with that. And to get the MIDI files, let's say you go to a website like this, there's usually this download thing, or you can just download from torrent or something, I don't know. And yeah, just use the midley crate for parsing the files. It selects a channel and just parses that. And those also supports Guitar Pro format. I don't know who uses that. It's like feels very ancient, but you can also do that. And what I'm doing is I'm not parsing everything at runtime, but instead I'm just like parsing everything at build time and just creating this module, because otherwise the device just crashes. You don't have that much memory and so on. So putting everything in a module and just importing that basically runs in the terminal. I mean, of course, right? Yeah, so there you go. It's looking a bit bad because my gain is all high, but anyways. So yesterday, started working on the animations on the device. This is not my device, but this is another ESP. So you can actually use Tachyon Effects, which is a animations crate, to run these thermal emulations on embedded. So just works. So I have some animations going on here. One sec. Let me just show you. There's a So that was the animations part. Still working on it. It will get faster. So this is available as a DIY kit, as a prototype, but it works. So I have this little booklet that shows you all the instructions for building this. Let's show you here. And it's also on GitHub as well. There's this GitHub link at the end. I have one copy of everything. So if you have this, you can build the same thing. So I want to give this to somebody who will actually build it and try it out and contribute. So if you have a guitar or if you want to hack on this, come and find me. I'll just give it to you with the condition that you'll actually contribute back and help me out building this, Everything is in there, so don't worry. Okay, I don't think we have time for this, so I'm just gonna skip. But bigger screen, bigger problems. I tried, and I got this error. Memory allocation of 8 bytes failed. Embedded stuff. I'll talk about this later. And as a last thing, I didn't build any of this in the dark. I didn't do everything in my room. I've been live streaming the whole thing on YouTube, so if you want to check that out, I have this YouTube channel, and there are some live streams. There are some live streams there. So more than 100 hours spent on this, and 80 hours was on camera, and I'm gonna keep building it. So it would be nice if you follow me there and see where it goes. Speaking of that, what's next? So bigger screen. I want to turn it into a customizable guitar pedal. Right now it's input only. I will add output and have the screen for customizing the sounds or whatever. It's gonna be quite fun. And at the end, I think I will just do a Kickstarter or code supply campaign for this project. It's available on GitHub. And if you're going to these events, I'll be there to talk about Ratatouille and embedded stuff. And so, yeah. Really important note, if you want to see me building this, please consider sponsoring. It's not for the money, but like motivation. It really motivates me to push things forward. Sometimes for the money too. Not gonna lie. All right, thank you everybody.
All right, we have time for one, maybe two quick questions. Does anyone, one down here?
Hello, it's Pink.
Hey.
We met last time 7,000 kilometers away in a meetup.
It was great, thank you.
Anyway, when can I play Twitter Hero?
Coming soon. Yeah, microphone and cable mode now possible. I have this, like this is the open version. You have the microphone here and input here, so you can just press here, switches the mode. So now it's there.
Any last burning ones? Lucky last.
Are you planning on adding any backing tracks?
Yeah, would be nice. I think a metronome would be also nice. A lot of things to do, man. This project consumed my whole life, so looking forward. Thanks for the idea.
Okay, round of applause.
One thing. I was planning to show you a live demo, but we don't have time. So maybe now, if you are still around, let's do that now. So.
Or I could do a quick wrap up and you can outro us off the stage.
Yeah.
Yep. If you want to leave it there. I'll never say no to some waiata. All right, I'm just going to quickly wrap up and then do a karakia and then you can outro us with your music. Mean. All right. That's very feedbacky. All right. So we're back here today we're back tomorrow. My brain's about 1,000 miles ahead of where it should be. So the venue opens tomorrow at 8:15 with talks starting at 9 a.m. And if it's anything like today, it's going to run to time, okay? It's a whānau, so if you're late, you're late. But we will kick off. You're welcome to hang out a bit longer in the co-creation space as well if you wish. We will be closing up here about 6:30 p.m. I will remind you again that we have, it's not on my tag, the Discord channel. So there's lots of people already posting about where to get beer, where to get food, where to get beverages of other kinds. So please make use of that. If you're, that's my timer. If your social battery's out, that's kei te pai. Go faceplant a bed somewhere or couch. Preferably your own ones and not some random other person's. But safe space, we don't judge you te whānau. Other than that, I haven't been given anything else to talk to you guys about. I'm just going to close us with a karakia and then we'll let the music take us out. Ka pai? Manawa mai te mauri nuku. Manawa mai te mauri rangi. Kia mahara ki te whakaaro, kia mahara ki te aroha. Kia mātou, kia pakari, kia aroha teitahi ki teitahi. Hei o ranga wairua, hei o ronga hininaro. Hei o ronga tinana, hei o ronga nākau. Hei o ronga whānau, kia mauri tū, kia mauri ora. Haumi e, hui e, tae ki e. And we'll see you all back here tomorrow. All right, take us away.
Yeah, let's do that. maybe can I talk into this? Yeah. So just some info about this device. Like I said, I connected the input here, and you just press this button here to switch between the microphone and jack. You see the raw samples coming in from the microphone, and you can switch to the jack input. And if you turn this little thing over there, it should show some stuff right there. There you go. Those are like the raw samples. So if I just play something, see the signal coming in, and you can just use this knob to adjust the gain on this. So now if I hit a string, I mean, it's E3, or like, let's do, it shows E5, it should be E4, I don't know why it's doing that. But yeah, so B3, D4. So just like reads the signal and just shows it real time. Going to the fretboard. This is FPS, by the way, this little number here. I'm trying to show it to you, but it's really difficult. Okay, this one is FPS. We'll get higher FPS, don't worry. So live mode, let me try to show you that. So high pitch works better usually. You won't get much detection for the low strings, but if I scroll the fretboard here a little bit and just hit some stuff to show you how it looks. I don't actually see it. You know, I play it and you see it on the fretboard, basically. I remember. I forgot the song, sorry. Anyways, there you go. You got the idea. You go ahead and press this button over here. Sorry, not that button. I'm so confused still. So that's the scale mode. I just cannot stabilize this. So you see the name of the scale up there and the root note. You can change that by pressing some buttons. Is this okay? In case you're wondering why this is important, this is for basically, I mean, I use this for solos mostly. So let's try to play blues in the A note. Where's, yeah. So I'll try to play this one sec. Something like this, so you get the idea. Just like to learn the scales, you can use this. Let's go to random mode. I'll try to play this. Don't laugh at me if I fail, but. It's really hard for me right now, especially being on the stage. Okay, I challenge everybody to test this out, actually. So yeah, you have the point right here, so it just resets after a while. Okay, the song mode is also similar. It just shows you the notes. So let me play something, and you see it will switch to the next one. Yeah, basically like that, and you can switch to different songs. I load some stuff into this. 1 second. Of course, Minecraft. So that's all that it can do. Also, there's another thing that I want to show you. Like I said, this is the open version. This is the case for it. I made it using I melted plastic, basically. You gotta do what you gotta do, man. So you see everything is on there, and if you turn this on, it's basically the same, but without the animations. So at that point, it just it was not flashing because of the optimization level thing. So I decided to not touch the firmware on this, so it's a bit old, but works the same way. It actually works better because it's in a case, doesn't have much noise. There's also the mini version. 1 sec. So this is the mini. Like I showed you, this is my first prototype, and it only supports microphone. So you need to plug this in, and basically the same firmware, literally same firmware, but without the jack input. So yeah, there you go, the microphone right there, and it is a longer fretboard, which is nice. But like I said, this was a really small screen, but maybe it could be used to as a clip onto the guitar. But yeah, since we're just vibing on the stage, I'm gonna also show you, just flexing my stuff here, guys. So fun, my best talk ever. So yeah, yeah. I know you guys are just nerds, so you're gonna enjoy this anyways, right? Great. There you go, the circuit board. You have this nice Resideo logo on there, and also this is only for Rust Forge, so Rust Forge edition right there. I have a couple of ones here. If you want to have this as just as a gift or just to show off, I can give it to you. Just let me know, because I ordered more than I need. So there you go. Just find me after the thing. And I guess that's all, everybody.